Hello, Professor David Bose.
Hello.
My name is Sushil. I am the faculty advisor of the OSS student chapter.
Nice to meet you.
My pleasure. Yeah. So, Sandeep, what time do you have by your watch? Sandeep, you're muted.
Yes, 9:27. I will start at 9:30.
Okay, you have a few moments. Okay. Professor Bose, have you had an occasion to travel to India before?
I have not. I hope someday.
Great. So the next time we are allowed to meet in person.
I look forward to it.
Thank you. We'll make it a point. Thank you.
Yeah.
Okay, I think we should start. Hello, everyone. Am I audible?
Hello.
Yes, Sandeep.
Okay, yeah. Thank you. Hello, and welcome to the second day of the conference. I am Sandeep, and I'll be chairing the first session of today's uh, conference. And the first session is nanophotonics and biophotonics. Before starting, I just want to remind that please ask your questions after the talk is over. And if you have any questions, raise your hand and we'll unmute you. So having said that, it is my great pleasure to introduce our first speaker, Professor David Bose. He is the director of the Neurophotonics Center at Boston University. He received his BS in physics at Rensselaer Polytechnic Institute and PhD in physics at University of Pennsylvania. He is the founding president of the Society of Functional and Near-Infrared Spectroscopy and founding editor-in-chief of the journal Neurophotonics published by SPI. Dr. Bose was awarded the Britten Chance Award in Biomedical Optics in 2016. He was elected a fellow of AIMDE, SPIE, and OSA in 2007. As a director of the Neurophotonics Center, he facilitates the development and application of novel optical methods to address a broad range of neuroscience questions from basic science to clinical translation. His own research efforts focus on neurovascular coupling, cerebral oxygen delivery and consumption, functional near-infrared spectroscopy, and physiological modeling. During his academic career, he has supervised more than 50 students and postdoctoral fellows, and he has published over 300 research papers that have received over 40,000 citations. His today's talk is Functional Brain Imaging with Functional Near-Infrared Spectroscopy in 2023. With this brief introduction, I would like to welcome Professor Bose to deliver his talk. Professor Bose, yeah, now you can share your screen.
Okay, thank you very much for the introduction. I will share my screen. I think you can now see my screen, Is that correct?
Yeah, I can.
Okay, great. All right, well, I think I'm going to be telling you about some biomedical applications of near-infrared light, something I've been playing around with for quite some time now and having a lot of fun. I started off in a more traditional physics optics lab when I was a graduate student, but I became more and more interested in how we could probe tissue using light and trying to understand how light scatters through tissue. We're able to look at hemoglobin, and it turns out you can actually use that to look at brain function. And so that was first demonstrated actually in almost 30 years ago now. And so I'd like to just tell you a little bit about that history of where this technology derived from, how it evolved over the last 30 years, and where it's going in the future. There's this movie, maybe some of you saw it in 2002, called Minority Report, actually, where they were using near-infrared light to measure brain function in these people. So it was very much ahead of its time, and they were predicting where this technology was going to be in the future. So the basic idea is, and this was first demonstrated, well, actually before Franziopsis, but pulse oximetry uses light and probes the hemoglobin content in your tissue. If you use near-infrared light, you can actually get light to penetrate many centimeters through tissue. So this is the absorption spectrum of hemoglobin. The dominant absorbers in tissue in the visible and near-infrared light are hemoglobin. And so at 600 nanometers red light and beyond, hemoglobin absorption is decreasing quite dramatically. And you reach this window, transmission window, and you go to longer wavelengths, water absorption gets larger and larger. So we've got this window between 700 and 900 nanometers where actually light can travel quite far, hundreds of centimeters through tissue before a significant amount of it is absorbed. And so Franziopsis in 1977 showed that actually if you used 800 nanometer light, you could monitor the amount of hemoglobin in somebody's brain. And they showed modulation of that hemoglobin. And so during the 1980s, several people wanted to use that technology to actually apply it in clinical situations in newborn infants and adults to try to make clinical assessment of the health of the human brain. And already commercial systems were being developed by 1990. And the idea, actually, the physics is quite simple. You're just doing absorption spectroscopy. There's the Beer-Lambert law. You just look at the logarithm of the intensity of the signal relative to the input intensity. That gives you an optical density, and that optical density is equal to the absorption of the chromophores in the tissue times the path length of light through the tissue. Now, in the case of tissue, light doesn't travel straight through the tissue, but it's scattering on a very short length scale. And so you have to understand the effects of scattering and how that changes the path length of light through the tissue, so that you are able to do this quantitative absorption spectroscopy. Now, we actually want to use this to look at brain activity. So maybe you know something about brain activity. It's related to neural activity. Neural activity are electrical changes in the electrical potentials of neurons. What does that have to do with hemoglobin and absorption? Well, when there's neural activity, it actually produces a blood flow response. So neural activity requires oxygen and glucose to support that neural activity. So whenever neurons are firing and active, they actually need more oxygen and glucose in order to support that greater activity. And so they actually release molecules that diffuse to the arteries in the brain, and it causes the arteries to dilate, and it increases blood flow, and that will deliver more blood volume and more oxygenated hemoglobin. At the same time, there's an increase in oxygen consumption, and so there's an interplay of all of these factors, and you get changes in blood flow, cerebral blood volume, cerebral blood flow, cerebral blood volume, oxy and deoxyhemoglobin. And so you might see a response like this. This is showing if you have a brain activation, and a common task we might do, say, is tap your fingers. And if you look at the motor cortex over here, you'll actually see changes in oxyhemoglobin in red. Oxyhemoglobin goes up, and you'll see deoxyhemoglobin go down. Okay, so this was actually first demonstrated 28 years ago in 1993. There was a series of 4 publications from different groups. They showed that you can actually measure this change in blood flow, resulting in an increase in oxyhemoglobin, decrease in deoxyhemoglobin. So this was a group in Berlin, Germany. This is a group in Tokyo, Japan, showing very similar effects. So the idea is you have to put a light sensor on the scalp of the head, and a light source and a light sensor, and you want that light to penetrate through the scalp and skull and reach the brain. And so when I was first talking about this long ago, nobody believed that actually light would go through the scalp and get into the brain. So we ran simulations, Monte Carlo simulations of how light diffuses through the scalp and skull, and you can see this is a source, and this just shows the fluence profile of photons diffusing through the scalp and skull. I have a detector some distance away. This is the probability of light reaching from some point in the tissue to the detector, and if you take the product of the source profile with the detector profile, you get the sensitivity profile. This is light that travels from the source, reaches the detector. Where have you sampled in the tissue between the source and detector? So remember, photons are scattering on a length scale of 1 millimeter. They're diffusing throughout the volume of the head. Some of those photons scatter and are detected by your detector. And so red are regions where you're highly sensitive to the absorption changes in the tissue. And you can see that here's the cortex, the gray matter of the brain. You can see that you are sensitive to the superficial regions of the brain close to the skull. So diffuse light, light does diffuse through the scalp and skull and interrogate the brain, and then come back out where it can be detected. But we can only see regions of the brain that are very close to the skull. That is, the light doesn't diffuse all the way deep into the brain. But fortunately, as it turns out, the cortex is the vast majority of the gray matter of the brain is very close to the skull. And this is where the interesting functions are occurring in the brain. And so we can use that near-infrared light to really interrogate the brain activity patterns. I'll skip that. So the first papers were in 1993, Over the first 10 years, after those first papers, there was 148 total papers in the field. And they covered many topics. Basically, already people were showing that you could look at motor tasks like tapping your fingers, or you could measure the brain activity as somebody who was walking down the street, or if you presented visual stimuli to the subject, you could see their occipital cortex on the back of their head activated. Cognitive tasks activate the prefrontal cortex. People could were demonstrating that they could measure all of those brain activity patterns. They were applying it to various clinical conditions like schizophrenia and stroke. I'm going to tell you a little bit about what we did those first 10 years of FNIRS, where we were comparing it with functional magnetic resonance imaging, which was invented pretty much the same time. Using big magnets, you can get really high resolution images of brain activity. And actually that field was very interested in using near-infrared light to help them better understand the origins of that fMRI signal. This doesn't work, I'm sorry about that, so I'm just gonna skip over this. This was showing some just early movies of brain activation. So I was telling you about magnetic resonance imaging. So magnetic resonance imaging can give you a really beautiful image of the brain. You can get a structural image of the brain, and you can also do functional images. So this is showing in the colored regions here, you can see the regions of the brain that are activated when this subject was tapping their fingers, for instance. Now in this study, they placed a source, a light source and a light detector over those regions so that they could simultaneously measure the hemoglobin concentration changes during brain activation and during the fMRI measurement of that brain activation. And they were correlating those measurements. This was another group that was doing that. They got an MRI image. They had an optical image overlaid at the same location, and they could show nice spatial correspondence of the two images. And then, you know, here's looking a little more detailed at the temporal correlation. And basically, what's happening here is you're seeing this modulation of the optical density going up, coming down, going up, coming down, going up, coming down. Basically, the subject is at rest, then they tap their fingers and the blood volume increases, absorbs more light, then they stop tapping their fingers and the signal goes down, and it just keeps oscillating like that. The colored lines are the near-infrared light. The black line is actually the bold fMRI signal, and you can see a strong correspondence between the two signals. Okay. There was early on, it was interesting, people were using 780 nanometers with 830 nanometers. And the reason for that was that they wanted to use wavelengths that were close together. I need to find that image again. Close together so that it would travel the same path length of light through the tissue. But you need to be on either side of this isospectic point of hemoglobin. So you want to wait, this is at 800 nanometers, the absorption of deoxyhemoglobin is the same as the absorption of oxyhemoglobin. You need, if you want to do spectroscopy, you need wavelengths preferably shorter than 800 nanometers and greater than 800 nanometers, so you can have sensitivity to distinguish the different concentrations of oxy and deoxyhemoglobin. And so early on, people were using 780 nanometers with 830 nanometers because they thought it was a good idea to have those wavelengths close together. But it turns out that actually that gives rise to crosstalk. And so we and many others realize it's you want to separate those wavelengths, get a bigger differential in oxy and deoxyhemoglobin, and that will give you a better estimate of the hemoglobin concentration changes. And so now, today, everyone's typically using like 750 nanometers with 830 nanometers to get more accurate estimates of the hemoglobin concentration changes. During the second 10 years of the field of functional near-infrared spectroscopy, we're seeing a rapid growth in the number of papers that were being published every year. And just a lot more technologies being investigated for improving the measurements of brain activation. There were a number of studies getting much better at cross-validation with fMRI, and using multiple light sources, multiple detectors, getting images of brain activity. So here in the blue, you're seeing images of decrease in deoxyhemoglobin during, again, this is a finger tapping task. So this is over the motor cortex here. And this was using a very brief 2-second stimulus. And you see, again, the very classic increase in oxyhemoglobin in red, the decrease in deoxyhemoglobin in blue, and the black line is the fMRI bold signal. If we normalize all of these signals, you can see that actually the deoxyhemoglobin and the bold signal follow each other very well. If anyone has questions, feel free to interrupt me and ask questions. Now, the bold signal was expected to match the deoxyhemoglobin signal very well, and that was because deoxyhemoglobin is paramagnetic while oxyhemoglobin is diamagnetic. And as a result, the deoxyhemoglobin will perturb the magnetic field and change the MRI signal that one measures, whereas oxyhemoglobin does not do that. Right? So fMRI is able to get maps of changes in deoxyhemoglobin in the brain. And so basically this was just showing a correspondence in the temporal profile of the deoxyhemoglobin signal measured by near infrared light with the deoxyhemoglobin signal measured by fMRI. And we could also extend that to look at spatial correspondence across many subjects. Now to get, these were all measurements typically made, most measurements of brain activity with FNIRS are made with just a low density arrangement of sources and detectors. And typically the source and detector will be 3 centimeters apart. And that's because you want the light to diffuse through the scalp into the brain. If the source and detector are too close together, you just measure the scalp. You don't actually ever see the brain. And so 3 centimeter separation, that basically means your spatial resolution is going to be about 3 centimeters. You can't see anything smaller. The way to see something smaller is you need to have overlapping measurements. And those overlapping measurements then allow you to do a tomographic image reconstruction. Joe Culver's group and our group were making advances to improve the spatial resolution and going to high density arrays of sources and detectors, showing that you could really push spatial resolution to about 10 millimeters. Now, we want to measure brain activity. To measure that brain activity, we have to, the light has to diffuse through the scalp and skull to get into the brain. So what that means is actually we measure hemodynamic fluctuations in the scalp very well, not just the brain. And it turns out there are many fluctuations in hemoglobin and blood flow and blood volume in the scalp, not just the brain. So every time your heart beats, you can feel your pulse, right? Because the heart is pumping blood into the arteries, causes the arteries to expand. So that happens in all of your arteries. And so this is, the green lines are measurements from 4 different corners of the head. And this is spanning 50 seconds, 60 seconds, and you can see the cardiac pulsatility happening every second, right? So the heart beats about once per second. So you can see that cardiac pulsatility very well. On a slower time scale, you can see a slower oscillation as well. Well, it turns out this is related to respiration. When you inhale and when you exhale, it causes actually a slight modulation in your heart rate, which then causes a modulation in your blood pressure, which modulates how much blood volume there is in your arteries, right? So all of this physiology is affecting blood volume in the scalp. And that makes it harder to see the brain activity, that's happening beneath the scalp, beneath the skull in the brain. And so people began to understand this more and more, and it was very important to develop strategies to help you do signal processing to distinguish the signal from the scalp from the signal in the brain. And so many approaches were tried and developed over the years. It turns out the most robust method for dealing with this is to use a short separation measurement, say that source and detector 8 millimeters apart, that sees only the scalp. And then you also have your detector 30 millimeters away, where the light is able to penetrate more deeply into the head and see the brain as well as the scalp. So in this case, you have a measurement that sees only the scalp. You have another measurement that sees the scalp and the brain. And so you can use the short measurement to filter the scalp from the long measurement, right? So this can work very well. So for instance, here's an example about a few minutes of data. Again, red is oxyhemoglobin, blue is deoxyhemoglobin. The green is the sum of the two, which is total hemoglobin concentration. And there's this brain activation at every shaded box here. And so you don't really see a pattern that clearly correlates with brain activation. That's using 3 centimeter separation. If you use the 8 millimeter separation, it turns out the signal looks very similar. So the long separation that should see brain and scalp looks a lot like the short separation that sees only scalp. But if I now filter this short separation from the long separation, what I get left is this. This is the residual of that filtering. And now you can clearly see every task, every brain stimulation, we get this expected response of an increase in oxyhemoglobin, right? So that filtering is very powerful for improving your estimates of the brain activation. And now everyone's using that technology to improve the measurements of brain activity. So also in the early days, this is now the second decade of functional near-infrared spectroscopy, people began to use near-infrared light in other ways to measure brain activity. So functional near-infrared spectroscopy is doing absorption spectroscopy of hemoglobin, but you can also use the Doppler effect. So when photons are scattering from moving red blood cells, they get Doppler shifts, and this results in a fluctuating speckle pattern. And so we can actually monitor the temporal fluctuations of that speckle pattern and learn about how fast the blood is flowing in the brain. And so you can also use that to measure blood flow changes during brain activation. And so that proves to be useful. Other technologies that were investigated, everything I've been describing to you is using a continuous wave light source. You just measure modulation of the intensity of the light you detect, but you could also use pulsed lasers. And so you could put a picosecond pulse of light into the tissue, and then you measure the light that comes out, say, a nanosecond later or 2 nanoseconds later. And the longer you wait, the longer the light has traveled through the tissue. And so that's very useful because the continuous wave light, basically, when I put light into the tissue, some photons travel a short distance through the tissue, other photons travel long distance, right? Their photons are essentially undergoing a random walk through the tissue. So if I have a laser pulse, I can then gate and measure specifically only the short path lengths or measure the longer path lengths. And if I measure the longer path lengths, then I'm selecting photons that have traveled deeper into the brain and improves my sensitivity to brain activity. This helps me also distinguish brain activity from the confounding signals that are occurring in the scalp. And so nice time domain systems were built for doing that. Okay, and advanced to providing images, for instance. Okay, so another nice thing is with a continuous wave light source, we need to have this 3 centimeter separation distance between the source and detector so that the light we detect has been able to travel deep enough and see the brain. Well, if you use a pulse of laser light, you actually can keep that source and detector at the same location and just wait longer. So you can put a pulse of light in and then wait 2 nanoseconds, and the light you detect then has traveled deep into the brain and come back. Now, the advantage of doing that is your sensitivity profile now has a much better spatial resolution, right? So with a 3 centimeter separation, your sensitivity profile is spanning, say, 3 centimeters. You have poor spatial resolution. Time domain, you get now like a 1 centimeter spatial resolution. The photons are confined to a much more small location. Okay. So the first 20 years, people were developing instruments that were big, heavy instruments. But now, in the last 10 years, electronics have been getting more and more powerful, more and more small, and people started building portable, wearable, functional near-infrared spectroscopy systems. So these were some of the early systems that were built, and the technology has been getting even better. So it was about 10 years ago that actually the field had grown quite large, and we started the Society for Functional Near-Infrared Spectroscopy. This happens every 2 years, the conference, and it's a lot of fun. So if you ever have the chance to come to one of the meetings, I hope to see you there. To celebrate 20 years of the field, there's this, we organized this very nice special issue in NeuroImage. If you want to learn more about all of the applications of the technology and technological advances, I highly recommend you go to this issue in 2014, where 58 articles were published. You know, since then, there's now probably 600 papers published a year in the field. The field is becoming quite mature. The technology is still growing, and more and more applications are being found. So this is, for instance, one application that we worked on where we wanted to assess pain in the operating room. So patients who are undergoing surgery will be put under anesthesia, which will help make them sleep. But they also need to be given an analgesic, which will make it so that they don't feel pain. So it's very different things. Anesthesia helps them sleep, but analgesia will block the feeling of pain. So a very bad thing is if you put somebody to sleep, but you don't block the pain. So they don't remember feeling pain, but their body remembers feeling pain. And that can lead to problems after the surgery where their body has been sensitized to very painful experiences and they'll continue to feel that pain. So an anesthesiologist needs guidance to make sure that the patient has enough analgesia to make sure they don't feel pain during the surgery. And so we know how the brain responds to pain, And so you can actually try to measure brain activity in a patient undergoing surgery to see whether or not they're feeling pain. Right? They're sedated with anesthesia, so they can't tell you I feel pain. But their brain can tell you if the brain is processing the pain. And so we've been demonstrating that this is possible to do, and we're now working to bring that towards the clinic. So I told you the technology is advancing, so people are making larger and larger arrays of sources and detectors that will give them high resolution images of brain activity over the whole head. Is becoming more and more like an fMRI machine. So here we're beginning to lose the advantages of the portability of fMRIs, right? So that's where wearable systems now are advancing even more, where we're trying to achieve this whole head coverage with systems that allow you to walk around in the everyday world. And so as we approach the future, I think it's going to be quite natural where we have these wearable systems, just like we have a smartwatch that can measure our pulse and our blood oxygen levels as we're walking. We can have these devices on a cap. I'm making caps now like this that I can 3D print, where I'll have light sources and detectors measuring my brain activity as I'm walking around. So we can make these devices just about 10 millimeters in diameter, and we'll make these high density systems very portable. So many groups are working on this now, making really great advances, and companies are getting into this technology as well. Let me skip over this stuff. So I think just to summarize, there's lots of really important applications where people are using this technology to measure brain development. You can actually, this is fun, measure the activity of 2 or more subjects who are interacting, perhaps playing a card game or socializing, and you can see how those brains interact together. People are developing brain-computer interfaces using this technology, integrating with EEG to have nice advantages. The field is going to continue to grow very rapidly, and I hope to see many of you there at future conferences, and I'd be really happy to have some discussion about this technology if you'd like to discuss it further. Thanks for your attention.
Thank you, Professor Bose, for your delightful talk, and I think we can have some questions here. So if anybody has any questions, they can ask Professor Bose. You can raise your hand and I'll unmute you.
There's a question in the chat.
So Dibbasankar, I'll unmute you. You can ask.
This may be, I can read the question, maybe off-topic question, but how much of this technology can be used to probe other mechanisms non-invasively in other parts of the body? Say non-invasive glucose detection in blood. So absolutely, many people have tried that. I think if you look in the literature, you could probably find dozens of different approaches people have tried, and also literally dozens of different companies have tried to develop technology. I think one way of doing it is going into the infrared, say from 1100 nanometers to 1600 nanometers. Glucose, has good absorption fingerprint at those wavelengths, and people have tried to develop that technology, and it works. And the challenge for the last several decades has just been making it precise and accurate enough to guide, for instance, a diabetic in giving themselves insulin shots. I think that actually recently now, those technologies are sensitive enough, and we're beginning to see devices being marketed to help diabetics, better monitor their blood glucose levels. That's one application. Another application is cancer screening. I mean, the whole field of biomedical optics is using light in many different ways for diagnostics, and for therapeutics.
Any other questions?
Sandeep, I have a question. Can I?
Yeah.
Okay. Professor Bose, this was a very fascinating presentation, and we are in the field of light transport in disorder systems, so aware of diffusion, quasi-diffuse light, snake light, and all that terminology.
Yeah.
I have a question which dates back related to the research that your group did, not your group, Arjun Yod's group did in UPenn. Listening to your talk, some reminiscences of that time. Your group proposed the technique of photon density waves for biomedical imaging that worked as separation in time for diffuse and non-diffuse light. Do these probes also use some such modulating photon density or some such technique for time separation? Can they use that?
Yeah, absolutely, they can. I mean, it turns out, right, so I had the pleasure of working with Arjun Yod when I was a graduate student, and working on these diffuse photon density waves. That was a lot of fun. When it turned out so there you modulate the light source, say at 200 megahertz, and you can measure a phase delay, and that allows you to quantify the path length of light through tissue, the average path length, and that allows you to actually quantify the absolute absorption coefficient. Here in this application, we're not quantifying an absolute absorption coefficient. We're quantifying the change in the absorption coefficient. So we're lucky because we have brain activation, which changes hemoglobin concentration, right? And so that allows us to use simpler continuous wave light, and just quantify the change, and that's all we care about. Right? Okay. However, the frequency domain, 200 megahertz diffuse photon density wave still is very useful for applications where you want the absolute absorption coefficient.
Yeah, of course. Thanks.
Right.
Thank you very much.
There's another question in the chat box.
Another question. Can you please tell some details about the detector used? Excellent. So those wearable systems, so long story, the early days, people were using photomultiplier tubes, very sensitive photon counting detectors. Then when we started building our first imaging systems, we were using avalanche photodiodes. They were just more robust than the photomultiplier tubes, and they were sensitive enough. Most recently, with these wearable systems, just using pin photodiodes. The amplifiers you can put on these silicon photodiodes allow you to get noise equivalent powers of like 150 femtowatts per root hertz, which is plenty good for measuring these brain activity patterns. So, I mean, you can go out and get yourself a $1 LED and a $1 photo detector and wire it up, and you could be measuring some brain activity patterns. It is really quite nice how inexpensive you can make these devices.
Any other questions? Okay, Professor, I have a question. So you can measure the brain activity using, measuring the current also, right? So is there any correlation between this current measurement and this hemoglobin density measurement? Is there any correlation?
Sorry, correlation between hemoglobin and what?
Basically you are measuring the hemoglobin density, right? By probing it with a inner light. But you can also measure the brain activity by measuring the current.
I'm just not hearing you well. By measuring what?
Current.
The current. So like with EEG, measuring the electrical potential changes? Yeah, exactly. Yeah. So the electrical potential changes, the neural activity, right, is happening on a time scale of tens to hundreds of milliseconds. And when the neurons fire, they release these molecules that then diffuse to the arteries, and it causes the arteries to relax and dilate, and that allows the blood flow to increase. That time scale of the molecules diffusing to the arteries dilating and blood flow increasing is on the order of seconds, right? So the electrical signals are occurring on time scales of 100 milliseconds, but the hemodynamic response occurs on the time scale of a few seconds, right? So they're very different time scales. It also turns out, like the EEG electrical signals, you're measuring basically synchronous electrical activity, and EEG is not well spatially localized, right? Electrodes pick up signals from all over the head, whereas the near-infrared light is very well localized, measuring the hemoglobin concentration, right? So it turns out these two technologies, they measure different temporal scales, they measure actually different spatial regions, so they're actually very highly complementary, right? So more and more people now are are combining the technologies to try to learn more and more about brain activity. So a few people have done that recently, but there's a lot more to do there. So I think over the next 10 years, we'll see a lot more good studies being done combining the electrical measures with the hemodynamic measures to teach us more about the human brain.
And another question is like, basically, if you use a temporal, like a pulse laser, so you can detect like at different levels of the brain, right? But you said like, suppose you are measuring up to 1 nanosecond, so it will come from a particular distance, and if you go to a higher time frame, so that will penetrate more. But in diffusion, can you like separate these two things? Like, can you image a particular cross section of the brain from this time measurement?
Yeah, I skipped. I went through it quickly. So like, you can, if you have 0.5 nanoseconds, you're only seeing the scalp, right? And at 1.5 nanoseconds, 2 nanoseconds, you're seeing the scalp and the brain, right? So you can use a filtering method to help you now distinguish, the brain signal. So you have the scalp only measurement, and you can filter that out from the longer time delay to get the brain only signal, right? So you can do very crude separation of brain from scalp using time delay, right? Just like as I described earlier on, how you can do that with a short separation versus a long separation.
And what will be the resolution for that, like with the temporal measurement?
The temporal resolution, 500 picoseconds. We've done it with 500 picoseconds.
And the spatial resolution, you can like differentiate between two layers of the brain.
Yeah, the spatial resolution is poor, right? So I would say you can distinguish, say, that the top 10 millimeters from the bottom, right? So you can really distinguish 2 layers. You can't do better than that.
Thank you, Professor. I don't see any more questions. So thank you, Professor,
Great.
again for
thank you. You're
wonderful
welcome.
talk. Yeah, thank you.
I'll stop sharing. Thank you, everyone, for your attention.
Okay, thank you. So I think we are actually out of time, but our next speaker is already here, I think. Yeah, so the next speaker is Dr. Ravitej Uppu. Dr. Uppu is an assistant professor in the Department of Physics at the University of Iowa. He carried out his PhD research on nano-optics and random lasers at TIFI, India. Subsequently, he gathered postdoctoral experience on nanophotonics and quantum information processing at the University of Twente and Niels Bohr Institute. His research on quantum dot single photon sources, quantum secure communication, And programmable photon correlation was covered in the Dutch and Danish national media, along with several online science news websites. His recently founded research group in Iowa will develop deterministic entangled photon sources for applications in quantum imaging and sensing. And today he will talk about scalable quantum dot single photon sources. So with this brief introduction, I'd like to invite Dr. Rupu to give his talk. I think you can share your screen now. And we are actually ahead of time, so we can take 5 more minutes.
Sandeep?
Yeah.
What was the comment? We can take 5 more minutes as in?
I mean, Ravita Yupu can take 5 more minutes for his talk, like he can use 35.
Oh, that's what you meant, yeah.
Dr. Yupu, you can share your screen.
Can you see my screen now?
Yeah, we can.
Yeah, perfect. Great. Thank you. Well, good morning or like good day, everyone. We are on pretty different places at the moment, but that's the nice thing about virtual conferences, right? So yeah, my name is Ravi Tejupu, and currently I've just started my appointment at University of Iowa under a month ago. What I will talk today about is quantum dot based single photon sources, and also how can you make them scalable. And I'll try to introduce and cover several different aspects in my title. And so this work that I'll present today was carried out at the Niels Bohr Institute in Copenhagen, at the Center of Excellence for Hybrid Quantum Networks. So, and it's a pretty large consortium like group at Niels Bohr Institute, which is pretty interesting because it covers quantum nanophotonics, the research group led by Professor Peter Loda, optomechanics with Albert Schlieser and Anna Sorensen's theoretical quantum optics. So it kind of comes together to look at problems bigger than what only optics or only optomechanics can deal with. So my particular topic that I'll cover today was largely in the group of Professor Peter Loda with on quantum nanophotonics, which is, so we are a few people working on nanofabrication, on optical spectroscopy and spin physics of quantum dot systems and many things. And in particular, I would also like to acknowledge, apart from my group members and wonderful colleagues, our collaborators at Ruhr University Bochum, Andreas Wick and Arne Ludwig, and also the group of Professor Richard Warburton at the University of Basel. So my title, this scalable quantum dot single photon sources. First is, what is scalability? Why care about single photon sources, and why use quantum dots for all these things? So, and that's the things that immediately click me when I look at my own title, for that matter. So let me try to introduce first what scalability and why I care about this in the context of quantum optics or quantum technologies, as it's being called now. So this concept of quantum advantage. Well, we hear about quantum computing and being able to outperform classical computers. Well, that's kind of like a very far away goal probably, but let's look at what is quantum advantage at the core of it. It basically can be summarized in this statement that it's the ability of a quantum machine to perform a specific task faster than a classical machine. Now, and this specific is kind of important because we are not talking about replacing a computer, right? We're not saying that we take our PCs that are sitting on our table, throw it away, and then replace it with a quantum computer. But you're saying that, is there a task where a quantum machine would outperform a classical machine? And the answer is yes. And few such problems that that have been theoretically explored, and very recently also some initial experiments are coming about, are, for instance, the case of far from equilibrium many body systems. So many body systems, we know that they are difficult to solve because of the parameter space that they need to span. For instance, examples could be what happens if you have a very complex physical or a chemical process that's happening, let's say you have a set of spins which are randomly moving. Okay, not just simple Ising models, but with like couplings going all the way to infinity. Then how would they thermalize if you perturb few of these spins? Now these are classically hard problems to solve, and that's where a quantum simulator could potentially overcome these limitations of a classical machine. Another case would be to, for instance, one of the largest quantum simulation that has been done to date is, well, it's a very simple case of a 4-atom system. So it's to calculate the Hartree-Fock energies of cis-trans isomerization problems. It's a start. We are going there, but what's stopping us to, for instance, this can be solved on a standard PC in almost no time, but a quantum computer needs this huge Google AI quantum collaboration project to solve this small problem on a quantum machine. So what's stopping us from here? The thing that stops us is the resources that this requires. So we need to have a nice quantum resource that that would stay coherent over several different quantum operations that one could do. So this is a complex thing to solve, and indeed this is one of the main directions to look at. But is there something easier or simpler that we can do living with photons? And the answer for this again is excitingly, it's true, and it's an overwhelming true, because photons and to realize this, it's actually for someone coming from disordered background, this was very exciting to look at. And this special task is called boson sampling. Now imagine this. Imagine you have basically a collection of beam splitters and prisms and mirrors and all, which are just set in a random aggregate fashion, which is equivalent to a piece of disordered material, right? Now you send in certain number of single photons into this, and let's say 4, and they would interfere in a very complex fashion unitarily, and this can be represented by a unitary transformation of this input state, and they would come out of the system and evolve to a unknown state, unless we know what this operation of this unitary matrix is. Now let's ask ourselves a simple question. Now I'll just try to make it into an abstract box here. So this white box that we have is our unitary operation representing this whole cluster of random beam splitters. And this 1 with the subscript 0 to n represents the n optical modes which have 1 photon in them, and the rest of the modes have no photons in them. Then we ask a very simple question. If I send, let's say, n photons in, and then ask the question where, let's say, and I pick some n random output modes out on my output, and ask to calculate what's the probability for these n photons to come out in these specific output modes. And it so happens this problem, let's start with the case of 2 photons. And this is this celebrated Hongo-Mandel interference problem. So if you take a simple beam splitter, so it's basically 50-50 beam splitter, and send in 2 single photons into the system, then there are 4 possible outcomes. And if I also include the phase relationships, what you will see is that the 2 paths where the photons either get reflected, both photons get reflected, or both photons get transmitted, cancel out. And this is true only if you have identical photons. So remember this term of identical photons, because that becomes crucial later on. And then if you were to have detectors, now if I put 2 detectors, one at the output of each output port, and ask, will I ever see a coincidence between the 2? So if I will ever see a state where one photon would exit this beam splitter here and another photon would exit the beam splitter here at the same time, the answer is basically it has zero probability. Now we are just looking at a larger version of this problem when we are talking about this large random matrix of optical transformations. Let's just look at it with two photons, but going into n optical modes. Earlier we just looked at it in the case of two optical modes for a beam splitter. Now, if you have to calculate all possible probabilities for this outputs, for instance, I send the two photons out or two photons into input modes 1 and 2, and then I want to calculate what's the probability that these two photons will come out through photons 2 and 3. Although I'm coloring them gray and like a darker gray and lighter gray, remember that both the photons are the same because I want to look at only the case of identical photons. So you have two different possibilities that these two photons would end up on output ports 2 and 3. Either the photon 1 goes to output mode 2 and photon 3 or like photon in output mode input mode 2 goes to output mode 3, or they swap. Then with two photons, we have 2 factorial possibilities of these outputs, and you can write out their probability amplitudes, and then we see that the probability that these two photons will end up on output modes 2 and 3 is given by this expression, which is called the permanent of this matrix. Permanent is basically the determinant without the negative sign. So all the negative signs replaced by plus. And similarly, you can also do this for 3 photon case, which I have shown here. So 3 photons will have 3 factorial possibilities for them to end up at the at a given set of output ports. And if you just go ahead and do the same exercise for n photons, you'd see that you'd have n factorial possibilities. And this kind of makes life a bit challenging because of this permanent calculation. All classical algorithms known for calculating the permanent of this matrix. So the best known case has a scaling which goes as 2 to the power of n. And this 2 to the power of n means that it scales exponentially with the number of photons that we put into the system. In contrast, what Aronson and Arkhipov showed in like early 2000s, or late 2010, whichever way you want to look at, I think. So what they showed was that if I were to sample, basically I sit with detectors on the outside and just do a sampling problem. So you send in photons and you sit with detectors on the outside and create a sampling distribution. Then you can actually construct the probability distribution of the photons arriving at the outputs faster than a classical machine would calculate all these permanents at some very large number of photons. At least the scaling, the interesting part is that the scaling goes as n to the power of a, and you can remove out this exponential part. So it's at least non-exponential, which is pretty exciting. And the nice thing is all that this demonstrating such a thing, the requirements for boson sampling are that, well, you need n identical photons. You need a low loss optical network so that you're not just losing all the photons. Then there's a problem of just detecting the state, because you are losing n photons. You would have an exponentially small probability of detecting n photons in the output. But the good thing is low loss optical networks are something that are readily available even for and even through like industrial foundries. And the third thing, equivalent to the loss on a network, we also would want to have very high detection efficiency. So we want to detect almost every single event that can happen. Again, the good part is the rapid advancements in single photon detection and the necessity for that, especially through so-called nanowires, superconducting nanowire detectors, have achieved like efficiencies close to or even above 95%. So we kind of are sorted on these two fronts. These n identical photons, and to understand why did I put this in red and why is it challenging, we need to understand what this n is. How large is this number n? Now, if we were to demonstrate quantum advantage, so what I'm plotting here in this graph, on the x-axis is the number of photons, and on the y-axis is the number of steps to calculate a permanent. As you keep increasing the number of photons, the number of steps that you need scales exponentially. That's why I'm plotting this on a semi-log scale. And to just put this in perspective, so the number of computational steps, so this is basically about a teraflop over 30 days. So I'm basically setting a 30-day limit on my experimental time window, because that's about the longest quantum photonic experiment that we can possibly do at the moment with photons before everything starts to drift around. This is also a pretty high number. So if I have about 1 teraflops of operational speed for a supercomputer, which was the case in 2000, then you'd have to have more than 40 photons, roughly around 40 photons, so that it's interactable for classical computer, for the best supercomputer at this point. At the current point in 2020, we are looking at about 100 teraflop or 100 petaflops of computational power, which is the IBM Summit. Well, going at the scaling, at the current scaling of supercomputers, at 2050, it would probably be around 20 or 10 zettaflops. But as you can see, the marginal gain in the number of photons from 2000 to, let's say, even 2050 is only from not even a factor of 2. So for the time being, let's look at our 2020 scenario. If we can cross a number of photons of about 54, then we can definitely say that we do better than, or at least we might be able to beat the best supercomputer available to us. And that is why when I say this n over 54 nearly identical photons, and nearly is a catch I'll come to. Nearly identical photons is what we need, and this has been a very big challenge till recently. Pretty much it's been last year where we've managed to solve it, and then also there have been subsequent works which came out claiming that now we have sort of trying to bridge this problem. So our approach to generate this 54 or more single photons, identical single photons, is using quantum dots. So semiconductor quantum dots are essentially tiny islands of one semiconductor material embedded in another semiconductor material. So our dot itself is formed using indium arsenide islands. So this has a lateral dimension of about 50 or 20 nanometers, and height of about few nanometers. So what would you get by sandwiching two materials within each other? So let's just look in the height direction. So you'd be embedding indium arsenide, which has a smaller band gap in comparison to gallium arsenide. And by making it small enough in all 3 dimensions, you get 3-dimensional quantum confinement for the electrons. And by exciting one of the electron from the valence band to the conduction band, you can create something called an exciton. Basically, an exciton is an electron-hole bound pair on a quantum dot. And when this electron and hole pair recombine, so it's basically the electron goes back to or recombines with the hole in the valence band, then it emits a single photon. So for all practical purposes, for now, imagine this just as a 2-level system. So there is a ground state where the quantum dot is empty, and there's an excited state where you have created this exciton. And the good thing about these kind of single emitters, which are sitting in a host material, so it's sitting in a gallium arsenide like material, is that we can create nanostructures around it. And why do we care about nanostructures? It's because if this dot was to sit in just bulk material, it would emit in all directions, and we won't be able to efficiently collect all the light into a single optical mode. By creating nanophotonic structures around the quantum dot, we can engineer the local density of optical states so that you'd end up basically so that the quantum dot is forced to emit only into this single propagating mode. Now, one of the geometries is to make a rectangular profile waveguide, or we can go a little further and say we'll make a more complex waveguide. And why do we make a more complex waveguide? It's so that we can completely suppress the emission into any other direction apart from the one single mode that we want. And to do this, what we do is, so you have this indium arsenide dot, which is sitting in a thin membrane. So it's 170 nanometer thin gallium arsenide membrane. So this tiny dot sitting in this huge membrane, basically, and then we create holes, pattern of holes in this membrane to create a 2D photonic crystal, and select the lattice constant of this photonic crystal so that this is in the band gap of the photonic crystal. So the emission wavelength is in the band gap of the photonic crystal, and then you remove a row of holes in your design so that you create a single mode waveguide. And now, because the quantum dot is sitting within the band gap, and then you allow just this one mode, the quantum dot is selectively, if otherwise would be inhibited from emitting, but because of this single defect mode, it emits only into this single optical mode. So in essence, you can see this from the schematic. Now, if the quantum dot were to emit, it would, with a very good probability, emit into the single optical mode. And so that's what we would term as gamma WG, which is the radiative decay rate into the waveguide. Gamma NG is the radiative rate into non-guided mode. So it's basically scattering out of plane of this photonic crystal waveguide. And there could be some non-radiative processes for the exciton to relax out. The key figure of merit for this coupling efficiency, that's basically if you excite exciton on the quantum dot, that it would emit a photon, and this emitted photon is always in this waveguide mode, is given by this beta factor, which is the ratio of the waveguide rate divided by the total rate. That is the rate that it would emit into the waveguide mode, into the non-guided modes, or lost because of non-radiative decay. And this beta factor, if it's 1, it means that all the light is only in this waveguide mode. The really neat part about this is that beta factors in excess of 98% have been, I mean, even recently another group has reported over 99% beta factor for quantum dot sitting in a photonic crystal waveguide. So this is very exciting. So basically every single photon that this quantum dot would ever emit is always in this waveguide mode. So that's one problem sorted. So if you have to look at how do we realize a photon source, a single photon source, this to generate this stream of or this 50 photon resource that we need for doing the boson sampling. So now at least we have a source of single photons, and these single photons are all going into a single optical mode, so you can very efficiently collect it out into a fiber or something. But then, what are the properties of the single photon? So how good are they? So these are characterized by these basically these two parameters that I show here. So how coherent is their emission, and can this dot emit more than one photon at a time? So this is what we'll talk about now. So a quantum dot basically apart from, so as I said, the efficiency. So while What the beta factor quantifies is that if the quantum dot emits a photon, then it will be in this optical mode. But what if the quantum dot doesn't emit a photon at all? So as I said, there's also this non-radiative decay processes, or the fact that it could emit at a different wavelength because of some other process that's happening, right? Like Auger or some, yeah, many processes that can affect in a semiconductor. And to ensure that nothing disturbs this exciton that's formed in the quantum dot, we cannot only rely on the nanophotonic part of it. We need to also engineer its electronic properties, because what can happen is, so you created this electron in the conduction band by creating, or this exciton hole pair in the quantum dot, and there could be a stray electron sitting in gallium arsenide, which could hop into the indium arsenide quantum dot and either shift the energy levels because of Coulomb repulsion, or it could scatter this photon or scatter this electron off and break the electron hole electron hole pair. All of these are non-radiative processes, and the way to overcome this is actually something that I schematized here, is to embed this quantum dot within a PIN type diode heterostructure. So now imagine what I'm doing is I'm doping this gallium arsenide on either side. On one side, it would be N-type, so which means I'm increasing the density of electrons, and in P-type, so I'm decreasing the density of electrons in comparison to the intrinsic, like natural gallium arsenide. And by doing this, I'm changing the shape of this conduction band. Instead of it being like this simple structure, it goes into this kind of a step structure, or like a steep hill. And what this means is that there is an inbuilt electric field because of this band bending in a semiconductor heterostructure. So this inbuilt, or you could also think about it like a very thin capacitor, because there's a difference in the electron density on either side of this quantum dot. And how thin is this heterostructure I'm talking about? This whole thing is embedded within the membrane. So this width of this PIN diode is 170 nanometers. And so, and the capacitance for this is typically of the order of a picofarad. And so the voltage buildup within this thin diode heterostructure is of the order of hundreds of kilovolt per centimeter. So what this does is it naturally creates like a blockade, a charge blockade. So if an electron wants to jump in from the N-type contact into the quantum dot, or the other way around, or for the electron to jump out, there's this huge opposing field which is acting like a barrier. So this charge screening should help from these kind of unwanted processes and improve the coherence of the state. So because you're not scattering of electrons. And on top of that, this gives us a very interesting handle. So I can, because it's a PIN diode, I can change the bias voltage by externally connecting to contacts and using a DC power supply to change the bias voltage. And if I then tune the bias voltage and excite this quantum dot with a above band gap laser, then you would see that the quantum dot emits at different frequencies at different bias voltages. And you can understand this by looking at this curve. So basically at some bias voltage, so what you're doing is you're changing the shape of this well. You're using this as a lever and moving it up and down. So which means at when the bias voltage is low, so you have a very steep hill, and so this particular state of the quantum of the quantum dot is not resonant with the Fermi level. So you are screening every single electron from ever entering the quantum dot, and then you apply a more bias voltage, so it starts to lower down. Then you can selectively populate it with one electron. So one electron is always allowed in the quantum dot. So you can select, and then if you optically create an electron hole pair, then you have two electrons and a hole. So you create an X minus, so-called a negatively charged exciton. So you can create all kinds of different excitonic complexes like this. And on top of that, if you see what I'm plotting in this curve, on the x-axis is the frequency or the wavelength, and y-axis is the bias voltage that I'm applying. And if you just trace this one line, you see there's a tilt, which means that as I tune the bias voltage, I can tune the wavelength of emission of this quantum dot by a small amount, by about 0.2 nanometers. And in some heterostructures, we can even tune by about a nanometer. And this can allow us to tune, if you have multiple quantum dots, you could in principle tune them into resonance by using this electrical control. And on top of that, we are also using this negatively charged exciton. There's also this interesting thing that can be done called spin photon entanglement, which I will not talk about today. So as I said, just to recap here, so what we have is a quantum dot sitting in a photonic crystal nanostructure, and with the membrane of this photonic crystal nanostructure itself having a nanoscale features because of this electronic control, so PIN type of diode, and where I apply this voltage bias across this thin membrane. And then go ahead and the standard nanofabrication, it's not standard, it's a pretty complex nanofabrication process with multiple steps involved. So what you can see here is this one single device of a photonic crystal waveguide. So you can see the waveguide as well. And there's this trench made around the device with this metal electrode, yeah. So with the metal electrode that can change the bias voltage. And there are an array of such devices on this chip. So the important part is to have very precise nanofabrication together with low noise and locally defined electrical contacts to reduce all kinds of unwanted electrical noise on the circuit. And to check how good the dots are, what we do is to use a very interesting property for quantum dots, or like single emitters, very coupled with this high beta factor to a single mode waveguide. So you can see single photon nonlinearities. And what do I mean by this? So let's say you have a quantum dot, which is sitting in a single mode waveguide, and you send in, let's say, a attenuated laser, which has just one photon. Mean photon number is much less than one, but let's consider the case where the incident wave packet has exactly one photon. Then this, if you can, then this particular photon, when it interacts with the quantum dot, which is sitting in a single optical mode, then the transmission amplitude of the photon and the re-emitted light completely cancels out when the frequency of the laser is on resonance with the quantum dot, and you would get zero transmission exactly on resonance. And when you're off resonance, then this interference doesn't happen, and you would get basically the laser transmitting through because it's not interacting with the quantum dot strongly. And this is not the case if you send in two photons. So you cannot observe this if you just send in a bunch of like very powerful laser light through, because if you have two photons, then you have all possible combinations and you would end up with non-zero. It's more than zero transmission. And as you increase the mean photon number, you'd get more and more like mean photon number of coherent state of light, you'd get less pronounced dip in transmission. So the important thing is that the single quantum dot in a photonic crystal waveguide, a single mode photonic crystal waveguide, can act as a nonlinear medium. Now we use this particular feature that this transmission dip can occur to measure the line width. What's the line width of the quantum dot? So you take a very, very narrow line laser and then tune it across the frequency of the quantum dot. Then by fitting this line shape, sorry, I cannot hear you.
Dr. Uppu, you have 5 more minutes.
Yeah, sure. Yeah, so, and by fitting the line width, you can get, we measure what's the line width of this quantum dot, measured line width of the quantum dot, which is 540 megahertz here. And you can get the natural line width of the emitter by measuring its lifetime trace, which is 1 over gamma. And then the transform limited line width is this gamma over 2 pi, which is measured to be 460 megahertz here. And the really nice thing that you see here is that the measured line width is only 1.17 times. So it's only 17% broadened in comparison to transform limit, which before doing all this electrical contacting was several factors. It's almost like 4-5 times larger than the transform limit, or even bigger. And we could do this over a whole array of dots, not just a single dot. And what I show here, for instance, just focus on these 3 measurements. So with the corresponding orange circle. So the orange circle is the natural line width, so the transform limited line width, and the orange square, and the blue square is the measured line width. And as you can see, all of them stay very close to each other. And we did this whole series of measurements over like 80 quantum dots. And you could see at least 65% of them had really low noise behavior. And we believe that this could be improved even further. So that covers this part about transform limited emission. And going ahead is to generate the single photons themselves. And to do this generation of single photons, what we have to do is like we send in pulsed laser. So these are few picoseconds or like 5 picosecond laser pulses coming in at 140 megahertz rep rate. That's what's defined by this disk. And they excite the quantum dot from the top of the membrane. And the quantum dot emits the single photons into the waveguide. And we have this outcoupler. So this is this apodized outcoupler, something similar Amit was showing yesterday in his talk. And then we have a fiber that collects the light out here. The single photons out there. And because there's a spatial separation between the excitation laser and the collection spot, the laser is completely separated. And keep in mind that the excitation frequency of the laser and the output single photons are of the same wavelength. So it's actually very important that they are spatially separated to get good laser suppression. And so what we have here is what I'm showing here is the pulse area or the power of the laser for a given pulse width, and on the y-axis is the intensity or the number of photons per second that are detected using a nanowire detector. So you can see that we have almost over 10 million photons at pi pulse. So that's when you reach perfect saturation of the emitter. And on top of that, it also follows the Rabi model very well, showing that there is very little dephasing in this quantum dot. And then you can go ahead and at pi pulse, what we do is to do a Hanbury-Brown twist measurement, which is basically you take the emission from the quantum dot, put it on a beam splitter, and on the 2 output ports of the beam splitter, we have 2 detectors and measure the coincidences between these 2 detectors. And if you have a pure single photon, it would either click on detector 1 or detector 2 at 0 time delay. And as you can see from this plot, so you have these side peaks which correspond to 1 laser pulse separated or 2 laser pulse separated or 3 laser pulse separated. But exactly when it's 0 excitation laser pulse separated, you have a very strong suppression of this peak. And from this area under the curve, you can calculate what's the G2 of 0, and we measure it to be less than 1.5% at perfect excitation. So, and we are generating over 10 million photons into the fiber. And this can be further reduced. Now we can go ahead and then see how identical this train of single photons that this quantum dot is emitting. And to do this, what we set up is a Hongo-Mandel experiment using an asymmetric Mach-Zehnder. So the 2 photons arrive at this beam splitter, and they can either take the short path or take the long path. And this long path is something where we can adjust this fiber delay to be either one laser pulse separated or 2 laser pulse separated, all the way up to 115 laser pulses separated. And if both the photons have the same polarization, they will interfere at this 50-50 beam splitter, and we would see this Hongo-Mandel effect where there should be a suppression of the events where we get coincidences on these 2 detectors. So that's what we see here when it is separated by 2 laser pulses. in the light blue curve, and at 786 nanoseconds, which is 115 photons separated. And for control, when we change the polarization of the long arm, that is, these two photons are orthogonally polarized, then they won't interfere here, and you would get very large number of coincidences, or at least half the number of coincidences as what's being sent in. And what you can see is from this interference visibility, we can calculate the photon indistinguishability. And what we measure is that over this whole string of 100 photons, 115 photons, we have an indistinguishability of over 95, 96%, which means essentially we have 115 identical single photons that are generated from the source. So you have basically solved the key problems. And on top of that, what I did not highlight too much is this grating, apodized grating that I showed you, which can have an efficiency in excess of 80%, which also solves the problem about how efficient can we make them. And we have newer designs which can go above 90% even. So in all, we have a source of single photons, which has an intrinsic efficiency. This is beta factor times the quantum dot efficiency, which is over 84%, and a collection efficiency in excess of 80% at least, and maybe even over 95%. G2, which is quantifying the multi-photon emission probability of less than 2%, and indistinguishability in excess of 96%. So we have a total single photon efficiency of about 80%, but is this good enough for the boson sampling thing? And in fact, in this paper, we actually also quantify whether the source efficiency is good enough for quantum advantage thresholds. So what we show is that if the source efficiency is above 78%, which is smaller than our 80 odd percent that I showed you earlier, then at n equal to 54 photons, we should be able to do experiments. Now, all it takes now is few million euros to buy the necessary equipment to do the experiment. Not few million, it's like maybe over a 10 million euro to do the actual experiment. With that, I think I will talk I will actually stop my talk with just interlude saying that apart from going from this very complex top-down illumination, we could also do a more convenient inline or in-plane illumination or excitation of the quantum dot, where you could just plug in laser into one end of the device and get single photons out, suppressing all the laser out. So yeah, anyone interested could go ahead and look at this other article from us.
Thank you, Dr. Rupu, for this wonderful talk. And now you can take a few questions. So one question is from Professor Gopal. Professor Gopal, you can go on.
Hi, Ravitej. Excellent work and a very good talk. And so I have a couple of comments and questions. So,
yeah.
So with MBE grown, so you need to operate these at low temperatures or these room temperature?
No. These are all at 1.6 to 4 Kelvin.
Yes. So these are Indium arsenic quantum dots. Okay.
Yeah.
So and you have large inbuilt potential, which also means your applied bias is going to be larger.
Not so much.
Because you
so
need
actually, we do a
compensate.
bit more. Yeah, we do a bit more with the heterostructure engineering. So in this particular chip that you saw, we apply a voltage of about 1 volt, but we have devices where we can operate near 0 volt bias. So,
okay, but how do you compensate for the Fermi level?
So what we do is to have intermediate endo layer. So is this PIN or PIN kind of diode heterostructures where you can populate X zeros. And then play around actually defining the thinness of the layer and add a tunnel barrier in between.
Okay.
So yeah, it is.
But those are for future, I guess, not yet. Or do you have those structures or?
Yeah. So we have a 53 nanometer tunnel barrier even in this one.
Okay. Yeah. So what is the coherence time of quantum dots in this? You said the coherence time improves. So
yes.
Do you see any improvement in the coherence time compared to the?
So coherence time in the sense that spectral diffusion side of things, or are you talking about T2 time?
I thought when you said so you talked about improving the coherence time of quantum dots, in these structures. So I
Coherence
thought it's the T2
of
time.
emission. Yes. So what I meant by coherence time of emission. So there are indeed two different things there. So one is this T2 time. So that T2 time is going to be, that's a bit more involved process, but there is some improvement even there actually, because you do screen out. And so it depends on, so there are some effects on the nuclear spin properties, but what I mean by coherence time is basically long time scale coherence of basically this indistinguishability that I was talking about, that all the photons that are generated from the dot are identical. So the spectral diffusion of the quantum dot is minimized. So the charge noise is very small.
Okay.
So the nuclear spin noise is a bit more complicated thing.
Yeah.
But then also we have some exciting things. So we do have like T2 star time for a whole spin of.
But I guess it will be typically still in the nanosecond range.
Yeah, 20 nanoseconds for indium arsenide, because it's indium with this 9R spin, which is a pain.
You have indium segregation and all these effects.
Yeah, exactly. So I mean,
but
droplet dots probably.
Yeah. So this pulse train, which you said, so is it the pulse train is coming because of your applied bias you're pinging in, or?
No. So we don't electrically control them, because electrical control or like electroluminescence is a bit more challenging problem, because you're creating carriers, right? So you would have all kinds of Auger processes which reduce the coherence of the photons. So these are resonant optically excited. So optical excitation is like the cleanest thing to get photons out.
Okay. And what's the frequency for these?
This one we are exciting at 145 megahertz.
No, I mean not the energy, the frequency of the separation between these pulse trains. I guess it's driven by the optical pulse frequency.
Yeah, 6 nanoseconds.
6 nanoseconds. Okay.
Yeah, but we can take it down to under a nanosecond, because the lifetime is about 300 picoseconds.
Okay.
Just about.
Thanks. Yeah, thank you.
We can take one more question.
There's in the chat actually.
We have a question from in the chat box.
Can you explain the requirement of forming a PIN junction if the excitation is done by the laser pulse itself? So the PIN junction, as I explained, has this large inbuilt potential, which kind of screens the exciton from interacting with like an additional electron. So it improves, basically, if you have all these processes, what it does is it adds kind of line broadening mechanism. So we start with this 460 megahertz line width, and then it starts getting broader as your electron comes and collides with it. So all these processes basically couple to different, you could think of it as different states in a quantum dot. And so all these would have like in-out rate. So the total rate would just keep getting broader and broader, which is bad. Okay, I also see Ashwin asking a question. Ravi, if you apply a large enough bias magnetic field to the quantum dot, is the spin dephasing time affected due to coupling to nuclear spin? Yes, but how large a magnetic field, like typically, like I showed you this spin physics interest. So when you want to work with charged ions or charged excitons, so we typically apply about 2 Tesla in plane fields and probably larger. It at that point it doesn't affect, but that's a bit more undetermined territory there. So there are instances when there is some kind of nuclear polarization locking and it becomes super nice, and sometimes it goes a bit hayward there.
I think if anybody else has any questions.
Sandeep, can I go? I have two short questions. Is it okay?
Okay, one more question, and then we can forward if you have any questions, so we can mail us the question. We can forward it to the speaker, and we can get back to you. Yeah, Sushil, please.
Okay. So Sandeep, you said one question. I have two short questions. So,
Okay.
this is about the placement of your quantum dot exactly at the mode maximum of your single mode waveguide.
Yeah.
How reliable is that process?
So I actually in this process don't try to place the quantum dot anywhere. So you actually go around because it's a broadband device, right? A photonic crystal waveguide. So you just go with high enough dot density and just find a dot that works that's coupled strongly to the waveguide.
But then the in-coupler and the outcoupler, is it post-fabricated? I mean,
no, it's broadband. So it has a center, like we design it for 935 nanometers, 930 nanometers, but it has this very high efficiency for about plus minus 5 nanometers. So, and that's very large band for, so I did not show this plot in a 6 nanometer band typically. So this 80 dot statistics that we took is just in a 5-6 nanometer band. So you can control it very well actually.
I see. And the next question was the discussion on the scattering being resonant, right? Because it's the quantum dot, you excite it at the same wavelength at which you detect it. Is multi-photon absorption a solution there? Can I use a 2-photon laser absorption so that it becomes degenerate?
Yes, you can do multi-photon absorption for the exciton. So there's this work that was done where they were driving it with a bichromatic pulse. So it's basically with sidebands,
True.
right? And it's just that you need to handle more power because you are not driving it on resonance, and then you need to also suppress it so well. It can be done. So there's this work from earlier last year and also even before that, 2019, 2020, showing this bichromatic drives. But it's typically like you need to reach about 7 pi excitation for a resonant excitation for the bichromatic pulses. And it's better, the further away you are, the better the suppression is, but you also need to put so much more power.
Okay. Thank you. Very nice stuff. Thank you.
Thank you, Dr. Uppo, for joining us. Thank you again.
Thank you.
Now we'll have a tea break for 10 minutes, and then we can rejoin at 11:20. So we have 3 more talks in this session. Then we'll go for lunch break. Okay, thank you.
Thank you.
So what time do you have, Ravi?
It's about 11:30.
Okay. Is that your time to call it a day or still work?
No, I need to prepare some questions for my lecture tomorrow morning. So,
Oh,
yeah,
Teaching.
Yeah, I have a lecture at like 8:30. Yeah, I'm teaching now.
Good.
I'm teaching basic physics course. So,
Okay.
nice.
I have the questions. I need to put them into like Zoom polls. So, so that it's interactive. Yeah, because it's online classes, right? So I put it on Zoom polls so that I could do it during the lecture.
Do you also have to record?
Yeah, I mean, because I have like about 80 odd students for the lecture, so not all of them can attend. So, so I do record and keep as well, so that they can watch it later or while doing their assignments and all. It's just helpful to have a recording. Yeah, it's a bit of work, so I'm getting used to it. It's just been a week, right, since I started teaching on the 25th. So just about 2 weeks. So. Yeah. The first week was a little challenging, but now it's good.
And how's the COVID situation in your city?
It's all right. I think it's like few cases per week on the university, because it's largely the university around here. So and because it's a university, it's also much better. Like they are very strict in enforcing that everyone should wear a mask. And for instance, my lab building and also my office building where my office is all, because it's almost exclusively only research, you don't find many people. It's only the people who come in to do their experiments, like PhD students or faculty. Mostly, like I don't see any social activity happening, which is also helpful. Yeah, but I don't know how long it's going to be like this. So
Cool. Thanks a lot, man. Thank you very much.
thank you for the invitation. And it was, yeah, it's really nice to be part of it, and it's also really fun to see that we finally also have an OSA student chapter. Yeah, because we were, I think Anjali and I were also thinking at one point.
Yeah, this thing has gone through several iterations,
Yeah.
and it's a memorable process starting the chapters. I think the students here will have lots of nice stories to tell you at some point.
Yeah.
Chill, man. I'll move. Bye. All the best, Ravi.
You're not here, Gopal?
Thank
Or
you.
No, 11:30. That other talk will start. Ready.
Oh yeah. Okay, yeah. Thanks.
Bye.
But you are there after that, right?
Yes, I'll be there. Yes. Afternoon.
Thanks.
Bye.
Yes. Yeah, the missing talk. I think I'd have to also get going. But I see that it's all available on YouTube. So I have to follow up and probably write some mails to speakers because I was watching SJ's talks. I was watching Amit's talk and also I forgot RT, was it? The first two speakers I was watching, yeah. It's nice collection of talks.
Yeah.
I couldn't still finish the rest. I'll watch them.
Yeah, of course. Yeah. Sure.
Yeah, I hope I can join in the early morning talks. When for me, early mornings or late evenings talks. By then, if I'm up.
Oh, you
Yeah,
mean what happens late evening here, right?
Yeah, exactly. So probably I might be able to join if I'm up.
So what time is it in India when you are normally up and working, or at least up and awake?
I am normally up around 5:30 because I'm going to the office by like 7 or so.
Oh, wow.
7:30. So yeah, because my lecture starts at 8:30 and I have it on 3 days anyway, on Monday, Wednesday, and Friday.
So what time is it in India at that time?
It's like 6 here is 5:30 in India in the evening. So it's half an hour offset. That's all.
Oh, you may catch a couple of talks, partly at least.
Yeah. I think I might be able to catch 1 or 2 talks.
Yeah.
Otherwise, I'll just watch it on YouTube.
Of course.
Okay, I'll see you, Sushil, and yeah, I'll catch you later. Thanks, everyone.
Thanks, Ravi. Good night to you there. Bye.
Bye.
Hello, Pawan.
Hi, Sushil.
How are you?
Yeah, good, good. 1 second. I'm just switching on my earphones. 1 second.
Okay, sure. No worries.
Hello. Am I audible?
Rabi.
Yeah. Welcome everyone. Myself Ravi Shankar. I'll be chairing the rest of the session. So our next speaker is Professor G.V. Pavan Kumar. Professor Pavan Kumar is an associate professor of physics at Isaac Pune. He obtained his PhD from JNCSR, Bangalore, and subsequently held postdoctoral position at ICFO Barcelona and Purdue University. In 2010, he joined the faculty of Isaac Pune. Pavan's research interests are at the interface of nanophotonics and soft matter physics. In recent times, he has been working on topics related to thermoplasmonic trapping, light scattering from optical to its plasmonic and soft matter systems. He also blogs on science and related matters. He has received many awards and fellowships, which include Swarna Jayanti Fellowship in Physical Science, Malhotra Field Foundation Award in Nanoscience, Narcis Kopas Young Scientist Award, and INSA Medal for Young Scientists. He is also a senior member of OSU. The talk of his title today is Colloidal Dynamics in Thermoplasmic Terms. I welcome Professor G. Pavan Kumar to present his talk.
Thank you very much for your kind invitation. So can I share my screen?
Yeah, sure. Proceed.
Yeah. Okay. Is it now visible? All fine?
Yeah, it's visible now.
Yeah, okay. So should we start? Because my what says it's still 3-4 minutes are there, or should we start right away?
Yeah, just 1 minute left. I think
Yeah.
25 it will start.
So Sushil, how are you?
Yeah, very good, Pawan. Thank you very much.
Yeah, good.
Actually, you are absolutely right about being 2-3 minutes ahead of time, which is why I decided to say a casual hello.
Yeah. Even I thought that's the reason I was also online a little early. I was just thinking that we may.
But the chair is the boss, so I said.
Yeah. No. That's the reason I request Ravi to.
No, you can go ahead, sir. No problem. We'll start at around 1-2 minutes later. No problem.
Yeah. So everything fine there?
So all the students are back at work here, so that's a good thing.
Good.
How about your place?
Yes. Yeah. The research students are all back. Undergrad students are all away.
But that's going to be online anyway, right?
Yeah. Meaning first 4 years of undergrads is all online now. The fifth year who have a research project are all here. All people who do research are on campus, so that's not a problem.
And the government's recent recommendation of 15th Feb, are you guys working on that?
What is it? 15th Feb?
They recommend to try and see if degree colleges can have 50% attendance voluntary.
Attendance, yeah.
Voluntary.
See, the only issue is that since it's a residential campus, we already have a few students, for example, who have some issue with internet connectivity, and maybe somebody who doesn't have good access to facilities. They have all been asked, been asked to come back as early as December. So they are already on campus. So we have few undergrad students who find it very difficult to study at their place. they have all been asked to come back. So in that way, accommodation is already done. Over and above, maybe slowly the numbers will increase. But already the next semester is announced as online. It's already going on.
Nice, very nice.
Yeah.
Okay.
So,
Okay. Then.
Yeah.
This
So,
yeah,
okay.
go ahead. Okay.
Yeah. So,
Later.
Yeah.
Can I
So
start
first,
now?
yeah.
Sure.
Okay. Thank you very much. The TFR OSA student chapter. It's actually a pleasure for me to give this particular talk. I also thank generally the TFR research community, because with whom I have good interaction, like Sushil and Gopal and Prabhu and various different people, JD and Sudipta and everybody. There's a lot which I have learned, and there's also a lot of interaction which we have with this community. So, in general, thank you for this opportunity to share some of the stuff what we have been doing. Since last morning, yesterday morning, we have heard some talks where speakers have alluded to some very interesting prospects of using optical forces, be it trapping of atoms, as Amit mentioned, or with nonlinear traps, as Professor Deb mentioned. These are all very interesting opportunities to utilize forces which are generated by electromagnetic effects. In addition to the electric field and the magnetic fields, what a light beam facilitates, there is also a conversion of this electric and magnetic field energies into a form of heat. And that heat, many a times, is a nuisance. And some particular times, it can be an excellent kind of opportunity to utilize heat at micro and nano scales. And one such application is thermoplasmonics. So I'm going to go further and I'll tell a little bit more about how heat generated by light can be harnessed and utilized for some specific applications. I'm actually, I've planned this talk in such a way that I can give you an overview to largely the student community, but I'm also going to include some of our work as we go along, because it's roughly around 25-minute talk. So I've just kept a kind of a balance between these two things. So first, I'm going to give an introductory aspect of this whole concept, and then I'm going to show some of the work which can be done. So broadly speaking, as Ravi introduced, nanophotonics and soft matter, the interface between these two things are something I'm quite deeply interested in. Terms of nanophotonics per se, surface plasma on polaritons is a kind of a surface electromagnetic wave. There can also be various different surface electromagnetic waves, as you probably would have come across, among which plasmons have gained a lot of prominence because you actually can perform a lot of interesting photonic operations beyond the diffraction limit of light. And it actually created a lot of buzz, especially around early 2000s and early 2010s. There were also several questions related to its utility in terms of devices, because heat was one of the issues when it came to many important applications. So one aspect of the heat related to surface plasmons is of relevance to this particular discussion. In terms of soft matter, I assume many of you would have come across, in fact, right from biological systems to artificial soft matter systems, including colloids, liquid crystals, polymers, biological surfaces. All these things have gained a lot of prominence, and it has a very interesting connection to condensed matter physics, where you look at emergence, you look at various different concepts such as phase transition and also critical phenomena. All these things actually are very interestingly related in both the soft and hard condensed matter system. So the questions which are of general interest to my own research is what is the nature of colloidal dynamics? In this particular case, the soft matter I'm talking about is mainly colloids. And we ask how do colloids behave in the presence of surface plasma on polar atoms. Another question which has recently kind of gained a lot of interest from soft matter viewpoint, and also where optics can potentially be applied, is to understand entropy driven ordering. Generally, we think entropy is a form or rather a concept which is associated with disorder. But in certain conditions, you actually can harness entropy to order objects. So that is something very fascinating principle, which dates back to Onsager principle and various different concepts. So that is one very interesting question. The other aspect, which is slightly more kind of oriented towards engineering structures, is to ask what is the effect of dimensionality on the dynamics of, let's say, nanoparticles or nanosystems and various different kind of soft matter entities. The motivation for asking such questions is there are many, but those which actually are of very high interest to my own research is something I've just noted down here. One is the light-driven active matter, because light actually has very unique features in terms of polarization, in terms of intensity, amplitude, phase, and beam profiles, and various different parameters of light can be actually coupled to matter in very interesting ways. And that can further impart momentum, both in terms of forces and torques, which can be harnessed for various different interesting applications. And another important aspect is that the electrodynamic forces kind of emerge out in the form of optically bound matter. And the kind of systems what you actually can bring together by optical forces have also very interesting implications. Single molecule studies and swarmings and networks, and these are all questions which are slightly oriented towards statistical physics, but optics can actually be an excellent tool to harness and utilize in such applications. This is a slide probably a lot of you would be aware of. This is one kind of selling point of plasmonics for the last several years, where a case is always made for why you need to study plasmonics. If you look at the past decade, most of the operating speeds and critical device dimensions happen to be large and slow, generally speaking. But of course, there is a huge and very mature technology in terms of semiconductor electronics, which has pushed the limits of transistors down to a few nanometers. And dielectric photonics, thanks to a revolution in optical fibers, actually has kind of, literally accelerated the transportation of information. And there's no other or no better example than internet, for example. That is one of the greatest things which has come out of this. But there is some niche for where you actually can really scale up the operating speed, and also potentially make devices which are smaller and smaller in scale. I should mention that this is something which has turned out to be not to the mark, meaning the metallic nanoplasmonics were tipped to be something which is supposed to have really fast applications, and potentially replacing devices in silicon nanotechnology, and also to see whether the critical dimensions can go all the way to subwavelength and even to atomic scales. There are some applications which have shown, but one of the issues is that if you heat metals, if you illuminate metals, there is a local heating, and that heating creates a lot of problems if you want to use it as a photonic device. Okay. But what happens is in the last 10 to 15 years, one actually came to a consensus that it's not only the radiative decay principles which play a critical role, but also a non-radiative component associated with illuminated metals in the form of thermoplasmonics, which has arisen as a very interesting prospect, where you can utilize the local heating of the metallic nanostructures and put to use for various different applications. So, which means that this has evolved itself into a very interesting area of research. If somebody is interested, I would urge you to just have a look at the applications and challenges of thermoplasmonics, which has appeared very recently, a few months ago. And there's also a very nice book by Buffo about 2 to 3 years ago on thermoplasmonics itself. the basics are laid out very, very well, and you would actually get a feel for the subject in reasonable detail. Now, before we go into the heat related to the surface plasmons, very brief introduction for the case of completeness. Surface plasmon polaritons are coupled oscillations of light and electronic charge density waves at the metal dielectric interface. So, for example, this metal can be, let's say, coinage metals like silver, gold, and the dielectric medium can be something like a fluid like water. And if you illuminate that particular interface with a very proper phase matching condition, you would end up getting the electric field distribution, which exponentially decays from on the either side of the interface. And you can actually recollect the one which actually penetrates into the metal is called as the skin depth, and that has its own implication for various different applications. Now, the optical properties of metal per se actually is very tightly connected to its dielectric properties, meaning the dielectric constant which we come across in conventional condensed matter physics or in very particularly in solid state physics. You all probably would be aware that the so-called dielectric constant is actually not a constant. It actually varies as a function of wavelength. And it also has a real and imaginary parts to its functional. And it also depends on the charge density of the metal which you are considering. And this particular charge density has a close relationship to the plasma frequency associated with the metal and the frequency at which this particular operation is conducted. Now, you can break this particular equation into real part and the imaginary part. And as we all know, the real part of the, for example, refractive index or the dielectric constant is associated with the transmission of the light. And the imaginary part is mainly associated with the absorption of the light. So in order to actually harness the heat when you illuminate some metallic nanostructures, it is the imaginary part of the dielectric constant which actually has to be engineered or harnessed for various different applications. Now, you actually have now a variety of metals, for example, silver, aluminum, gold, copper, lithium, palladium, platinum. There's a plethora of different metals which actually can be utilized. And this has its own utility in terms of the frequency at which you are functioning. For example, you can extract something called as quality factor, where radiative processes are actually very efficient. So you can see that gold and silver happen to be two of the best metals. Aluminium happens to be the best in, let's say, in roughly in the UV wavelength regime. Although silver happens to be the best plasmonic metal in visible frequency, especially for radiative processes. But the handling of silver films, for example, has been challenging because of oxidation, and also if you are utilizing it for biocompatibility applications, there are questions related to the silver getting kind of oxidized and creating some other problems. So therefore, gold has turned out to be an important metal for various different applications. Now, the crux of the whole discussion is to ask how do plasmonic structures generate heat. So associated with the imaginary part, which I just introduced to you, of the dielectric constant, one can associate the heat power density. So if you actually consider an electromagnetic wave and you associate an electric field with that electromagnetic wave, then the intensity times the imaginary part of that particular metal or under illumination times the frequency at which you are actually illuminating creates a heat power density. Okay, so this is the expression for the heat power density. This can be actually derived from coupling the heat equation with the electromagnetic equations. And second point is that if you ask for a given particular geometry, if you integrate it over its whole volume, what is the total power absorbed by such kind of a structure? And that expression is given by this particular entity. So associated with this, which probably many of us in optics will recognize, is the cross section of absorption. Okay, this is also something which you find in various different contexts. For example, Beal-Lambert's law and things like that. So if you take, for example, a solid structure and illuminate it, then there is an associated cross section for absorption times the intensity would also be related to the total power absorbed. Okay. So in terms of experiments, this is also a crucial factor. Now, this is the heat which actually is very useful in a particular context, as I will probably allude to in the next few slides. Now, generating heat with metal nanoparticles. Now, this is a very important area of research to explore and understand. So, for anybody who is more interested, I would urge you to have a look at this very nice review article, where there is a very detailed calculation for a given particular particle. For example, 30 nanometer particle. And if you compare, let's say, the gold and the silver and gold, you can see that there is also a very interesting role played by semiconductors in this particular wavelength. So you can also utilize semiconducting nanostructures, especially those which are doped, which are heavily doped, can play a very critical role. Which means that the total power absorbed or heat generated also has a wavelength dependence. In fact, if you look at it very carefully, I would draw your attention to the gold. It actually peaks roughly around 500 to about 520 to 530 nanometer. And we all know that 532 is a frequency doubled Nd:YAG laser, and this precisely falls roughly around that particular region. And therefore, its utility in heating actually can be harnessed, as I'm going to show you going further. Now, you can also tune the size of the particle, what you are actually interested in. This is still a theoretical calculation, so I'm just showing you the results from that particular calculation. So you actually can tune this, the particle size, and you can see that the increase in the temperature around the local medium can be actually tuned by changing the size of that particular structure for a given particular illumination of excitation. You can also now arrange these structures. For example, instead of having one single particle, you can take those particles and arrange them in arrays. And you can actually now also look at probably the formation of a thin film, which actually is perforated in nature, which means that by creating a kind of an array of these kind of nanostructures, you would be able to now create a large change in the temperature, meaning a gradient of temperature can be created thanks to the difference and also the coupling effects between the plasmonic nanostructures. And remember, all these things are driven by an optical excitation, and optical excitation has a very important role to play. There are various different excitation schemes of plasmons, which can also be applicable for localized heat sources. For example, Kretschmann coupling and the tip-based coupling, and also grating-based coupling and scattering-based coupling. One can also utilize something called auto-coupling, which actually brings in a medium from the other side of the interface. So there are various different techniques. For example, I'm going to show you a little bit about this kind of excitation technique, and maybe also towards the end, I might show some scattering-based coupling. One of the important parameters, as I alluded to, for example, this is the data from my lab, where we show that if you take a silver film and you actually have a particular 532 nanometer line, you can ask for a what particular angle of incidence, let's say in prism coupling, would you be able to excite plasmons efficiently, which means also you can excite the localized heat source efficiently. So you can see that for a particular angle of incidence with respect to the prism, for a given particular wavelength of light, you are sitting right on top of the resonance. In that sense, you are able to transfer the energy very efficiently into that particular medium. So let's see how we put this into the use. You actually can take, for example, the 2 nanoparticles which I was talking about. You actually can create this kind of a confined optical field between 2 nanoparticles, where the electric field is enormously enhanced. You can also play around in such kind of geometries and create localized heat sources. And importantly, the power which you actually generate by such kind of interactions is essentially the expression what I was showing, which is the kind of product of the scattering cross-section times the irradiance what you have in your experiment. Now, the important question related to this talk is the effect of colloidal dynamics on such because of these kind of powers what you generate. So let me go to the first example. This was some time ago, about six years ago, or almost 6 years ago, when we actually did this experiment, where we showed that if you now take a plasmonic gold film and it's sufficiently thin, roughly around 40 to 50 nanometers, and if you have a fluid layer on top of it in which you have colloids, in this particular case, plasmonic colloids in this, like gold nanoparticles or silver or core shell nanoparticles. And if you eliminate this particular kind of fluid, you will now create a gradient of temperature, and the particles are now set into a convective roll. And as a function of time, you will start finding some very interesting assemblies which are formed, which because of an optothermal potential which is being created around this particular region of interest. Now, how does that look like in experiments? For example, I'm showing colloidal nanoparticle assembly when you have a single excitation. So remember, what you will see here is a kind of an elliptical formation, because if you take a Gaussian beam and you project it at an angle and take the projection on a two-dimensional plane, you will end up getting a conic section. And if you remember, if you take a Gaussian and take a conic section on that, you will end up getting with an ellipse. So that is what you would actually see if you eliminate a metal film. What you're seeing here is actually the trapped nanoparticles. And these particles actually are not individual nanoparticles, but they are themselves aggregates of nanoparticles. And their sizes are also sufficiently large. This is a kind of a large scale assembly of plasmonic nanoparticles. Now, the situation is very interesting in terms of electromagnetics, because if you now take the problem of nanoparticles at such an interface and ask yourself what are the possible situations in which you can create large electric fields, you see that you have various different configurations in which you can arrange the particle. I'm not going to go into the details, but you also have a capability of creating some localized heating potentials in this particular form. And importantly, if you now perform this experiment where this fluid has some kind of molecules, those molecules are now in the optothermal potentials of these nanoparticles. And they actually turn out to be so good and so strong that you can now detect them down to the single molecule scale. Now you can engineer the kind of film, for example, 532 nanometer, what I was talking about. For example, you take a gold film, you measure the reflectivity, and you can also now measure the nanoparticles plasmon resonance. You can tune the resonance. So you can see this is one of the very interesting aspect of this kind of optothermal thermoplasmonic trapping, is that you can create the potential by taking a particular film, and you can tune the resonance of the particles, where correlatedly you actually can change the size of the trap, what you actually obtain. So for example, you end up getting a smaller trap if you are slightly on the resonance, and if you are right on the resonance, there is a repulsion from this potential, and therefore you would actually eject out the particles, and you end up not getting any particles in the trap at all. So you actually can play around with this, and the optical resonances can be harnessed for various different applications. As you can see, this can be also used to sort particles, which means that if I have a mixture of this particle and this particle, only these particles get trapped, whereas these particles are ejected out. So there are a lot of applications you can envisage from such kind of trapping scenarios. Now, I mentioned that you can also look at molecules in such kind of optothermal potentials. Without going into details, I would like to mention that there is a very interesting fluctuation density spectrum. So shown here is the Raman shift of two different kind of molecules, Nile blue and rhodamin 6G, which are actually now in that particular potential well, which I just mentioned about. You can now ask how does the spectral structure look like as a function of series of spectra you can collect from a region of interest. And you can do reasonably involved statistical analysis, and you end up getting an extreme statistical distribution. Essentially, if somebody is interested, this obeys something called as Pareto distribution. So you end up getting single molecule events with higher probabilities, and a mixed event with lower probabilities, which essentially tells that you are now in the single molecule Raman scattering regime in such kind of potential wells. You can also play around with the potential wells by creating, let's say, parallel kind of structures. You can engineer the optothermal heating. So, for example, you can now align very long structures. For people who have some knowledge of pneumaticity, can recognize readily that these structures actually are now forming kind of a pneumatic structure. Especially people who understand liquid crystals would readily kind of recognize this. So this is also a raft formation principle, which also has some implications, but I'm not going to go into the details here. So again, going back to the heat, the last bits of the stuff, what I have to mention is that you can now play around with the structure which you can engineer. So this is one of our recent works where instead of taking a whole film, you now ask, can I take a kind of a reasonably kind of localized film structure? So for example, this is a fabricated structure, a chemically synthesized gold single crystalline triangle, which actually can also be used, by the way, to excite plasmons. I'm not talking about that here, but this can also act like a source of heat. Now, if you illuminate that kind of a structure through evanescent excitation, you create this optothermal potential. And geometry of illumination is something similar to what I just alluded to in the previous slide. Now, so if you perform, let's say, temperature distribution calculation using finite element methods, this is a three-dimensional calculations where you have an evanescent excitation, you actually can see the distribution of temperature in such a kind of a situation. You end up getting a large temperature at the center of this kind of structures, and it decays along this particular area. There's also a gradient of temperature in the z-axis. Importantly, these fields generally scale as 1 by r, not as the evanescent waves. So therefore, there is slightly different operational regime. So the experiment. Yeah.
Hello, Pavan. You have 5 minutes left.
Yes. I'm almost done. Thank you very much. Yeah. So if you now look at this kind of structures, you can look at this. This is a movie. What I'm going to play. This is a triangular structure which is now immersed in water, and you illuminate this kind of triangular structures, and you ask what happens to the distribution of the particles. In this particular case, silica particles in this particular fluid regime. What you end up getting is a very nice two-dimensional crystal. So you can see as a function of time, I'm going to play this movie again. If you illuminate this kind of structure through an evanescent beam, you end up getting a very nice two-dimensional crystal of colloids, which is now formed because of the optothermal potential what you have created. And this is all happening at metal fluid interface. So you switch off the light, and then this crystal makes a transition to a liquid again. Now we can go further and do some slightly more involved analysis. For example, Voronoi analysis to ask what is the distribution in this kind of assembly formation. How good is the hexagonal packing in such kind of structures? And what is the maximum coordination number for in this particular geometry? So you can readily recognize that the probability of having 6 as the coordination number, which is the case for hexagonal geometry, is maximum. But there are also some structures which show slightly different coordination numbers. Then you can also ask how good is the hexagonal packing. So you can see that the hexagonal packing probability is reasonably high in terms of order parameter. And this actually can also be used. For example, you can now create artificial defects in such kind of structures. You can also optically induced defects can be formed in such kind of structures, and you can play around with it. So finally, the question is, can you go all the way towards a single colloids with this kind of thermoplasmonic fields? And the answer is yes. This is a kind of a system which we have been studying. For example, if you have now a plasmonic wire, which also facilitates propagating plasmons, you can excite the plasmons from one end and outcouple the plasmon from the other end. In between, there can be a sphere which can also participate in this interaction. Interestingly, this can actually be utilized for various different applications because microspheres themselves give rise to some beautiful whispering gallery modes. So this is actually an experimentally measured whispering gallery mode. You excite the wire at one end and look at the light which is coming out at the distal end. So this is an EMCCD image of that particular interaction which is happening. But here in this particular structure, the colloid actually is statically coupled to the wire. What we are now trying is that whether we can actually move this particular colloid around. So here is a movie which I'm going to show where we can reconfigure the optoplasmonic coupling between the wire and the particle. So you can see that the sphere actually is now trapped and moved around the wire very carefully. You can now place the sphere at the location of your interest, and you can play around with its geometry. I should mention that we already have been pushing the limits of this, the trapped object. For example, what I'm showing here is roughly around 2.5 to 3 micron in diameter. We can now go all the way to about 200, 250 nanometer nanoparticle. So then your interaction actually can be tuned in terms of plasmonic structures with the plasmonic wire and things like that. So this is a work in progress. Hopefully some other time I can actually give you a greater amount of information on this. And we are reasonably excited about the prospects using such optothermal potentials, because the wire itself actually is a plasmonic structure. So it can create some interesting opportunities. So to summarize, I've just spoken about dynamics of colloids in the presence of surface electromagnetic waves, especially the SPPs. One can engineer absorption of metallic nanostructures. I kind of gave a slightly small tutorial where you can understand the main principle behind this mechanism. You can actually expand this all the way to Rayleigh limit. In fact, yesterday, Amit was giving a very nice kind of prospect of trapping atoms nowadays on a chip. These kind of potentials actually can also be of very high interest there. But here, the thermal noise is an issue. So there is a lot of interesting questions. Whereas if you take single molecule spectroscopy, their thermal noise might actually not be such a very crucial factor, although it does play a role. One of the fundamental question is the principle of back action, where you can ask what can these colloids, for example, do to the SPP itself. This is kind of an interesting and open question which needs more attention. With this, I'm going to just end my talk by acknowledging a lot of people who do quite a lot of work. And I only just present most of it. But I should mention that I'm quite excited about the stuff, what we do. And also, I myself am doing some experiments. So hopefully I will be able to report some of the experimental results also at some point of time. Past students have played a critical role, and they have set the ball rolling in that sense. And both MS students and PhD students and postdocs. And our funding comes from various different resources. And I thank you all for turning up on a day when India is playing a cricket match. Thank you.
Thank you, Professor. So for the informative talk and the wonderful talk. And so now the floor is open for question. Whoever has question can raise your hand. And also, yeah, so one question from Roshan Theory.
Yeah.
Yeah, hello, sir.
Yeah, please.
Very nice talk. Yeah. So
Yeah,
my question is that you gave a slide where like a lot of particles are trapping, and based on that, you gave a line profile, like extinction profile of that. So
yes.
Yeah. So my question is like, as the density of particles are increasing, so the line profile that the broadening will happen of the spectra, isn't it?
Absolutely right. You're absolutely right.
I can see that, sir, in that 3 slides, like 3 figures.
Yeah.
One of that extension and broadening is not as per that. Can you just?
Yeah. I'll come back to that plot. This one, right?
Yeah, this one. Second one is quite broadened in comparison to the former first one.
Absolutely right. Right.
Is it some density or something like density of
that?
No,
this particular resonance is measured prior to the trapping. Okay. This actually tells you what is the probability of formation of the trap. This is a very important point. If you actually go and read the paper, this is something which we have discussed in reasonable detail. But I'm very glad that you mentioned this particular point, because see, what happens is as a function of time, once you create such kind of aggregate, the resonance starts broadening and also shifting towards the red end of the spectrum. Right?
Okay, sir.
Yeah. I mean, no, this is an important point. The most important point here is that if you actually have a resonance already in the particle, even for the first particle to get trapped, it's very difficult. Okay, that is where actually the problem arises. The problem arises not because the aggregates themselves actually create a larger and larger resonance and move towards the red end, but the problem arises when you actually have the first particle itself going away from the resonance. In fact, if you look at the principle of optical trapping, for example, in dipole approximation, even for, let's say, atoms and other things, this resonance tuning actually is a very important parameter. So you will have to choose the particle to begin with, which is slightly away from the potential wells resonance. Once the particle comes in, then obviously the structures which they form, their plasmon resonance would actually change quite a bit. In fact, that would actually also act like a self-limiting factor. So this is actually quite an involved process. Huh? I'm glad that you brought this up, because there is some role for the resonance to play up to a limit, and after that they might actually breach that particular limit, and you'll have to worry about it furthermore.
Mm-hmm. So like the aggregates entire these aggregates are forming, so the resonance will shift, isn't it, because of this?
Absolutely.
Mm-hmm.
The resonance will shift. Now, if you look at the experiments, what we do, there is also a limit up to which this potential can be created, and in principle, then you should keep adding more and more particle, but that doesn't happen. If you again look at the data what we present in our experiment, there is a very nice sigmoidal curve which shows the growth of this cluster. Okay, initially it actually keeps increasing in size, then it saturates. Okay, that saturation also probably also has to do with various different factors. I should mention that there is now an optical kind of a potential there. There's also thermal potentials there. Excuse me. So the factors which you have to account for will be multiple. But for example, if you replace this with, let's say, dielectric spheres, then you actually don't have to worry about that at all, because there will be no resonance per se in the dielectric spheres there.
Yes.
Yeah. So there is a fine kind of trade-off between these two you have to use. Yeah.
Okay. Thank you, sir.
Yeah.
Okay. Any other questions?
Ravi.
Yeah, Sushil has it.
Ravi,
Yeah.
most students want to ask. Can I ask a couple of questions?
Yeah, sure.
So thanks, Pawan. Actually, I've been following this work for a while now from your group. So sometimes I have felt that the triangular metallic islands which create crystalline structures, those actually are quasi-crystalline. Have you tried to investigate the structure from the quasi-periodicity point of view?
Yeah. Actually, it means if I understand correctly, you're talking about quasi-crystallinity of the spheres which are assembled.
Yes, yeah.
You're absolutely right. You're absolutely right. In fact, see, if you look at the paper, we actually only tell that there is some kind of a packing. It's not a perfect single crystal. In fact, again, a lot of details don't come in the talk, but this is something which is very important point. The problem is that there might be actually a kind of a quasi-crystalline assembly which is happening. The Voronoi analysis actually is indicating towards that direction. In fact, I did not also get time to show a data. Maybe I can show you something. Okay, this is, let me just quickly see whether I have the data here. Yeah, so this is actually a data which probably would be interesting. Is the screen visible?
Yes.
Yeah. So now what we do is, see, instead of doing this optothermal potentials through an evanescent excitation on a triangle, we do it through a film. Okay, what I just showed earlier. So I'll show you some data, which is something quite interesting. So you can now see that the assembly process actually gives rise to some very interesting periodicities. This is slightly more, if we do the analysis, for example, you can also perturb the system and perform the experiment with the wave vectors, which are now parallel to the film or are really focused onto the film. Okay, that actually can also act like a parameter. And you can also assist the assembly in the presence of a wire. Okay, and this can also tune the periodicity, or rather in terms of the hexagonal packing efficiency, which can be tuned. Now, this is not just only the movies. For example, you can now go and do the analysis. See here, you can see now for a given particular assembly, the coordination number actually is much more in terms of the probability being 6, and there is still these wings. Okay, which indicates that it is not a perfect crystal, and there is some kind of a quasi-crystalline kind of distribution which is happening. So this is something which we are still trying to understand, but a very important point what you made. And it's not a perfect crystal. There's still room for us to make it better. But having defects in crystal probably also makes it better in the sense it may have its own.
I wasn't addressing. I wasn't sorry to interrupt you. I wasn't addressing the system as not a perfect crystal. I was addressing it as something more exciting of creating quasi-crystals.
Quasi-crystal.
I mean, for a person from disordered systems, departure from periodicity is actually more attractive.
Absolutely, absolutely right. No, in fact, I should tell the other way around. In fact, we have been actually looking at your work, and we are trying to learn a little bit about such kind of distribution systems, because see, we can also do optical measurements on such kind of periodic structures. And they are all dynamic systems, meaning you can create and then perform and then release it back. So this is something which we would want to go a little further and do some work and then probably talk to you and
that's nice.
they understand this. So one of the things we can also do is a momentum space distribution measurement from such kind of structures. So which will tell, as you mentioned, if there is some kind of a quasi-crystalline pattern formation. Let's say if you have molecules on top of such kind of structures, it will become like a quasi-crystalline periodic crystal. So that then we can actually look at the k-space distribution to look at the stop bands and other things if in case there is any. But we are still working towards it. But this is something we would want to pursue at some point of time. I will surely get back to you once we have some more concrete results. As you can see, the lockdown had played a havoc. Actually, these were all right at the thick of the that time and all. 6 months students were all gone from the lab. So that's
very nice.
Problem.
Very nice. Thank you. Thank you.
Yeah, thanks.
Okay, thank you again. So I hope there are no questions. Thank you again for the wonderful talk. So now we'll move to our next speaker. So our next speaker is Professor Ayan Banerjee from IJAR, Kolkata. Professor Banerjee is presently a professor of physics at IJAR, Kolkata, and has been working in the field of optics and spectroscopy for the last 22 years. He obtained his PhD in physics from ISC Bangalore and joined General Electric Global Research Bangalore as research scientist. Since 2009, he has been faculty member in the Department of Physics at the Indian Institute of Science, Education and Research, Kolkata, where other than being deeply involved in undergraduate and postgraduate teaching, he has also set up a light matter interaction lab, which chiefly focuses on optical manipulation and study of mesoscopic matter employing optical features, with multiple projects in diverse areas of research. In IJAR Kolkata, he also plays a key role in science translation into technology, being one of the founder directors of the Research Innovation and Scientific Entrepreneurship, that is RISE Foundation at IJAR, a section of 8 companies formed inside the premises of IJAR Kolkata to incubate deep science-based startups. Professor Banerjee has close to 50 published papers in peer-reviewed scientific journals and 21 patents. He is also senior member of SPI since 2002. The title of his talk today is Transforming and Manipulating Light Using Optical Tweezers. Now I invite Professor Banerjee to present his talk.
Yeah, thanks, Ravi Shankar. I guess that's who you are from your Zoom title, What is Coming, Ravi Shankar. Thanks for this invitation. I think it's a great idea that, these student groups are coming up and making conferences. We also in IJAR, we have, both SPI and OSA student chapters, and we too, have conferences, and hopefully this year we also shall have something coming up maybe in the summer. But yeah, that also will probably be online, though things might have settled down somewhat. But yeah, we probably won't take chances because online is one modality where you can actually have a lot of people coming and joining without all the hassles of physical travel and all. I think it's going well. Okay, so today's talk is on, as Ravi Shankar said, on spin-orbit interaction. So I'll just share my screen. Hopefully it'll be fine. Yeah. Yeah, is it visible?
Yeah,
Yes.
yeah.
Okay, now let me just get this tools. Yeah, can you see my pointer?
Yeah.
Okay. Acha, Ravi, please warn me when there are like 5 minutes left or
Yes.
something. Okay, because
Sure.
I just took a class. I just finished a class, and a teacher does not stop talking. So yeah, please tell me. I'm
Yes.
still in
Yes.
that class mode. So yeah, when time is up, you please tell me, and I will just stop. Yeah. So today, yeah, as I think it was announced already that we are going to talk. I'm going to talk on this topic called transforming and manipulating light using optical tweezers. So this is interesting because yeah. So before we just go on to the topic, this is my lab, and of course there are a lot of other students as well, but these pictures of these guys have been put in because these were the people who were instrumental in doing the work that I'm going to present today. This person is now a faculty at IIT Madras, and all these are MS students. This person, Ramanandan and Souvik, these are the ones who are working presently. Yatish and Devapriya have both moved on doing PhDs abroad. And Ratnesh also is almost finishing his PhD at Singapore. No, yeah, at OIST. Yeah, that's Japan. Sorry, not Singapore. So he's almost done. And these were the 5 people who have led to whatever work has happened that I'm going to, 6 people actually, report today. And this is something, yeah, this was actually the first thing that we did in our lab, one of the first projects, which of course, we have plenty of projects with optical tweezers in our lab, and this is the one which I really am fond of, especially because this is the one that started off our lab. This is spin-orbit interaction of light. Other than that, we also have very diverse, experiments on microreology, and then this is a technique we have evolved. In fact, I just could hear Pavan's talk just last 10 minutes because my class finished just before that. And this is also something where we use this thermo-optical potentials to create bubbles in order to, to then draw patterns, which we sort of have evolved in our lab. Then a lot of stat mech. And this is a very different project, trapping in air using, it's like a tweezers in air, but does not use dipole forces. These are much, much, much more stronger traps and very dirty systems as well. And the physics is pretty intriguing, not too well known, but you get very, very interesting results. So today's talk, however, is very different. Optical tweezers. I'm sure many of you must have heard of it. So you basically have this focused light beam, which essentially traps particles, and particles that have a polarizability or an induced dipole moment. So that can go from dielectric particles to even metal particles. Of course, they have to be small, because unless they are small, they do not feel the force of light. So these photons have momentum, but this is very small. And of course, if you and I go out in the sunlight, we will not fall down because of it. But if you have a mesoscopic particle, then actually that will be kicked around quite a bit. So optical tweezers take advantage of that. So you have focused light. So that creates an optical gradient, and that gradient has is basically the gradient of intensity that creates a restoring force, which helps to trap these particles. And they can be trapped and manipulated. And the reason that we call this thing, this object as tweezers, is that this light essentially takes particles and does whatever it wants with them. Whatever we want with them, rather. And so this is a very good system for trapping and probing particles, giving controlled forces and huge applications. So Ashkin's Nobel Prize, which happened in 2018, was, however, for biology, not for the other things, because enormous things are done in biology. So little example of what we can do to small particles. So these are all mostly polystyrene particles of this is like 1 micron diameter. This is slightly different, but some kind of a particle where this is like this is an elliptical particle size. This is like a soft oxymetalate. Both of these are that, and this is a quartz particle. So basically, what we are doing is, here we're changing polarization, and the particle is moving around this. This is spontaneously rotating. This is something very interesting. I'll cover this actually. But all sorts of things light is doing to particles. However, and that is what I'm going to talk about today, actually the tweezers also does very interesting things to light itself. And this is a small representation of that. This is less the transverse cross section, okay? So think of transverse cross section as a horizontal section. So this is the horizontal section, and this is the vertical section. So this is the horizontal section. But look at this, the mode of the beam has become like that. It's discontinuous almost. Okay. Then here it's rotated somehow. Here it's again very, very different. Different here. This is rotated in the other direction. So all kinds of things are happening to light itself due to the tweezers. And not only just to the light intensity, but also the light polarization. So very, very intriguing things happen in the process of optical, of tweezing, if I say so, because essentially what we do is tight focusing, and that tight focusing causes something called the spin orbit interaction of light. I'm very glad to see that Pawan also has published in this, I think this year itself. So this is something, this is fascinating. SOI, of course, in atoms, I'm sure you guys have studied in your masters, that it removes energy degeneracy. In fact, that's what I was just teaching in the class that ended now. So, the hydrogen atom problem, what Bohr said is that you just have n square, right? There is no dependency on the on the orbital angular momentum, the magnetic quantum numbers, nothing. But then that was not correct, as spectroscopy showed, and then it was understood that it is the spin orbit interaction, relativistic effects, which actually causes these many, many, many energy levels to happen, and fine structure, hyperfine structure, all kinds of stuff. What is SOI in light? What does that give? So that gives physically realizable, measurements as well, and that is basically gives trajectories which depend on polarization. And oppositely, you have so the path of light basically depends on its polarization, and that can be measured as well. Shifts of the path of light due to polarization, due to input polarization, and it also gives intensity profiles which depend on the polarization. It gives all kinds of things, spatially varying polarization, which is like the spin Hall effect, and you also get a lot of interconversion of spin. So light has two types of spin. There is the polarization, there is the orbital angular momentum. That can also, orbital angular momentum can also be intrinsic or extrinsic. So for example, if you just take a lens, have light pass through it and block half of the lens, then basically what you create is something like a phase gradient, okay, an azimuthal phase gradient that causes an extrinsic angular momentum. If you think of, if you just take the Laplace equation, I'm sorry, our Helmholtz equation, and solve it in cylindrical polar coordinates, the solutions themselves give the Laguerre Gaussian modes, the LG modes, as we say, and those have intrinsic orbital angular momentum, okay? So what is the spin orbit interaction? So essentially, it is nothing but some kind of weak coupling between the spin and the orbital motion. So this is a beautiful thing that Konstantin Bliok, was one of the gurus of this field, wrote in Nature Photonics, that if you have, for example, a k vector of light which is following a curved trajectory, then you see that if I define a polarization vector initially here, then as the light beam reaches here, then the polarization vector would have rotated. Okay, because of the curved trajectory of the k vector. If this were physical, I could have shown you, just you take, extend your hand and do some rotations, and you will find that your hand, the fist direction would have just rotated as you got your hand from like 90 degrees out of your body, sort of from your sides to your front. You will see that it would have rotated. Your hand fist would have rotated. Anyway, so here what you see, however, is a different thing, where you start off with a right polarized, RCP, right circular polarization, left circular polarization. You let them propagate through an optical fiber or something, rather here. You start from here, then you see that this blue and the red, they have actually, they have shifted in the transverse direction. This is called the spin Hall effect, okay? So what happens? What is the spin Hall effect? This is what I'm sort of, this is a very important part of our talk. And this is, as I said, as was apparent in the last slide, this is nothing but the transverse spatial shift of the opposite circular polarizations. And that and what is the orbital Hall effect? That is essentially, you have these, if you, have these orbital angular momentum modes, then you will actually see that even those might actually shifted in space. And that might cause intriguing effects in terms of particle rotation. Otherwise, you can also get very interesting rotation of the beam itself. You remember I showed some pictures where of the optical of the light beam, where those two lobes seem to be rotated with respect to each other, right? And then what is so that is something which happens if you actually have this OM induced or present in some manner. Okay, this OM, when I say it's orbital angular momentum. And what is the origin? Origin is very, very simple. See, essentially, pointing vector is something which we know is in the longitudinal direction, right? It's in the direction of the K vector. That has a very important assumption. That assumption is the Maxwell model, if we can say Maxwell picture for plane waves, are all perpendicular to each other, right? Nothing in the direction of propagation. You have EX, EY, EZ, everything, nothing in the direction of Z, right? However, that is, and so as a result, the pointing vector E cross B is only in the longitudinal direction or the K direction. However, that is not correct the moment you confine the field. If you confine the field, immediately you are not allowing, so del dot E equal to 0 has to hold, it has to trivially hold. And this is trivially satisfied for a plane wave. This is trivially satisfied because intensities of plane waves are the same everywhere. There is no spatial dependence. But the moment you truncate a beam, immediately X and Y, you actually create a boundary. So there is a gradient in X and Y, strong gradient. In order to satisfy this, you have to have a gradient in Z as well, which means you have to have a Z component, right? The moment you have that, that means that you have a transverse component of the pointing vector as well, because now you have a longitudinal component of the field. And the more you confine, the more strongly you confine, the greater is this longitudinal component. And because of that, the transverse component of the pointing vector is also large, which leads to very interesting, and this transverse component is dependent on hypotheticity, as a result of which you get very, very interesting effects. Okay. So this is what we do. This is our system. So tight focusing is equal to optical tweezers. Okay, so what do? We have an objective lens. Light comes in from here. We have a bit of immersion oil, which is like, that is basically used to reduce spherical aberration and all that. So, and also to increase the numerical aperture of my objective lenses. That is just 1.4. You will never get an air. So this is, you need 1.5, 1.6. Then you have a cover slip, which is typically of the same index as the oil. And this is where we really do interesting things. We change the refractive index of the cover slips. Everybody keeps the same refractive index. We did it by serendipity. I was not experienced. This is optical tweezers. I've never done before this. And I just bought cover slips from Sigma Aldrich. And yeah, so anyway, let me just continue. So then we have this little bit of water, drop of water, about 30 to 40 maybe microliters, thickness about whatever 28 to 30 I've mentioned. It can go up to 40. We have our particles suspended here in the water, typically polystyrene, and we have a top glass slide, which is just to sandwich this water layer. We just put a drop of water on this cover slip and just paste. This is very, very simple. Okay. And this has led to these, and this is because essentially I made a mistake in buying the cover slip. When I bought this cover slip, typically this is what I saw, and we were completely dumbfounded because these were polystyrene particles. We did nothing, and you just let it turn on the system, and lo and behold, they were coming like this, forming these nice patterns. This, and then I also got cover slips from, I think I don't remember, from standard glass cover slips. These were not glass cover slips, which gave these. I got standard glass cover slips, and then we never ever saw this. We only saw clumps of patterns. And as a result, there was nothing, no report in literature. So we had to simulate. We had to find out what was happening in the electric field. And this is what you have. You have, the system is like this. You have plane waves. If you have a Gaussian beam coming in, you have the numerical, high numerical aperture objective. You have the oil here, different refractive index. Then this is the sort of cover slip. This is the sample chamber. This is the top slide. So you have a stratified medium. And importantly, for most optical tweezers experiments, N1 is equal to N2. Our case, it was not. N1 was not equal to N2. And that led to fantastic effects. Okay. What was happening here in a nutshell? Just give me a second. What we were doing, now just think of it. These were my initial K vectors, all in the same direction. Then I'm starting to focus, right? And there are two types of, so what is happening is now all these different K vectors have, so initially if I say that they was all polarized in single direction, the moment I start focusing, their orientation is different. So this is almost like a depolarization effect, but what is more interesting to understand is actually what this is happening is that they are gathering some kind of a geometric phase, because there's an illusion of polarization. So there are two ways that you can sort of develop geometric phase. One is that if you change polarization states along the Poincare sphere, that is the Panchratnam-Berry phase, and the other one is if you change the trajectory itself. What we are doing here in the act of tight focusing is that we are changing the different K vectors in different directions, as a result of which we have a gradient of the geometric phase. Gradient of geometric phase, and this is, remember, very much in the azimuthal direction. And what is, if you have a gradient of geometric phase, what do you have? Delta phi, del phi is the angular momentum operator. Right? So you're actually generating some kind of orbital angular momentum by just the simple act of focusing because of this gradient of geometric phase, right? And if you look at this, what we are actually doing is we have an objective pupil, that's the plane, and then it's kind of going, changing, focusing it here. And essentially what we are having is we are doing some kind of, if you think of, we're going to r theta phi coordinates, we are basically doing some kind of a rotation, and actually a rotation in terms of theta and phi. Let me just explain this in a different way. So this is complicated, right? Because the paraxial approximation has broken down. We cannot work with the paraxial approximation now. What we have here is basically we have to track each K vector. Okay, so what we do, this is called the angular spectrum method, where you take, sort of a Fourier transform, you find out how a certain K vector evolves in space, right? And then you do immediately an inverse Fourier transform and get back to the field. Then you go a little bit of, you first find it at say z equal to 0, then you increase z, do the process again, keep doing it to whatever you want, whatever z you want. Okay, so this is basically you're finding out the transverse distribution of the electric field by this method. And in the paraxial limit, this is essentially just Fourier transform. Here it's more complicated because you need to keep track of the polarization as well. Okay, how do you do that? So this is the general, you don't have to look at these complicated expressions, but this is the general sort of framework where this is the incident field, and I'm writing in terms of theta phi, and I'm doing this sort of, this A is essentially this whole thing, right? And this A is basically, so as I said, I'm doing some kind of the focusing, the act of focusing can be thought of as rotations in phi, theta, minus phi, you come back to the lab frame. Okay, and this T essentially are the Fresnel coefficients, which for a layered medium will actually be complex. And that also gives an additional phase. And this is what is critical. When we have stratified in medium, these are complex, you actually have additional phases which come in. So what people generally saw in optical tweezers was only that limited, that phase gradient which comes in geometric phase, that kind of thing. But that was just too small to see any kind of noticeable effects. Moment I do this, I get stratified media inside this, then that phase gradient increases. And then we get all kinds of very interesting effects. So what is happening finally? This is that A matrix. So think of this. I come in with incident light which is linearly polarized. I just put this, this is just a matrix multiplication. And this is my final light. And this is essentially all kinds of complicated Bessel integrals. Forget about that. But this is what I get. But more importantly, if I actually come with input circular polarization, if I just break down this in terms of these sort of eigenvectors, or if I call these the angular moment, the spin modes, what you see here is I came with input, maybe right. This is the same, but now I have a left. And along with that, for angular momentum conservation, I also have an e to the I power 2 psi, and this is orbital angular momentum. And see, the total momentum is still 1. This is 1 minus 1, this is 2. Total is 1. It has to be conserved. This is it, and this is the longitudinal component. What is very interesting is if I come with linear polarized light, I will now actually have it broken down into regions of right and left, which is remarkable. We have done this in experiments. So this is light, this is the transverse profile of light, and this is, of course, this is the spin. In terms of polarization, we have marked out we have done the spatial distribution of polarization. So these are essentially with positive ellipticity, these are negative ellipticity. And this is essentially my spin angular momentum density. If I put a birefringent particle here, which can exchange angular momentum with this here, what I will see is actually particle rotating like this, clockwise. I put it here, I will see anti-clockwise. And most interestingly, if I actually have two beams which are next to each other, then this is sigma minus, this is sigma plus. If I put a particle here, it'll traverse and spin in one direction. If I come with this beam and overlap it here, these two will cancel. The particle should stop. Look at this. This is rotating. And here it stops. I let that other beam go. And here it starts again. Right? So this is remarkable. So we actually saw this. We could actually stop particles and have them rotate and do all kinds of things. Leave it and they go again. Okay, so this was a very interesting finding. It was done a long time back though, but we reported this in 2013 or something, I guess. The start of things, but more interesting was something phenomena called spin momentum locking. And what is that? So condensed matter physics, that surface states of these topological insulators have their spin locked at right angle to the momentum. What does that mean in optics? Basically means that the transverse spin that I just said it is a consequence of longitudinal component that is helicity dependent, but the spin angular momentum is not helicity dependent. Okay, so what does that mean? So basically, our Poynting vector you can actually write down in two components. So one is this, which is essentially due to the local. So this is like the canonical or orbital momentum. And why is this? This sort of depends. If you do this, remember this operator is like del phi, right? I del del. So this is nothing but the phase gradient, which gives you the OM. This is what gives you spin in light. This is nothing but my spin dependent polarization, and this del cross S is basically what gives that. And this PS, what we call is the Bell-Infante spin momentum, the curl of this essentially this what if that is this if you take a curl of this, you essentially get nothing but the spin angular momentum. Okay, so what is very interesting is if you now just write down these things. So this is a very interesting thing. I don't have time to go around this. So this actually tells you why you have, even for a beam, a Gaussian beam, why should there be spin? So you basically think of these small circular loops. If you think of the fluid dynamic picture, you have these small vortices generated. They will all cancel each other, but the one at the boundary, that will not cancel. So cancel out. That will not cancel out. So you will actually get some kind of a current at the boundary, and that is the origin of spin. That is actually circular polarization. Okay, so now if I just, this definition I gave you of the spin momentum density, and the Poynting vector is very, very clear, right? This is the Poynting vector. Everybody knows that. This is spin angular momentum.
Excuse me, sorry, you have 5 minutes.
5 minutes left. I'll quickly finish that. The last part I'll probably skip.
Yeah,
so
sure.
If I see that RCP, you see SZ, if I see this, if I have RCP here and LCP, SZ is flipping sign, but SY and SX are not. But these are calculations. So same thing is happening for PX, this is flipping sign. So transverse Poynting vector is flipping sign, but the longitudinal is not. So this is what is happening. So this is essentially called spin momentum locking. If I change my input circular input helicity, then what I get is that the Poynting vector, the transverse component, will flip its sort of spin direction, its direction, but the longitudinal component will not. And the opposite happens to spin angular momentum density. SZ will flip. And that is what causes particles to spin in optical tweezers. And now we did an interesting thing. We actually used these cover slips, which were like very high refractive index. You see this. So this is a plot of the electric field intensity, and that's this Poynting vector density. You know what the Poynting vector you saw. You see here that these regions, there is an overlap. So what I mean here is if I can actually trap a particle at a location where that spin momentum is high, I should actually be able to sample it. And this is what you see. So here, I mean, this is not so high. This is quite low actually. And then the intensity falls off very, very fast. If I go to this, I have these side lobes. These side lobes sort of start appearing in the beam intensity profile itself. And here the Poynting vector is actually, spin momentum is high. Here it's even higher. It's quite high. In fact, it's higher here than in the center. I will actually sample that spin momentum. This is the setup is simple. Standard tweezer setup. I have a lambda by 4 plate to change the input polarization. Okay, and this is what I have. So you see clearly, if I have RCP input polarization, I have the particle rotating angular momentum. So it is actually going like that. And here it is going like this. So this angular momentum comes because of the OM, that is not spin. But the direction, see, the OM does not depend intrinsically on spin, but the Poynting vector does. So the fact that when I change the polarization, this actually changes, the sense of rotation changes, is actually a direct manifestation of the Bell-Infante spin. So OM is, of course, the optical by the Bell-Infante spin. And here we do it online. So you can see here, this is the particle that is rotating. And in the same experiment, I actually flip it. I flip the polarization and see it's going the other way. In the same experiment. It is like sort of, yeah, you can see there's a small sort of they're very difficult to control and all. So there's a big story there. But you can actually see that this is very clearly precessing. And this actually, if you see initially, there's a small loop as well. Yeah. So this is what we had. And this was published last year. So I have a next thing which Ramanandan covered yesterday, my student covered. So I'm not going to spend time at all on this. But basically, it's a rotational Hall effect where if you have a higher order Gaussian mode, then essentially, and this will be created by a Q plate. And what we see is the AG beam center of gravity rotate. And that is because when I have this now, this is AG mode. If I write the input AG mode, which is right circular polarized, I actually have these left circular polarized components along with this high orbital momentum, orbital angular momentum, this I psi and 3 I psi. And opposite when you have LCP, right? You have the other modes coming in. So these essentially cause a redistribution in the intensity profile of the light beam, as a result of which you actually see, if I just consider these intensity profiles, I12 and I14, I get a clear rotation for RCP compared to LCP. And if I, however, take the total momentum, then this total transverse intensity, total transverse, I'm not taking the longitudinal bar, this is not the total intensity, total transverse intensity. Then, however, this rotation sort of decreases. And the reason is that we have now this, the Z component, which also adds on, which kind of reduces the play, the total, it sort of cancels out the rotation somewhat. And when you measure, you cannot just take out I12 and I14, you will take out the whole thing. And what we, however, get is something that's very close to experiments. So again, that, the total amount of rotation increases when I change my, refractive index of the cover slip. So here you can see that, this is these angles, these lines that I did was to try to quantify the rotation. So this is with respect to this line. So this is like a center of gravity, which we calculated from the pixel values of my the image. And then we sort of found out where they were minimum. And as we scanned along these directions, right? So we found the line of minimum intensity and we sort of put a plot there. And then with respect to that, we, found out the angles for these are two different covers. I mean, this is for RCP and this is for LCP or whatever, something like that. And you can see that the rotation is nicely reversed. Our error bars are quite big here, but very clearly we follow the simulation trends that as you increase refractive index, the tilt is actually increasing. So mind it, this is not a direct a manifestation of OM. If you actually put, this is not an active trap as well, we just imaged the beam. If you put, however, particles, birefringent particles, then an AG beam carrying no intrinsic OM or orbital angular momentum should actually rotate, have the particles move in orbits. You should actually see rotational motion in the sense that you'll see orbital motion without having any input orbital angular momentum. This is what we plan to do next. This work is unpublished, by the way. So it's probably fine, you're recording, but it's okay probably. I trust everybody around here. So fine, so we are actually, this is the end. As I said, I think I have given you some kind of a description of how tight focusing, which happens in optical tweezers, it naturally changes the light, both intensity distribution as well as the polarization profile, and generates these interesting effects of spin Hall effect and orbital Hall effect. And these actually cause different trajectories dependent on input polarization, and you get very, very novel modes of particle manipulation. You get both spin motion as well as orbital motion. So we were able to show for the first time, probably for propagating beams, at least the existence of the Bell-Infante spin. And we now have to go on to higher order modes where we plan to probably see effects of orbital angular momentum in a beam which did not have any intrinsic OM. We've already seen indirect effects of the rotation of the beam, which is like a manifestation of the optical, the orbital Hall effect. Yeah, and this is really, a lot of stuff can be done here, and we are on that route. Hopefully, more interesting things to report in the future. Yeah, thanks.
Thank you, Professor. That is a wonderful talk. Now we'll take question. So yes, Professor Pawan, you can continue.
Should I? Yeah, I think it's fine. Should I stop sharing or something? It's okay. No, you should.
No.
You'd like to see the slides.
Anyone have any
Pawan, hi.
Yeah, hi, and very fascinating topic and very nice work. In fact, this prospect of spin and angular momentum, especially in tweezer, is very, very fascinating. So can you please tell me the transfer of momentum? You did mention that there is a gradient, which is which is the reason which you are.
It's basically the geometric phase gradient.
Phase gradient. So if you have an inclusion, for example, in such that inclusion is static. For example, if you have a glass cover slip and you had some kind of a foreign object, and if you try to, let's say, trap another floating object in the vicinity of the this particular static object, would you also find such kind of manifestations?
So that, Pawan, you are making it very complex.
Yes,
because I'll tell you why. See, because OM, so if you look at Nirmalo's group, we also have somewhat contributed. A lot of this stuff happens in scattering as well.
Scattering, yes.
Hugely. So what you're doing, Pawan, is you're actually mixing these two up. So you're doing both tight focusing and scattering together.
Scattering, yes.
So that will probably have very interesting effects.
Yeah.
Sort of gleaning them out, that may be a bit complicated.
Yeah. No, I totally understand.
Both approaches. So that will be
exactly. I know.
Why talk about this? Because see, Nirmalo has already these set up. I mean, he has codes to find out, how things, how the sort of spin-orbit interaction happens in scattering and the transverse pointing. Everything they have.
Yes.
They published several papers on this, and we have this thing. So we could, in principle, marry these two and see what happens if you have a scatterer, and then you have a particle trapped in its vicinity, and then see what very, very, very intriguing. Probably.
Yeah, very intriguing. Yeah, thanks. Thank you very much. Thank you.
Very intriguing.
Hello. So, sir, I have a question. Like, so what is the birefringent material? I mean, if I missed that, but Hello.
Yeah.
So, what was the material, birefringent material you used?
I didn't. Oh, yeah. Okay. So what we basically was very simple. Yeah. It was some kind of soft oxometalate, and these have no inherent birefringence.
So voice is breaking.
It was just formed birefringent. Okay, so very weakly birefringent. That was the first material. Later on, of course, those.
Hello, Professor Varad.
Particles.
Your sound is breaking.
Yeah, my internet. Yeah. Can you hear me now? It's got static and then it's back.
Yeah.
Can you hear me now?
Yeah.
So these actually were liquid crystals. So these were liquid crystals. Particles made out of, these were basically liquid crystal drops. I mean, particles made out of some liquid crystal material, actually. These had good birefringence, but the ones that I showed, one was quartz, which has again very, this is like a elliptical quartz particle. Again, this had a bit of form birefringence, and I think these were soft oxometalates. These are very poor videos as well. These were like soft oxometalates, again, form birefringence with no inherent, not really birefringent material that way. This one, however, was liquid crystal. Yeah.
Thank you. Anyone has any question? You can ask.
I have a quick question.
Sushil, please.
Sure.
This is really amazing. I probably missed one point. You want to have a higher refractive index contrast.
Yes.
And that contrast is between the special cover slip which you accidentally bought and
Yes.
the liquid in which the particle is kept, right?
So basically, no, actually, Sushil, so this is my oil. Okay, this is not drawn to scale.
That's oil,
This is very small. This is the cover slip.
Correct.
So basically, in most tweezers experiments, you see these two matched.
They are matched.
But we don't have it. Okay, so we have different, all four are different. Okay, so typically in optical tweezers, you have N1 equal to N2 and then N3. So it's basically like a lens, just one layer and another layer. Now we have three. So you can do, fantastic things. For example, at the moment, what my student Souvik is trying to do is essentially see if you put gradients in this direction. We have now gradients only in the longitudinal direction, axial. But what happens if you do gradients along this? Right? That makes it even more phenomenally. So more gradients you should generate. In the sense, the geometric phase gradient will be even more interesting. So at the contrast, it was just this.
Sorry. So sorry to interrupt you. The enhancement of contrast that you were talking about was between the oil and the cover slip.
Yes.
Oh, that. Okay. I thought between the cover slip and
no. But it's finally becomes the same, right? So that contrast will be more here as well, right? The more I input here, or water is fixed, right?
So which one is the parameter that you're? I mean, there must be some.
This one. N2. Completely N2.
Okay.
Completely N2, entirely N2.
I see. Okay, thanks.
By the way, Sushil, I would really like that correlation thing you were mentioning, right?
Image
correlation. To get in touch with you. So what? Because can we just discuss this offline? I'll send you an email. Maybe Absolutely. You can just tell us, if there is an algorithm you guys have or something by which we can, because we have not published that yet. What one can do in order to get this. See, because autocorrelation may be working. I don't know. Anyway, we should not waste time here. So whatever, maybe if you had some thoughts, we could just share it.
Yeah, I have some only raw thoughts. I didn't think very carefully about it, but we can talk.
In MATLAB, there will be correlation.
Yeah, but see, we want to find out the rotation, right? Rotation makes it very complicated. It's an angle we are talking about.
So you can actually, you can actually calibrate. You have the known rotation and you have the known correlation. So you can calibrate that later.
Yeah, but I don't know how much it will rotate, na? See, for that, in the sense that first one, I cannot assume that it should agree with the simulation, right? I have an unknown rotation, which I have to find out. That is the problem, because it makes it it's an angular autocorrelation. It's a theta phi thing. It's pretty complicated. What we did here is basically just minimizing that, the RGB counts and drawing a best fit, and that became like a line. And then you sort of find it out and you see a rotation. But that makes the error pretty large. 30% is pretty large. I mean, some of these we have almost of that also. We have some less also, but depends on the picture itself. I mean, initial image. Okay, yeah. Any other things or else? Yeah, thanks. Great.
Okay, thank you, Professor, for the wonderful talk. We will now move to our last speaker of this session, Professor Shiva Ramakrishnan. Okay, I think Professor is here. So, Professor Shiva Ramakrishnan is an currently associate professor of physics at IIT Madras. He did his PhD from in physics from University of Heidelberg and Max Planck Institute for Nuclear Physics, Germany in 2011. After his PhD, he returned to India and served as research engineer at IBM Semiconductor Research and Development Center, Bangalore, for 2 years. From November 2022 to 2013 to July 2014, he was appointed as postdoctoral scientist at TIFR Hyderabad and then joined IIT Madras as an assistant professor in July 2014. He has received many awards in his career. In 2012, he was selected into the elite group of young researchers for the Lindau Nobel Laureate Meet. He was also nominated as head of Max Planck Partner Group in 2017. Recently, he has served as guest editor of European Physical Journal Special Topics. Today, he will be talking on photonics in the UV multi-electron spectroscopy to probe weakly bound quantum aggregate system, that is multi-electron dynamics. I invite Professor Shiva Ramakrishnan to present his talk. Hello. Professor Shiva Ramakrishnan, are you there? We can't hear you. Hello.
He is there. He was actually. Shiva, we can see you, but we can't hear you.
Hi, Sushil. Can you hear me?
Yeah, now we can.
Yeah.
Okay, then I'll go without these headphones. It should be fine. Yeah. Thank you for this very kind invitation and introduction. Is my screen also visible?
Visible. Visible.
I'm in presentation mode. Can you see the presentation?
Yeah, we can see the presentation.
Okay, wonderful. So thank you so much, and it's indeed a pleasure to join these student conferences. I find them far more educative than some and even idea spurring than many of these so-called other professional conferences, if you wish. And so it's a great pleasure to present a talk on in this conference whose refractive index will be very different from the others, if I may say so in the language of photonics. So I just wanted to flash this slide about more our campus than anything else, and I look forward to also students coming down to IITM and Chennai, and we can do a lot of nice things, not just on campus looking at the deer, but also the nice beach, which is there in Mumbai, for example, but it's much more sandy and amenable to other stuff in Chennai. And in this talk, I'm going to talk about photonics in an extremely different regime. So please bear with me, and this will probably be like looks like this will be the only talk on this kind of stuff, which is also nice because it adds some variety to the spectrum of talks in this very interesting conference. I'm again not able to attend all the talks as I would have liked to because I'm traveling to conduct the GATE exam, which is also important in these very testing times. In this talk, the work that is done is largely done with synchrotron light sources, unlike tabletop light sources. There is one impressive synchrotron in India, but that's largely dedicated to hard X-rays and X-ray scattering and sort of I would call materials-driven research to do this kind of stuff that we do with atoms, molecules, and and things in the photonics in the extreme ultraviolet domain. We need to travel to at least, to Italy or Germany, where we have appropriate synchrotrons, and therefore we have a healthy collaboration with not just our Indian peers in TFR Hyderabad and in IIT Hyderabad, but also in Trieste in Italy, and in other parts of Europe, Germany and Denmark. So it's really a sort of multi-way collaboration which comes through very coherently, and we address the same kind of problems. So in all of the talks, at least I could look through, nobody ionized an atom or a molecule, but in this talk we'll begin with that. So there is a bit of destructive stuff going on in this talk, because when I say EUV radiation, EUV is typically even below vacuum ultraviolet, right? So this would be 100 nanometers and below is extreme ultraviolet. And the most difficult atom to ionize in the periodic table is helium, whose ionization energy is 25, approximately 25 electron volts, but it's 24.6, it is 24.56 something, measured to extraordinary accuracy. Actually, that's one of the cool things about atomic physics, that you keep pushing the limits of precision, and we are going to talk about atoms and stuff like that. And I'm going to hopefully try and convince you that even this 2 electron atom with one, even if you consider the nucleus to be a point charge and nothing else, right? Even this 2 electron atom is a fertile playground for light matter interaction. So we heard some fascinating talks about tweezers. Yesterday we heard about, at least the parts that I could join, femtosecond lasers, and earlier also giving a spin to optics, if you wish, both yesterday and today. And I'm not sure when Professor Pawan talks, but that will also be fascinating. But then in one sense, if you see, there's a lot of spin in AMO science, and this talk will be a lot about the atom side, and photons will be playing an important but foundational role. So if I come with a beam of 25 eV photons, and that's incident on a helium atom with just 2 electrons, of course the photon will get absorbed with a certain probability, and this throws the electron from the bound to the continuum state. And elementary atomic physics tells you that the electron which is in the s orbital in the atom absorbs a photon with an angular momentum of 1 unit, and it must make a transition to a p state. Even if it's it goes from a bound to a continuum state, the continuum state should have this double p wave character, right? This is just warming up with the basics of our physics. So this is one nice thing, but then research doesn't end there. I want to progressively increase the complexity of the system. Okay, my animation is playing a bit of a havoc. So, okay, let me just go down to this one. Yeah, now it should be fine. Okay, now I've switched the photon energy deliberately a little bit higher. It is 63.8 eV. Why we choose this will become obvious in a later part of this talk, but just hold on to that 64 eV. I knock one electron out, but I want to make life a little more complicated. So what I will do is I will add a partner helium atom to this somewhere, and how we do that in experiment will also become quite clear. And as I said, the s electron becomes a p electron in the continuum. Then the electron is in the continuum. I can even push it using electric fields and measure this distribution on a detector, which is what we did in our own experiment. This is just raw data from the experiment and textbook atomic physics, right? So next what I do is I place a neighboring helium atom around it, and these two helium atoms, helium has a very low polarizability, so it forms a van der Waals say dimer. We will see in this talk, we can form large van der Waals collections or aggregates, and that's why I call them quantum-ish aggregates or quantum aggregates. So this helium dimer itself is a fascinating quantum system. Now I will not say anything about the interatomic distance between these two, because that takes us off on a slightly different track. But then whatever this distance be, actually the nuclear wave function is very extended up to nanometers, and there was even a question about whether this dimer exists at all. You'll be fascinated to know that the binding energy of this dimer, that is the two neutral heliums sitting together, it's just 100 nano electron volts. right? That could be an error bar in a theoretical calculation, even in a theoretical calculation, right? So it had to be proven by experiment that this indeed exists, and one can look that up. So if I do create such a dimer, which we do in experiments, but not dimers but N-mers, then this electron which is knocked off from the parent helium can be emitted along several different directions, but the conservation of momenta tells me that it should predominantly come out along the direction of the electric field. And if the dimer is so oriented, at least in a random sample, maybe if several of them are oriented like this electron which passes off from the left, the red blob, towards the green, towards the blue, will undergo scattering, and it has by the choice of photon energy and conservation of energy helps me to knock off one more electron from the partner helium atom, and these two come away. Okay, it would be pretty boring just to remove two electrons from an aggregate of two helium atoms, right? But then what if I can measure the angular not angular momentum but angular distribution of these electrons with respect to the bond axis of the helium dimer? Okay, once again, I'm not going to tell you how this is done. That could be a discussion for another day. But if I simply measure all the four charges coming out of this experiment, of course, one can imagine that because after these two electron leaves, because of Coulomb repulsion, these two heliums will come apart along the line that's sort of joining them, along their van der Waals bond, right? So if one measures the moment of all four particles, then one can indeed end up measuring the angular distributions of this system. Now let's look at it from the perspective of energies. We came in with a photon, we photoionized helium, but then I'm doing something slightly different here. So okay, so that I don't confuse you, there are three scenarios. One, there was just a single lone helium atom I was concerned about. A photon comes with 25 eV, ionizes, removes the electron, boring but instructive atomic physics. In the second case, I came in with about 64 eV, a photon with about 64 eV energy. I knocked off an electron, right? And that electron kicked basically up the partner helium atom, from which another electron was removed, and the whole system Coulomb exploded. Okay. Now scenario 3, I crank up the photon energy even more a little bit, so that I can not only throw off one electron in the continuum, but in the remaining helium ion, I can excite the, I have enough energy in the photon to excite this electron from the 1s to the 2s or 2p level, or n equals 1 to the n equals 2 and n equals 2 state, right? Now this is still a dimer. There is a partner helium atom at a distance of about few angstroms, let's say. So then what happens? Then these two guys start talking to each other. Okay, they are twins, so they even can exchange energy, and whole lot of other stuff goes on. But then what can happen, even over a distance of say 10 angstroms, which is a nanometer, which is quite large in the atomic universe, then in their afterlife, they post ionization, they can do a few things. But one of the things that can happen, which is interesting, is that this excited electron de-excites, and an electron is sacrificed from the partner atom in the family, so as to keep the family stable, but only for a short while before they Coulomb explode. So this is another type of process. All I wanted to say is that if I were to take an aggregate of atoms like this, just monoatomic helium, or say other rare gases, or say gold nanoparticles, and go into the EUV domain where I can start exciting electrons and doing things, it would indeed turn out to be a rather intricate, rich but complex society, where things start going on quite nicely, but following the laws of physics and quantum mechanics, right? So this is essentially what we want to study in atomic detail, not just calculate average properties, for example, like refractive index or dielectric constant or conductivity and stuff like that, which happens in solid state physics. But we want to study this in atomic detail, yet increase the size of the system. So this is a little bit of a crazy thing to do, because one must sacrifice or make a trade-off at some point. So let's see how far we can push it. So that's the name of the game in light matter interaction in the extreme ultraviolet, especially in the way that I'm going to describe that we are doing, right? So one can see a whole slew of processes which can happen in this sort of just a simple single photon absorption event where more than one electron can participate in this scenario. I will just draw your attention to just one process which is probably very popular, Auger decay, where I remove a core hole electron in a multi-electron system like neon over here. I knock off a core electron with a photon, and then this core hole is filled in by the by one of the valence electron, and instead of this being a radiative decay process, an electron from the valence shell can go away. So the interesting thing here is that now we have to relinquish this idea of two-body physics post absorption, that there is just one active electron I need to bother about, and the rest is just contributing to a mean field to that, like a Hartree-Fock kind of typical scenario. So in even in elementary processes in EUV, I need to be very careful because processes like Auger decay have an extremely fast rate and can dominate the whole system. Okay, so now let me look at a different sort of perspective, that is go ab initio from grounds up. And here the point is that why do we have motivations to study this? If you look at the strand breakage process in DNA, when say UV light interacts with it, or if one goes higher in altitude and goes to outer space, if at all we do, then we even have higher energy radiation. So DNA breakages are a prominent damaging scenario, and we would like to also understand them. And it was shown that even fairly low energy electrons can break DNA strands, and this is a science paper from 2000, which is probably cited already a couple of thousand times. So this physics is both interesting for physicists and people working in chemistry and biology. What we like to do in our experiments is the following. So we want to form weakly bound aggregates, but in a sense to mimic these weakly bound systems which abound in biology, such as the DNA molecule. The whole DNA setup has a prominent role of hydrogen bonds, for example. So that essentially means larger interatomic distances than covalently bound molecules such as water or carbon dioxide and so on. So we pick and make aggregates of helium atoms in a supersonic jet. This was also referred to by our colleague Professor Debu Goswami yesterday. So these jets are easy, if you wish, even cheap way to make sub Kelvin or millikelvin systems. They have an intrinsic temperature of just about half a Kelvin, and at this temperature, the binding energy of helium to helium bonds is 7 Kelvin. So therefore, the system will remain bound because it naturally cools down. And in the case of helium, we can form a helium cluster. We can even toss in other molecules inside this, and people have done fascinating experiments of doing a rotational spectroscopy of molecules inside trapped inside a helium droplet. I'm going to in this talk present only work with helium-4, that is the bosonic isotope of helium, and we will not touch helium-3. Helium-3 also becomes a superfluid, but has a lambda point of about 0.3 Kelvin, if I'm not wrong, or even smaller perhaps. But helium-4 has a lambda point of 2.1 Kelvin. So if an aggregate is cooled below the lambda point, it should also become superfluid. But we are not going to really, unfortunately, not study superfluidity in this setup at all, but exploit these droplets, which are formed in the following way. We take a nozzle, and metallic nozzle, it has a copper body, but a platinum orifice of about 5 microns is at the edge of this copper body, and helium gas is held at about 100 bar, and it's pushed out through this. So essentially, this creates a sort of fizz, but then this fizz comes out in the form of a cold jet, and this jet has a temperature of about half a Kelvin. This temperature is experimentally measured very accurately for a whole range of conditions, and in this jet, helium atoms cluster themselves, and so a jet with a cluster of helium atoms passes through a chamber. This is the chamber I'd used as a PhD student to work with. The nice thing is, once we have clusters in this jet, I can use this as a host medium which picks up dopant atoms, which I can hold in the vapor form, again inside a vacuum chamber. Either the vapor pressure itself is sufficient to put these atoms into a vapor form, or I can heat this cell, say, resistively to about few hundred degrees, and a whole host of substances can be doped into these helium clusters. So this is going to be the playground on which the rest of the story is set. And we have the same arrangement shown in this figure: helium nozzle, doping chamber, and this doped set of clusters is then made to interact here with a crossed synchrotron beam. Okay, the interesting part about this jet is this jet has very nice beam-like properties, owing to the fact that the momentum spread in the transverse direction is extremely small, unlike an effusive gas, which is what we would see if I just let a bottle of perfume open. This is more like what is close to the nozzle of a deo spray that one may even be using daily. So we take advantage of this and have a sample which is really cold in the laboratory and make it interact with the synchrotron beam. We are going to detect charged particles in this experiment. We are more or less forced to. One can also do absorption spectroscopy, but it would give complementary information. On one side here, we measure ions, and on the other side, we measure electrons, but we have the ability to correlate and tag these two more or less one-to-one. That's the hallmark of this study. The way in which we measure the electrons is to do a sort of imaging. This is another view of our setup, just to get you oriented to what we are doing. So this imaging of electrons is done by a technique called velocity map imaging. I will come to that in a very simple and present that in very simple language. Essentially, what happens is that electrons with different momenta can essentially come out of this interaction. And I have a set of electrostatic lenses here, ring 1 here, ring 2, and this is a position sensitive detector where I have a butterfly wing type of a pattern. So what I do is I project the momentum sphere at this point. You can see a traveling light green animated sphere over here. I mean, it's just a snapshot of that. This is projected onto a 2D detector, and this projection is done carefully using electrostatic lenses so that a certain amount of linearity is maintained in the process, and that's all we really need. Well, but how do I understand this so-called velocity map imaging? If you are a cricket buff, which a lot of Indians are today, and there is also a test match going on right now, what the velocity map imaging spectrometer does is exactly the following. So the batsman over here, he is the target. Okay, a projectile beam comes through, the bowler bowls the ball, right? He nicks the ball and there is a momentum transfer, and this is my position sensitive detector, the slip array. So depending on how much momentum is transferred in this interaction, either the wicket keeper or the first, second, or here it looks like the second slip has caught the ball, so you can determine the momentum transfer in the process, right? Now if the momentum transfer is very low, then it goes to the keeper, and if it is so tiny that it's difficult to catch, it would be at the limit of the resolution of the spectrometer, and here it could also test the limits of resolution of the umpire, right? But we also have other means. In fact, Hawkeye does a correlation measurement, if you really think about it. Okay, so now we use this technique and determine the measure electrons and ions. How do we measure ions? Ions also come out of in this reaction. In my setup, I had a spectrometer which I called a time of flight spectrometer. So if an ion is born at one point due to the interaction, I once again
sorry,
use.
Professor, you have 5 minutes left. Sorry.
Yeah, I will come to the close of the talk rather quickly.
Yes,
So how do I measure ions? Ions essentially are also projected onto one of the sides of this experimental chamber, and the principle that we use in that spectrometer is that the arrival time of the ions is proportional to the square root of the mass by charge in this case, and we are able to measure the helium ions and see a whole slew of helium ions because of the fact that we have helium cluster, we have helium plus, helium dimer plus, helium 3 plus. Water vapor is ubiquitous in all vacuum systems and elsewhere. So we have this. It's accidental that we have lithium. It's for some other reasons. So this is the technique that we use, and I will just go over to in this short presentation, skipping the single electron part, which some of which would be fairly obvious to this audience. I will go to a little short story that I can narrate in about 5 minutes, because this is of, I would say, also historic importance. In a typical helium atom, I can not only measure single electron processes. Single electron processes are like this. I come in with a photon. It is resonant with in its interaction with the atom, and I excite one of the electrons from its initial to the final state. Right? If I sweep the frequency of the photon, then typically this has the atomic line shape is Lorentzian. Right? Okay, if depending on the velocity distribution, it could also turn out to be Gaussian and so on, but it's just this inverted bell-shaped curve, right? But is that the end of the story? Helium is a 2-electron system. Actually, most of the species that we use or interact with are multi-electron systems. So we should also expect processes of this kind. Why not? I come in with a photon, and when after the photon is absorbed, not one but both the electrons in helium get excited. Okay, why not? If this happens, then what happens to the line shape, right? Does it still remain Gaussian? Okay, or does it assume any other line shape? In fact, this was an observation made in the 1960s by Maiden and Codling from astrophysical spectra, that the line shape is not Gaussian at all. It has this strange dip and peak. It's the typical Fano profile. As of today, Fano profiles are in every field. There are Fano profiles in photonic systems and whatnot. This was the but they were first discovered in an atomic astrophysical concept, and this strange shape was actually explained away by Fano and his PhD student Cooper in this very famous physical review latest paper. Just imagine how many citations this would be having by now. And people then discovered a whole series of Fano lines. I mean, you can imagine that the two electrons needn't occupy the same level. You could throw in one of the electrons at the n equals 2 state, n equals 2, l equals 0, that's 2s, and the other one can keep climbing a ladder, which would then be called a Rydberg series, and so on. This is one such Rydberg series, which begins at 64.4, which also explains to you why we chose a certain photon energy. And then we can, as we increase the energy, these beautiful Fano profiles play out. In fact, I even have a selfie with this, because when we were trying to do this experiment and characterize, there was this thing appearing on the screen, and actually it was at midnight, and it was really a fascinating experience as a PhD student. Okay, but that's probably why we are here doing science, right? Seeing really live stuff. And one can see in some experiments from our collaborators, they use laser pulses actually to see how these Fano profiles evolve in time, and that's another fascinating piece of work. And all of that is possible only because very enthusiastic students who are passionate about optics, master a femtosecond laser, create extreme ultraviolet light pulses from that, and really at the break of midnight, when the world is sleeping, do these kind of nice experiments. I say midnight because this requires extremely high temporal precision in terms of two pulse experiments, and most things switch off only at night when the vibrations are stable enough to sustain nanometer relative displacements in piezo stages, right? So these are nice and interesting. However, we asked a simple question. As of 14, people hadn't addressed the question of what if I put an aggregate of helium atoms and then sweep my laser frequency. Fano lines are interference lines. These are interferences in the spectral domain. Okay, so do they even survive? This was just a very basic question that one should have asked. But of course, technologically, there are limitations. You need a very cold supersonic nozzle to produce helium clusters and so on, which probably less than a dozen groups across the world do. And then you need to put it to a synchrotron and do a whole lot of stuff. The probability keeps decreasing when I do the Bayesian stuff of this after this after this, and so maybe that's why it was left to our to us to test this out. And indeed, the black curve that I show here are the Fano lines measured in the same setup at different conditions when I don't have helium clusters, whereas the red lines are essentially the cluster beam for which we measured the line profile, spectral line profile. And even this simple experiment, so to say, it was just done in one evening, is intriguing enough. We still are asking theorists to help us understand the various properties of how this happens as a function of the size of the helium cluster, which is called a droplet because it's in a superfluid phase. I can change the size by varying the temperature of the nozzle. You can see, in a way, we are trying to get rid of the Fano profiles by doing a lot of things, but the Fano profiles, which are delicate interference signatures, are not going away. They are getting probably fatter in their width, but they still are remaining and challenging us to explain the physics. So if any of you has a smart idea about why this happens, right? If it was a very thermal system and there were a lot of decoherences and all sorts of stuff that averages out. I mean, think of this as doing a double slit experiment on a table and then you start shaking the table in the lab. Will you see fringes? No, right? So exactly the same thing. We are trying to shake this up pretty hard, but these lines are not going away. So there is something interesting going on. We could measure as a function of the size of the cluster the Q parameter, and see the resonance is so robust. It doesn't shift in its position by any more than an electron volt, and it still survives. So this was something fascinating. I thought I should put this up and provoke people in the optics community also to think about it and come up maybe with optical analogs for it. Why not? So what else can you do? You can try and put some fatter atoms on top of this droplet and say the Fano line at least now go away. This is what I had proposed and done in the meantime. But the Fano lines say even if you put heavy enough rubidium atoms attached to the helium droplet, where rubidium has tons of electrons, it's an imposter in the system. Even then, the Fano lines survive on the droplet, right? So this is indeed something which continues to fascinate me. We will continue trying and probing the physics of the system using using photonics and allied techniques. With that, maybe I should just stop here and close this talk by once again thanking our wonderful set of collaborators, PhD students and postdocs, and the organizers of this lively little online conference for having me here. With that, I will stop sharing my screen for the moment and take questions if any.
Thank you, Professor Sivaramakrishnan. That was an informative talk. Any question from the audience? Okay, so Professor Sushil.
Hi, Sushil.
Yeah, hi, sure. Very nice talk. Ravi, when students are not asking, then I will go. Okay, so there's no.
Yeah, I mean, no one has raised his hand, so you can go ahead.
Okay, thanks. Shiva, you should not have switched off the screen because I'm trying to understand one of your plots in the end. Can you please get back your plot?
Yes. I'll just share this. Yeah.
A couple of slides before this, when you showed the evolution of the Fano profile as a function of number of the size of this one, yeah.
Yeah, this one.
Right. So one technical clarification is not this one, the next one, the multiple plots. No,
this one.
This one. Yeah. See, the droplet size is defined in 10 to the power something. How do I interpret that?
Okay, I'm sorry. That is essentially the number of helium atoms in the cluster. So if the interatomic distance in the case of this helium cluster is about 2.3 angstroms, and it's fairly uniform in density distribution. So these would be something like from.
We can't hear you.
Oh, you can't hear me?
Now we can.
Can you hear me?
Yeah.
So this is the number of helium atoms per cluster. Okay, right. And the interatomic distance is about 2 angstroms. So therefore, the size of the helium cluster varies from a few angstroms to here about tens of nanometers.
Okay. So Correct. So now that's nice to know that it's the number of atoms. So when this profile evolves, okay, when this profile evolves, as we can see, how is your community interpreting this evolution? When I saw it for the first time, as you described, there is a bare Fano resonance at some point which is narrow. Okay.
Here.
Yeah, and as the number of helium atoms, or let's say the droplet size increases, that peak isn't morphing into the wider one. It is being overtaken or overwhelmed by another wider Fano resonance, is what I am interpreting this. Is that what you interpret? Or, and the reason I say this
yes.
The narrow peak survives in every plot except the black one.
Yeah, absolutely.
How are you guys interpreting it?
Yeah. So I mean, really sharp eyes, Sushil. I must compliment that, because yes, there are, you can say, even a superposition of two Fano profiles. Well, this is the one from small clusters. Well, the point is that even in a clustered beam, I did not quite explain all the features of it. There is a fair amount of unclustered helium atoms, right? So they should be, I mean, of course, the spectral line is an incoherent sum of all the Fano profiles of individual clusters of different sizes coming together. The narrow sharp feature that we are seeing over here, right? So this has a contribution from the atomic part and from even, say, smaller clusters, and we have this other bump which is essentially coming from the other clusters. Okay, so I mean from the larger cluster. So that's how we interpreted this spectrum, I would say.
Okay, got you. Thank you. Got you. Very clear now. Yeah.
Thank you. As you are running behind the time, so we'll conclude the session here. So thank you, Professor Sivaramakrishnan, for the wonderful talk. So we will take the lunch break here right now. So we'll come back again around 2:20. So after 2:30, we have a keynote speaker, Professor Bhai Sandukdar from Max Planck Institute for Science for the Max Planck Institute for the Science of Light, Germany. So I hope everyone will join. We said this. I am signing off this session. Thank you all.
Thank you, Shiva, if you can hear me.
Thank you again, Sushil. It was nice to be online here with you guys. Cheers.
Hello, Wahid, are you here? I see your name. Hi, Wahid. Can you hear me?
Hi, Sushil. How are you?
Very good, Wahid. It's a great pleasure to see you again. How are you?
Yeah, same here. I'm all right. Still alive, and no, everything's fine. How about yourself? How is it going there?
Yeah, I'm doing fine. Why that statement? I mean, did you go through a COVID illness or something? No, when you said I'm okay and alive.
Oh no, I'm just being a little. I don't know. No, everything has been good. I mean, considering that it was a difficult year, I'm saying everything went well, or so far has gone well.
Right. Yeah. Yeah, same here. Same. We are all doing fine. Fortunately, in our organization, there wasn't a much existence of COVID. So, and our colony, our residential colony happens to be like at the edge of the city, far edge of the city, which under lockdown conditions had really small influx of people. So that really kept the numbers very low. In a way, we were.
But how is it generally in Mumbai?
Few weeks till about 4 to 6 weeks ago, things were bad. Mumbai is a very densely populated city.
Yeah, exactly.
There was the explosion of cases, and I think the only way the administration realized they can manage it if the temporary residents who are the migrants of different parts of the country into Mumbai, they wanted to go back, but the administration was sort of saying that you stay here, don't travel. But eventually, a large fraction went back. So in the hottest spots of the city, the densities came down, and what we learn now from various sero surveys apparently is there's been like 1 in 4 of us actually has been infected, knowingly or unknowingly. 1 in 4 has already been infected, and in the dense locations, perhaps more than that. So it's a mixture of good administration and herd immunity and so on. So for the past, I would say 3 weeks, the curve is flattening with a gentle downward slope. So we are feeling much more relaxed now.
So you have so much infections that is kind of becoming self-immune.
It's probably, yeah. So the dense population has had a herd immunity, local locations of herd immunity already, is what is being sort of conjectured.
Okay, but that means that a lot of people died, or
so the numbers weren't that bad in India, probably because there may be some natural immunity in this region, I presume, but the fatality rate was much smaller than that happened elsewhere in the world. Also, if you look at the population pyramid, so I don't really know the absolute numbers of deaths. I'm only talking in terms of per million. That's how they write the deaths. So if you look at the population pyramid, it's peaking not at 60 plus, right? It's peaking much younger. The number of deaths per million is a very small number.
Yeah. Okay.
And of course, there's this eternal discussion about when a death happens, do people record it as COVID related, or well, COVID doesn't kill itself, right? It kills via some other mechanism. So there's always the question.
But I mean, there's an interesting comparison. If you compare the number of overall deaths in 2020 to 2019, then you can kind of figure out how much was COVID, because
okay. Yeah, right. That's the one.
A country or a city has a pretty reliable statistics every year. So many people die of so many ages or whatever, and then all of a sudden there's a jump, and I think you can attribute all that basically to COVID.
Absolutely, that is yeah. We could look at that, yeah.
Yeah.
But right now it's positive.
No, that's good.
Yeah.
I mean, I remember I had this. There was this conference beginning of March in Delhi, and I was just deciding to go or not to go or whatever, and that was the first few weeks of the pandemic in the world.
Yes.
So I ended up not going, and but then everything shut down. just a week or two later, everything everywhere shut down. So
right. Definitely. So actually, 22nd March was when the government first announced that we will be shutting down, and we had one Sunday of 24 hours closure. It was just a taste of things to come, and then end of March already the lockdown began.
Yeah. Amazing. Okay. Well.
So right now, good thing is, I mean, all students have returned. They had all gone home, and there was no way to return because transport was stopped. But in the last 2-3 months, all our students have come back to work. And starting, I think, just 5 days ago, 1st of February, all the staff members have also been asked to report to work. So that's 100% attendance.
Okay. And a lot of people live on campus, right?
All students live on campus. The research students live on campus. The staff, only a small minority lives on campus. They live outside.
Yeah.
So if you don't have the support staff, the admin staff, it's a crippled way of working. And we lived through that for 2-3 months. But now that they've all started reporting, probably within a month's time, if nothing goes wrong, no other new wave comes, then we should stabilize in a month's time.
Sounds good. So there's this nice picture of your campus.
That is indeed the campus. How do I make this big? Right now I have you.
So where is your lab in this picture?
Okay, so actually you can't see the lab from this angle. You see this straight longish building.
Yeah.
That building ends at that edge. Then the ground level starts, which goes for some similar length. Then in the basement of that ground level is where my first lab would be. And the second lab, which I have, again, is towards before the closer edge of the building. So I don't know. It's not seen in the picture.
But facing the sea or facing away?
No, it's on the other side. So this place you see the square. I don't know. How do I? Okay, there's a squarish thing next to the lawn. That's our canteen. That's where we have lunch.
Very nice.
That's where I came back from. Yeah, so you would definitely love to be here because this whole canteen has glass walls and directly oversees the garden and the sea. It's a very pleasing location. Yeah.
Very nice.
We look forward to your visit to
Yeah. I would like that. So what one sees in the background, is that Mumbai or?
So this, you see the buildings all the way behind. The buildings all the way behind.
Yeah.
Across the sea, that's part of Mumbai.
That is not the city. It's just part of it, right?
It's a small part of it. It's a very small part of it. And there's a couple of buildings close by immediately after the official building. They are the residential buildings within our residential campus. And a few of the white buildings in the right corner, top right, are the neighboring campus. That's the defense colony. So we are sort of cozily encompassed within a defense colony.
Okay.
So how things at Masklank? New building, very fancy new building.
I guess you haven't seen our new building. The building is nice. It actually works. It's now 4.5 years old. So it's still kind of new. And it's almost full now. So we have grown quite a bit. There are lots of research groups now. There are only 4 directors right now, but there are lots of smaller research groups. These are people who come to us after something like a postdoc and before having a permanent position. So they spend 5-6 years to develop their research profile, and they have smaller research groups of 5 to 10 people. So we have, I think, 9 of those right now. So that brings a lot of interesting activities. And then, so we are building a new building for a new center that is supposed to be at the interface between not just our work, but generally physics and medicine.
Oh, okay.
And this building will be about 3 kilometers from our current building on the campus of the university hospital.
Oh, hospital. Okay.
So we're quite excited about that. And they've just started kind of the building process, and it'll be ready in about 3 years.
I see. But that's a Max Planck building or the university?
That's a Max Planck building. It's a Max Planck building, but there will be some university groups that will come into that building. So it's a joint effort between the university and university hospital.
Okay.
And Max Planck.
Nice.
Yeah, so things have kind of stabilized now. I mean, the whole thing is fairly new in Erlangen. Our institute is now 12 years old.
12 years. Okay. You mean the Institute of Science of Light?
Yeah, the official Max Planck Institute has existed only for 12 years.
Oh, okay.
So we were in the, you came to our former building, which was a rental.
Right. I also came to the new building for the nano optics 20 years.
Oh yes, of course you did. Yeah. That was just shortly after you opened. Yeah, that's right. Yeah. So you've seen it, but
it's really beautiful. Yeah. It's actually as good as the one that you see in the picture that is put outside. So normally what you see in the architectural videos and pictures, you learn to expect not to see the same, but it is actually the same thing.
Yeah, I know it's a good building. I mean, what's even more important is that, these buildings where there's a lot of technological infrastructure, there's a big danger that it doesn't work. So a lot of these buildings have all kinds of problems. As you build them and then you debug for 4 years, 5 years, up to 10 years, you're constantly solving problems that, because it's a very complex thing to build. And if you kind of follow the building process, you realize that it's actually a miracle that these buildings get built and work in any way, because there are so many different companies, so many different plannings, and the architect never has everything completely under control. So there are mistakes that just happen.
Okay.
It's like, the guy who puts the electrical cables and the guy who puts the plumbing and the guy who puts the cold air vents and the guy who puts whatever, all of these guys, they run the same kind of tract, and it's millimeter precision of who has how much or whatever, and sometimes their plannings get messed up and then you have to fix it. And there are all kinds of reasons why things could go wrong. So we were very lucky that obviously also after our building, there were some things that were not perfect, but overall it was very manageable. Because, I've heard a lot of stories from people who then moved to a building and then they still couldn't run their lab for a year or two because something was not working, and that would be a disaster if that happens to you. So. Yeah,
I guess the new building, probably based on this experience, the new building will be slightly immune to these issues, isn't it?
Yeah, so that's the thing. You try to learn from that and you try to minimize things, but it's still not obvious, because another technicality that causes problems is that whenever you want to do something, you have to write it, you have to advertise it. the bid,
Mm-hmm.
even at the European level.
Oh.
So then, you might end up working with a company that you don't really know. I mean, most of the time you don't know them, but they have no experience in doing what they're doing. It's just that they promise something and give a good price. And then you never know how it's going to be implemented. So if we could, for example, take exactly the same people who worked on this building, we would go a lot faster, but we're not allowed to do that. You're supposed to advertise it again, and a whole bunch of other people come in. And so in that way, it could be more efficient than it is.
Yeah.
But yeah, it's supposed to be fair to all these companies who want to.
And that too all over Europe, not just Germany. Yeah.
And all over. I think there is a certain price level, which for a building is, it happens immediately, up to a few tens of thousands, starting from a few tens of thousands of euros. It has to be advertised at the European level. So that's. I mean, you might have heard about the crisis with the building of the airport in Berlin.
Not really. I haven't kept track much.
This is now resolved, but they built a new airport in Berlin that was supposed to be ready, I think, maybe 8 years ago. And something like 2 or 3 months before they were supposed to open it, they realized that I think some things were not working. Part of it was the ventilation, I think. And it took them, I think it cost hundreds of millions more and 6-7 years to fix that problem. So there was this airport that was not operational for many, many years.
Oh.
And of course, everyone, like you imagine shops or all kinds of people who were supposed to run their businesses at this airport, they had already planned and they had maybe even stopped their contracts with other places and stuff like that. So it was a big disaster, but it was partly because the company who did it was not competent. Now it's hard. I mean, I haven't followed up on it to know exactly why they were not competent or what happened. But these things happen fairly regularly when you just kind of have to trust some company that says, "I'll do this for you," and then.
Right. So we trust what's on paper, what is promised on paper, and there's no real.
You can then take them to court if it doesn't work.
Okay.
But that process takes a long time because to prove that it was really this person's fault takes several checks and years. We're talking about hundreds of millions of euros deal, right? So, and until you've figured out exactly whose fault it is, you can't fix it. And so it becomes a mess. So legally, everything is in principle okay, but in practice, it could take forever and could become extremely expensive.
Oh, yes, absolutely. Yeah.
So,
I wonder if private organizations also go through that, like private universities perhaps don't go through the.
They don't. I think there are some regulations, but they're a lot freer. They're a lot freer, I think.
So we also being public funded, all purchases go to the same mode. So have similar experiences with a lot of things.
Yeah. So, I mean, the problem is everyone is worried about corruption. So the moment you can kind of just give a job to a certain company, everyone is then worried that you're giving it to your cousin.
Okay.
And of course, it's happened before, but it's still happening. So Yeah. So how is science? How is life?
Yeah, so things have picked up. So I wonder if you remember, I told you last time we met in Goa that we are making a shift to quantum optics. I mean, more quantum. And it got delayed because of the last year, but things have picked up quite in a promising way. So we are now able to make NV sources of our own. Okay, we are working towards the single photon level, and it will happen sooner or later. We are now able to have entanglement using different crystals like PPKTP, BBO, and we will now be using that for transport in disorder systems. So,
okay. Good. So how many other groups are working on related topics?
Well, TIFR is a very smallish, the Mumbai campus, we are a smallish organization. So there's one group which does optics and photonics and works on, like one of the ways is fabricating for quantum sources and all using nanofabrication. We don't really have and it's not a full-time profession also of the other group. So we don't have a declared quantum photonics or quantum technologies group, except in superconducting qubits. So there's one group which does superconducting qubits as a profession for a while now. And a group which does nano electronics, so graphene and that type of work, which has now started focusing again on quantum technologies.
Okay, that's good.
I think the thrust is because clearly the full world is shifting largely towards quantum, and also the Indian government has declared a big pot of gold for quantum funding. So in Indian rupees, they have announced 8,000 crores. That is what? 8 into 10 to the power 3 into 10 to the power 8, I think. 10 to the power 8 into 10 to the power 11 rupees, which is 1 into 10 to the power 10 euro. 10 to the power 10 euro over 5 years distributed in the country.
Wow. That's, okay.
We really hope we hope to have some part of that pie.
Yeah, that's a little bit of a trend that is happening everywhere. It's been very good for the field, but hopefully something good will also come out of it.
Even actual quantum tools, right? Actual quantum.
Or something interesting, even if it's not a quantum computer, some interesting discoveries or interesting devices or achievements or something. So are there material people at your institute?
Yes, we have a department of condensed matter and materials science. So there is some materials science component. Again, it's thinning down because that was the traditional approach. But yeah, we do have people who do some amount of materials science. Magnetism was one strong forte. So our institute has gone through this wave of retirement in the last 5 years. In fact, it's still ongoing. An entire generation sort of superannuates and moves out. So incoming are not exactly the traditional names don't apply. So, for example, my department is atomic and nuclear physics, but we are already several of us doing photonics, optics, and
So that's just the natural kind of evolution of these fields. I'm gonna. We have a few minutes, right? I'm gonna try to grab a cup of coffee. Be back. It starts in officially six minutes or something, right? Or
right. Absolutely, you're right. Yeah.
Okay.
Thanks.
Hello, Professor. How are you? Oh, I'm not able to.
Sorry, I was muted.
Yeah. How are you, Professor? I'm actually a postdoc under Professor Sushil. Yeah.
Good to meet you.
Yeah, nice meeting you, Professor.
So that was Pawan, my postdoc, and the one on camera right now is Krishna. He's a student.
Hi, Krishna.
And there are other group members who are right now with their videos off. So Pawan, are you managing this session?
Yeah, I'll be chairing this session.
Okay,
so we'll start now. I think it's nearly a minute before the talk starts.
Hi, Wahid.
Hi, how are you?
I'm good. I'm good. I'm good. Good to see you and looking forward to your talk.
Thank you. Thank you.
Hello, everyone. Welcome to the post-lunch session of the penultimate day of the SCAO conference. So this session basically allowed two talks. The first one by Professor K. Wahid. So let me give a brief introduction to him. Professor Wahid pioneers in the field of nano-optics, which merges various methods and research areas to investigate fundamental issues in the interaction between light and matter at the nanoscale level. Having done his BS in physics from University of California, Professor Wahid went on to pursue his PhD at the Yale University in 1993. After a postdoctoral stay at the École Normale Supérieure in Paris, he then went on to University of Constance in Germany, where he started a new line of research to combine single molecule spectroscopy, scanning probe microscopy, and quantum optics. In 2001, he accepted a chair at the Laboratory of Physical Chemistry at ETH Zurich, Switzerland. In 2011, he became a director at the newly established Max Planck Institute for Science and Light in Erlangen and Alexander von Humboldt Professor at the University of Erlangen, Nuremberg in Germany. Professor Wahid is a founder of the new Max Planck Center for Physics and Medicine, which is a center for joint research that aims to address questions in fundamental medical research with physical and mathematical methods. His talk today, entitled "When Nanophysics Meets Fundamental Medical Research Today," would enlighten us to understand the physics and the advances that have been made behind light-matter interaction. I now welcome Professor Wahid to give his talk. And Professor Wahid, you can now share your screen. Yeah, it's visible, Professor. We can now start the talk.
Thank you very much, Pawan, for the introduction. And of course, thanks to the organizers and the student chapter for this opportunity to tell you about our work. It's a great honor to be able to talk to you today. I've decided to kind of focus a little more in my talk. So I'm gonna talk only about the quantum optics part of the work that we do. Let me, before I get on with the science, tell you where we are. I think you all kind of know where Germany is located within Europe, but where Erlangen is might not be completely clear to you. So in Germany, you know, cities like Frankfurt and Munich and Berlin, and Erlangen is about 2-hour drive from Frankfurt or from Munich. And it's a town of about 110,000 inhabitants, and it's known for a lot of global industries like Siemens and Adidas and Puma. So these are companies that you probably have come across one way or the other. There is a big university of about 35,000 students in Erlangen, and but probably the most important part of Erlangen is our building, or our institute, which is only about 12 years old now. We have, in fact, just initiated a new effort together with the university and the university hospital to build a new building and establish a new center at the interface between physics and medicine. So we're excited about that. This new building will be ready in about 3 years' time. So in my own group, we have two different kind of directions of research. One is nano quantum optics, and these are the people who are working in that area right now. So the top row, Stefan Götzinger, Tobias Utikal, and Jan Renger, they are permanent staff, and then we have postdoctoral fellows, and the bottom row are PhD students. So you see that we're quite international. We also have a big effort now, as of the past few years, in the area of nano biophotonics, where we try to use our skills that we've developed over the years in laser spectroscopy and quantum optics to biophysical and medical questions. Again, the top row are the people who have permanent positions, and we have postdocs and PhD students. I'm not going to talk about this part today, just because the talk is fairly short and I want to be able to go into a little more depth. So I'll start the talk today with maybe a little bit of analogy, or giving you motivation of where some of these ideas might be going, or what some of the motivations would be for the work that we're doing. So signal processing is something that you usually do using electronics. And you could have a simple circuit that consists of major building elements like transistors and capacitors and resistors and such. But you, of course, you also have a power supply, so you need a source, and you have wires that connect all these things. So, and this kind of circuit has been miniaturized over the years, more and more, and now the hope is that it would be miniaturized all the way to the limit where quantum effects become important, even in microelectronics, and possibly even doing quantum computation. Now, if you want to do the same thing using optics, this is a dream that in fact has been around for more than 50 years. Shortly after the invention of lasers, people started to dream about integrated photonics. But still, if you want to do optics, the building elements or the basic optical elements are quite bulky. So if you look in your catalog, things like let me get my laser pointer. Things like a piece of prism or lens that is a millimeter or so might be called micro-optics, but in fact, it's still huge compared to the type of electronic counterparts that would be only hundreds of nanometers large. So a source of light would be something like a diode laser. It's small, but still quite large on the scale of things. And of course, when you're doing optics, you also have to somehow talk about wiring. So connecting different optical elements, if you do it using free space, that's very bulky and takes a lot of space. So there's been a lot of attention given to miniaturization and, for example, making waveguides and putting things on a chip and all of that. But if you want to miniaturize optics, you can imagine that you can go all the way to the nanometer scale, and there you sooner or later are going to be dealing with the fundamental kind of building blocks, which would be photons, so light particles, and things like molecules and atoms, which would be the material particles. So this is the level where we are interested, or have been interested for the past 20 years, to perform our experiments. So really trying to tame light so that you can control it at the single photon level, and tame matter in a way that you can control it at the single molecule level. And then, of course, you want to then put them together and build this up into possibly a device, but already the realization of this type of interaction, like a single photon and a single molecule in the lab, is something that is easy to write down on a piece of paper, but not so easy to do efficiently in the lab. So this is what we have worried about for a good number of years in the lab. And I'm going to give you a quick kind of overview of where we are. Now, I told you that you can, you want to go down to the individual material particles. You can do that with different types of materials. In our lab, we typically work with dye molecules. I'll tell you a lot about that in a few minutes. But everything that I tell you, almost, you can do also with semiconductor quantum dots or with color centers or defects and things like diamond or silicon carbide or any material that you can think of where you can get color centers or rare earth ions in crystals. Okay, so again, if you get to that level, there has applications in quantum technologies, but it also has very interesting applications in biotechnology. And I'm not going to talk about this so much today, but this is a very interesting field because there are interesting issues to address at the fundamental level, but you also very quickly find yourself at a point where technology becomes appealing. Okay, so at the fundamental level, when you talk about coupling a photon to a two-level system, in your quantum mechanics course or quantum optics course, we typically write a Hamiltonian that is reduced to something like E dot D, where the E is the electric field of light, and D is the transition dipole moment of the atom or material particle that we're dealing with. So that's the standard kind of approach that you have. I want to emphasize an alternative approach based on the scattering cross-section, which is a particularly intuitive way of thinking about things. So if you now think that you have light that is impinging on some particle, you can think of this as a classical particle or a quantum particle. This light would be possibly scattered or absorbed. And you can assign a cross-section to this process in the way that is defined here. That is, you say that a certain power is associated with the interaction, and this power would be written as the incident power P0 times some cross-section, which has unit area, divided by the area of the incident light. So this is a very elementary way of describing this interaction. We don't know anything about this cross-section yet, but you can always write this. Now, if you look at this in more detail, then you see that, okay, if I go back here, the light that is scattered, if I have something like a two-level system and a dipole or transition, the light that is scattered is going to have a dipole or radiation pattern. And the light that is incoming, I can write maybe as plane wave. So what you actually get on the detector in transmission can be written as the superposition of the incident field and the field that is scattered by this dipole. And if you write this down, then you get the individual intensities, but you also get a cross term that has to do with the interference of these two. So this is a very general form. Again, you can write that any time that you're interfering two different waves. You can show now that, in fact, the amount of light that you get in transmission in the forward plane, that is, if you put your dipole at the center, at the origin, and your light is coming from the left side, then you can calculate how much power is transmitted on the right side of this plane. And you can show that that power can go all the way to 0 because you can find a situation where the incoming beam and the beam that is, and the light that is scattered interfere completely destructively. Now this happens if the two fields have the same wavefronts so that the interference can be 100%, or let's say this is a required condition. And there you can then see that in order for that to happen, the incoming beam would have to be put in a dipolar mode. So not a plane wave, but a dipolar mode. If you do that, then you can show that on the resonance of the dipolar oscillation, you can extinguish this light in transmission with 100% efficiency. If you don't have a dipolar wave, but you have a focused plane wave, you can still extinguish this light, this beam, very efficiently, up to 80–85%. Now, this is a very fundamental, very basic experiment that you could do, and you wonder whether this experiment has been done before. Or let's say we did about 15–20 years ago, we were wondering about this question. Because if you look at this, then you see that this is actually a very efficient process. Another way of looking at the same problem is that, and this is more accessible in the textbooks because the argument that I'm giving you here is actually something that we calculated in 2008, but this argument has been around in textbooks for a much longer time. And this is, again, the cross-section argument, that you can find the cross-section of a two-level system to be 3 lambda squared divided by 2 pi, if lambda is the transition wavelength. And you can find that in your standard textbook, for example, the book by Rodney Loudon. Now, the point is that this cross-section is actually quite large. Lambda is a few hundred nanometers, which means that the cross-section is also a few hundred nanometers. More importantly, you can, let me just jump over this. Okay, I messed up my logic of introduction a little bit. We will come back to that a little later. The cross-section here is quite large in the sense that you can actually focus your light down to this level and have a very efficient interaction. That is, your sigma over A could reach 1 almost, because you can focus light down to something of the order of lambda squared. Now, there is one caveat here that this cross-section is for the ideal two-level system. But if you look also in your textbook, then you see that you have to worry about a factor that has to do with the ratio of the spontaneous emission rate and the overall homogeneous broadening. Namely, the moment you your emitter is coupled to a bath, for example, of phonons, then you get all kinds of other decay channels for the excited state. For example, you might have a non-radiative decay channel, or you might have a lot of dephasing. All of this makes this ratio small, and in fact, it turns out that at room temperature, this ratio is something like 100,000 times smaller than you would want it, just because there is a lot of dephasing and coupling to phonons at room temperature. Okay, Now, if you want to use organic molecules or any type of solid state emitter as a quantum emitter, then you would be limited at room temperature because your dipole is not going to oscillate nicely. It's going to be constantly dephased. So there is a problem of working at room temperature. Now, you probably have heard a lot of talks in different contexts. People look at things. Sorry, I think the microphone's turned off.
I guess Jeevan needs to switch off the audio.
Sorry for the interruption, Professor. You can.
No problem. Okay, so you know that single molecules can be detected, and this is the type of thing that you might know from lots of talks where fluorescence microscopy goes all the way down to the single molecule level. The type of dye molecule that is used in typical fluorescence microscopy would be, for example, of the rhodamin family, things that might look like that. Now, these molecules, you probably also know, they bleach a lot and they blink a lot, and generally one doesn't think about them as good quantum emitters, and they really aren't at room temperature. We use a particular class of molecules that are referred to as polycyclic aromatic molecules or hydrocarbons. And if you want, you can think of this as a tiny sheet of graphene that has been carefully cut and then passivated with hydrogen around it. And if you cut different shapes, you get different transition wavelengths. There are several reasons why these molecules actually end up being extremely efficient emitters of light and extremely photostable, at least when you go down to cryogenic temperature, to liquid helium temperatures. Now, the energy scheme of a molecule like that is like expected from a dye molecule. That is, you have a ground state, electronic ground state, electronic excited state. The typical lifetime is of the order of nanoseconds, like almost all the other optical emitters that you would know. Of course, because you have a molecule, you have lots of nuclei, you have vibrational degrees of freedom. And and that means that from the excited state, you have lots of different emission channels that would give you redshifted or Stokes-shifted fluorescence. And typically, that's how you detect single molecules, namely, you only collect the fluorescence light and block the excitation light. Now, when you put these molecules in a matrix, the energy levels become very broad because at room temperature or even at low temperature, these vibrational levels are very short-lived because they couple to the matrix. And that means that the channel that involves a decay of the excited state via these vibrational levels becomes incoherent because these states are coupled to the phonon bath. This is a very interesting system, and it's a workhorse that has been, but the workhorse has been around now for more than 30 years, since the pioneering works of W.E. Myrna and Michel Louis. In the next slide, I can show you a video where you see how these individual molecules are excited as you scan the frequency of your laser beam. So you see that this is a crystal of anthracene, and inside you have this molecule DBT. And as the laser frequency gets scanned, different molecules light up at different places. The reason for it is that the individual molecules in this crystal now see slightly different local environments, so that there is an inhomogeneous distribution of the resonance frequencies. So although all these molecules are identical, their local environments are not, and therefore there is a little small amount of detuning among these different molecules. But that detuning is the thing that gives you spectral access to individual molecules. So you can do spectroscopy and detect individual molecules by just looking at their spectral line. But of course, you also have access to the image of the whole thing so that you know exactly where each molecule is popping up in your crystal and at what frequency. So that's the workhorse of the system that we have. So this is the slide that I wanted to show actually earlier that shows that, you know, if you have light that you confine to a certain area A, and your sigma is given by lambda squared by 2 type of thing, then all you have to do is you have to focus light down to something of the order of lambda divided by 2. And this is something that you can do actually using a very good microscope objective. Focusing light down to the diffraction limit is not a problem in a typical microscope at room temperature, but there you use a very high quality microscope objective that kind of looks like this. But you can't put this in a cryostat because it's too complicated and it breaks very easily. So to work in the cryostat, you have to make your own lens, but that's fairly simple to do. You take a half ball lens as a solid immersion lens, and then use a simple aspheric lens. And together with that, you have something like a microscope objective that lets you focus down to the diffraction limit. So this is what we've done over the years, and these are a number of works that we've published basically using this principle, which is all kind of summarized in the right figure here, namely that if you scan the frequency of your laser across the resonance of one molecule and look in transmission after focusing your incoming beam onto the molecule, then you see that when you're resonant with the molecule, you get a shadow that is as strong as something like 10-20%. Okay. A 10-20% shadow from one single molecule is quite impressive. But in fact, I told you that you should expect even 100% shadow. And the reason that it's not 100% has to do with the fact that this ratio here, gamma 0 divided by gamma, for a molecule ends up not being 1. Because our molecule has these other levels. And so you don't have a closed transition between the ground state and excited state that makes it a 2-level system, but you have losses via these channels. So we call that something like a branching ratio, alpha. But for our molecules, alpha happens to be of the order of 30% or 50%. So fairly large, but not 1. If you want to do quantum optics, and you want to use, for example, your molecule as an element in some kind of an integrated circuit, then a loss of 50% is quite large, although for fundamental experiments, it's not a problem. So the question is, how do you get around that loss? You can do that by enhancing this transition. So you can make this main transition that you have so much faster that the amount of the probability of light going by the other channel becomes negligible compared to the amount of light that goes down here. And of course, you can enhance that transition by putting your molecule now in a microcavity. The physics of microcavity is well established, and again, usually done using the Jaynes-Cummings model and all of that. But I'm going to explain that to you using a simple concept of cross-section. So if you bring your photon and put it into the cavity, of course, you know that your photon goes back and forth many times. And that many times is given by something like the finesse of the cavity divided by pi. Now imagine that the photon is going by your atom every time that it goes back and forth. And every time it goes by, it has a certain probability of interacting with it, which is given by sigma divided by A. Now, the A is the mode area of this cavity. So the overall figure of merit that you have for the enhancement that you get from the cavity is given by the enhancement, which is a factor of finesse, but you lose, if you want, by the fact that the mode area is typically larger than the diffraction limit that we had before. So if you were to write this factor figure of merit that we have here, you can show that that's proportional to Q over V, which is the typical figure of merit that you know from something like the Purcell factor or cavity quantum electrodynamics type of treatments. You can rewrite Q over V also in terms of the cooperativity that you might find in the literature, which tells you something about the relation between the, this shouldn't be cavity loss rate, this is the coupling rate. Kappa is the cavity loss rate and gamma is the emitter decay rate. All right, of course, what you want to do ideally is you want to have this figure of merit as large as possible. You can do that by improving the Q of your cavity, but you can also do that by reducing the size of the cavity. And reducing the size of the cavity, if you want, is a little smarter, but a little tougher. Because if you go to very small mode volumes, then you can manage to get a large enhancement factor, even with a moderate or with lower Qs. Now, lower Qs are convenient because higher Qs are difficult to work with because you end up having very narrow resonances, and especially if you're working the cryostat, it becomes challenging to stabilize your cavity. So we have made sure that we can get very small mode volumes, and to get a small mode volume, you want to have mirrors that have a very large radius of curvature, or a small radius of curvature, very large curvature. We've realized that in different ways. For example, we've done focused ion beam milling of mirrors at the end of a cantilever tip or at the end of a fiber tip. Either way, you can make, using focused ion beam milling, you can choose to have very small radius of curvature. Then you take those mirrors and send them to a company to be coated with dielectrics in a way that you get a Bragg reflector, and you get to very high reflectivity. So this is a technology that we've established, but there are also a handful of other groups in the world that are pursuing this approach of making microcavities. So here's a quick view of milling a mirror. So using focused ion beam milling, you can choose the dose and the time and the amount of material that you send, and so that you can kind of dig this kind of curved mirror. And you can do this in a way that it could be very smooth so that you don't have scattering losses. All right, so when we put this together, and of course the setup is somewhat complicated because you need to make a high Q cavity in the cryostat, and you need to be able to move the various parts of the cavity and the sample so that you can get the optimal, adjust for the optimal coupling. But if you do that, you manage to get a resonance that looks like this when the cavity is empty, that is, you haven't coupled the molecule yet. And now if you couple one of the molecules that you have in your sample, you get a resonance that looks completely different. Now, on resonance here, you see that the cavity resonance transmission has been blocked by 99%. So all the light is going back, and in reflection, you find the complementary picture. What this is telling you is that one single molecule was enough to tune the cavity completely from resonance, or let's say the industrial refraction of one molecule was sufficient to be able to do that. Because we have an open cavity, we can look at the same molecule with and without the cavity, and here you see that the resonance of the molecule is of the order of 40 megahertz if it's not coupled to a cavity, and it becomes 600 megahertz or so when it is coupled to a cavity. So you really see with your own eye a large Purcell factor. That is, you've made spontaneous emission a lot faster, and therefore the line a lot broader. Okay, so by doing that, we've shown that we've turned this complicated multi-level system into essentially a two-level system as far as its interaction with light is concerned. So before I told you that we couldn't get a dip that was 100% because of these other transitions, and now I showed you a dip that was essentially 100%. So we've essentially done something like this. Now we've done something similar also using not a cavity, but a plasmonic particle. So you know that a plasmonic particle also has a resonance. So this resonance could be seen as something like a resonance of the cavity. There are some differences. One is that the plasmon resonance is usually much, much broader than the resonance of the cavity. But also there are losses involved in a plasmonic particle. So there are some applications that benefit from plasmonics, and there are some applications for which plasmonics are really not that good, and you should stick to your dielectric systems. Anyhow, so what we have here, I want to flash a recent work that tells you what happens if you send light onto a molecule that is coupled to a plasmonic particle or antenna. And the physics of antenna and the physics of cavity are quite equivalent. So instead of looking at light that is transmitted by a molecule in a cavity, we want to look at light that is transmitted by a molecule coupled to a plasmonic antenna. These plasmonic antennas we can fabricate again using clean room technologies. So these are lots of antennas that we put gold antennas on glass. We space them at a fairly large distance so that we can resolve each one of these in the cryostat, in our microscope. And then we put our molecular crystal on top of this so that you have a random distribution of molecules on this sample. And then we come and, so that's a matrix, we come and illuminate one of these particles, we focus onto it, and we will be talking to several molecules. We don't know exactly which ones necessarily, but we find them in frequency space in the way that I explained in the beginning. So this is now the schematic of the setup. Again, we have a solid immersion lens that lets us focus light very tightly. And right on that solid immersion lens, we have realized these plasmonic particles. And now we want to look in transmission or in reflection, and we can have...
Sorry to interrupt you. We have another 5 minutes.
Yeah.
Yeah.
Thank you. So then we can look in transmission, for example, and when you do that, you can find the resonances of the molecules, and you see that we find a resonance that is very strong and somewhat broader than before. And that indicates that that molecule, among all these other molecules, is actually coupled to the plasmonic antenna. So then we go and explore this molecule a little more and compare that to a molecule that is not coupled to the antenna. And if you do the studies, the bottom line is that you see that the molecule that is not coupled gives us a dip as before. This is a normal extinction dip. But the molecule that is now coupled to the antenna allows more light to go through. Now here, one has to remember that already the plasmonic antenna has attenuated the light. And but now by putting one molecule next to the antenna, the overall attenuation becomes less. Or you could say that the single molecule is partially cloaking this big antenna. But the physics of it is quite similar to the physics of the cavity that I told you, in the sense that light comes in and interferes coherently with the emission from the antenna, which is like the cavity, and the molecule, which is just like before. Okay, so I should quickly wrap up. Let me just not talk about this. I want to say a few words about the new kind of approach or the future of some of these things. And I think the bright future is in connecting many quantum emitters and many photons to each other. But you want to not do that in a totally ensemble kind of uncontrolled way, but you want to make a handful or a certain number of emitters and photons in a controlled way. And the way we do that is, again, we go to on-chip circuitry. So we can make waveguides and resonators, and that way, and put our molecules and couple the light that is in the resonator to these molecules. So this was the beginning of our work. So we just have a waveguide, and we put molecules on it. And some of these molecules happen to be coupling evanescently to the waveguide. So we can, for example, couple via grating structures into this waveguide and another grating structure to couple the light out. And then in the transmitted light, we see extinction dips, as you would expect from the different molecules that along the way have coupled to this waveguide. Notice that these molecules have slightly different resonance frequencies because each one of them sees a slightly different environment. But we can tune these resonances to each other by putting local electric fields, by integrating microelectrodes on the chip. And the idea is that now you can tune different resonances to each other so that 2 or 3 or more controlled number of molecules see the same incoming photon. So with that, I close. I just want to flash some interviews that we did with some of the pioneers of nano-optics, because we're talking about, I figure I'm talking to students, the student chapter. If you're interested in understanding the development of nano-optics and where it came from and where it might be going, I encourage you to go to this site and listen to some of the videos or interviews that we did with some of the pioneers of nano-optics. So from microscopy to quantum optics to plasmonics, there are different 16 different interviews, so you can kind of try to learn about their experiences and how they went through this already starting from 1980s. So with that, I stop here, and there's also a short viewpoint that I wrote. If you're interested in having an overview of nano-optics in the coming years, you can read these 2-3 pages. And with that, I thank you very much for the invitation and for listening. If you have any questions, I'd be happy to talk to you.
Thank you very much, Professor, for the lovely talk. We'll now have a Q&A session for starting with the students and then the faculty. If anyone has a question, you can raise your hand. I can unmute you.
Pawan, you are muted.
Professor Pawan, you can now ask your question.
Yeah. So I too am kind of a student, so I'd love to ask you questions. First of all, very nice talk. Thank you very much, Professor Hind, for a very nice talk. The question related to molecules coupled to the waveguides, what you mentioned about. There is also a possibility of kind of influencing the vibrational modes of the molecule in the vicinity of these waveguides. So when you are looking at these kind of effects in transmission, the vibration structure of the modes may also get influenced. Is that also evident in your measurements, or it's only the eigenstates which are related to the electronic excitations, only those are coupled to the interactions? You may want to just allude to this. That would be nice.
Yeah, so you're right that each molecule also has vibrational degrees of freedom, and you can also try to study those or try to manipulate those. We do have some access to these vibrational states via the Stokes-shifted optical transitions. We have a whole project where we now try to actually characterize vibrational states and learn about the phonon degrees of freedom, generally in the molecule and between the molecule and its matrix. Specifically in the context of the molecule coupling to the waveguide, I can't think of anything interesting that I should consider. The waveguide is broadband, so in principle, you can also talk to the vibrational levels if you couple the right light into the waveguide. You can definitely do that. But I don't expect the waveguide to manipulate or change anything just because these vibrations are quite local in the molecule. The coupling to the waveguide is an evanescent coupling that happens over tens of nanometers. So I don't expect the presence of the waveguide to have any significance for the vibrational modes per se, but you can certainly use the waveguide as a kind of a bus to talk to the vibrational degrees of freedom.
The constraint of using all cryogenic temperatures, is there a possibility that we can push the limits towards higher temperature? Because I understand it actually is very important to cut down the phonon kind of interference. But it would be great also to bring it down to the room temperature, and if we can do something, is there a possibility of that kind?
Yeah, that's a very good and important question. So let me go back to this slide where I talked about the problems of room temperature. So if we look at this cross-section, then we see that there's this lambda squared divided by 2 part, and then there is a part that has to do with this fraction, which is the radiative decay rate divided by, or line width, divided by the total line width. Now, we said that this dephasing at room temperature has to do with the coupling of the electronic transition to the path of phonons. And there is little that we can do about that. They're just there. In theory, you can try to engineer that to reduce that effect, but that is actually extremely hard. And I don't see any easy way to win a big factor right now. But another thing that you can do, which is more accessible, is to enhance gamma R, to enhance it to the point that this ratio goes towards 1. And of course, to do that, you would have to enhance gamma R by something of the order of 10,000 or 100,000 times. Now, that is also not easy, but at least theoretically possible. That is, if you, and that's why we're interested in these plasmonic experiments, that I was talking about. Let me bring my plasmonic experiment. So if I look here, well, in the work that we have done, we have made this right now only something like 5 or 10 times broader or faster. In the best work that we've done that we've achieved a factor of 100. And but again, theory shows that you can go all the way down to something like 10 to the 4 or 10 to the 5. And we're working hard to be able to get there. If you get there, then you can in principle do some coherent operations even at room temperature. Now, you have to keep in mind that you can never get around non-radiative decay rates, and there's a certain quantum efficiency problem, so we're not going to get a 100% performance, but we can, let's say, raise the temperature. You don't have to go to cryogenic temperature, to liquid helium temperature. Maybe you can manage to work at liquid nitrogen temperature. And anywhere that you can come. So you might not have to come all the way to room temperature, but work at a slightly more reasonable low temperature. So there is a kind of there's a lot of work to be done, and depending on the application, you might be happy to stop somewhere along the way. Go on.
Okay. Thank you very much.
Can I ask a question?
Please do.
Wahid, very nice, very clear talk as usual. Fantastic. This idea of coupling single molecules inside these cavities of some sort, isn't it? So one of the things that you were mentioning about the phonon, the bath coupling and the dephasing, right? So isn't it? Won't it be interesting that you could have molecules pre-oriented in some way, which would allow for a delocalization of the entire electronic state that is coupled to the cavity, rather than two single molecules? Because what would happen is, if you have a delocalization of the state across multiple molecules, you push your phonons also to lower and lower frequency, means slower time scales, which would allow for a longer, sort of a shorter non-radiative processes, a slower non-radiative processes, and you could account for, you could sort of push your limits of the lifetime.
So that's an interesting thought. I mean, we're definitely working towards. I tried to indicate that a little bit here, where we try to couple several molecules to the same mode.
Right.
And what we're trying to do here is couple several molecules to the same mode of the waveguide or of this type of microresonator.
Yeah.
And so then you would do basically what you're suggesting, and the photon would be delocalized over many molecules.
Right.
And they all see the same thing. And there is a lot of very interesting physics that you could do there.
Yes.
You could, in fact, even go to the nonlinear regime where you would have several photons that are being shared by several molecules. Now, I hadn't thought about winning in the plasmonic context of trying to fight anything by that, but you're right. In principle, if I think very in a simple-minded way that I have something like a super radiant state, where many molecules have collectively gone much shorter lifetime, then I can also fight quenching that way to some extent.
Right.
You're right.
So, but you have to organize them in the right orientations.
Right. So the orientation is not as much of a problem here in this system, at least. their molecules are embedded in a crystal, and because of the crystalline structure, they typically all have the same orientation.
Okay.
So the problem that we have is more that they're all at different resonance frequencies.
Sure.
So to get that collective interaction to be efficient, it'd be helpful for them to have little detuning from each other.
Little detuning, yeah, almost similar. Yeah, cool. Okay, thanks.
So Sushil has a question.
Can I go? Yeah, thanks. Thanks, White. That was really fantastic. I have a question about the cloaking of the metal nanoparticle. So, as I understand, the nanoparticle by itself would reduce the transmitted intensity because of its own scattering, but the molecule kept between the source and the nanoparticle restores the transmitted intensity back. So now the light, in a way, does not see the nanoparticle.
Right.
So the measurement is at the intensity level, or can you comment on the phase profile of the beam after the cloaking has happened? Does it approach the original phase profile, or it's not same? I'm thinking about the.
It should in theory. So we did the theory of this a few years ago, and you can show that it really works. That you can cloak, which means that you get the same phase and the same beam that you put in. So by that token, yes, you really also kind of retrieve you must retrieve the phase. Okay. You retrieve the wavefront, you retrieve the phase, you retrieve all of that.
So it's basically the same cloak as was shown in the microwave, pretty much the same cloak, right?
I don't know which microwave.
The very first cloaking experiment by Schultz and Pendry, that where the copper.
Yeah. So I mean, in that way, it's the same kind of cloaking. I mean, we call that cloaking. You can call that. I mean, this exactly the same thing is also discussed sometimes in the literature under dipole-induced transparency.
Okay.
So cloaking is always a little bit of an issue. The question is, how broadband is your cloaking? This is obviously very narrow band cloaking.
Correct. Yeah. Thank you very much.
Thank you very much. Thank you very much, Professor. It was very informative talk. Anyone having questions can always mail us so that we can mail Professor and we can get back to you with the answer.
Yes, absolutely.
We now go on to the next talk. The next talk titled, Does Holograph Replay Provide a True 3D Image? This talk is given by Professor Kedar. Professor Kedar received his MSc in physics from IIT Kharagpur with highest honors, and then went on to do his PhD in optics from the Institute of Optics, University of Rochester. He also worked as a lead scientist for over 5 years at General Electric Global Research in USA. He currently is an Institute Chair Associate Professor at Department of Physics, IIT Delhi. He additionally serves as an Associate Editor for the Journal of Modern Optics. Prior to joining IIT Delhi, he was also a professor. Research interest spans over a wide range in computational imaging. In recent years, he has been actively engaged in work on quantitative phase imaging, Fourier phase retrieval, computational microscopy, diagnostic MRI imaging, and structured light. We now request Professor Kedar to start his talk. Professor Kedar, you can start your screen share with us.
Yeah, thank you, Pawan. Let me start sharing my screen. I think, do I have access to screen sharing or no?
Yes, sir, you have it. You're actually a co-host.
Do you see my screen?
Yeah, we can see it now. You can go on.
Yeah, so thank you very much for this invitation. And I'm sorry that I have not been able to attend many other talks because we have just started a semester. So what I'm going to talk about today is something that we started thinking about for last 1 year or so. And this really questions, does holography, as we teach or as we understand many times, or as we explain, does it really do true 3D imaging? Okay. Well, this is not how IIT Delhi looks always. It was during the lockdown period. So otherwise, Delhi is never this clean. Let me start with this talk. And so the question is, as a student or also as a teacher, when you're teaching any optics class, what is the most attractive aspect about holography? And it is that it is able to do 3D imaging. Okay. And usually, how do you explain it, or how do most books actually explain this ability to do 3D imaging? Is they say that 3D imaging is possible because we are recording both amplitude and phase on the detector, and so you have all the information, and that is where the name holography comes from. That you have complete information. But the question we want to ask is, does recording of phase information really ensure 3D image recovery, or a true 3D image recovery? Okay, and this is seems like a funny question, but if you probe it a little bit, you find many surprises. To get everybody on the same platform, let us begin with very simple things about holography, and then we will get into this problem. So how you can understand holography is something like this. You have a source of light, and let's suppose you have a 3D object, and this object is going to scatter light, and this viewer is going to see it as an object. Your eyes will focus onto this object. But if you think about an intermediate plane in between, and if you can think that, if this object is not there, but you generate the same tangential E field on this plane, then the viewer here will actually get the same perception of the object. And so here in that perception, the ability of our eyes to focus onto that object is very important. If my eyes focused somewhere here on the intermediate plane, then I will not actually see this object, but we have this natural tendency to focus onto something that is sharp, okay, to get our eyes into sharp focus. And so, how do you actually generate that same E field here? And the way to do that is to record, meaning traditionally is to record an interference pattern. You don't have to do it by interference. You can generate the same field via, let's say, an SLM or things like that. The same effect will happen. But traditionally, how do you teach holography is that, you have a reference beam and you have an object beam, and these interfere and make a hologram. And when you want to replay the hologram, you illuminate by this R star, and then these waves go back and focus onto the object, okay? And this is, however, was how it was done with the film-based holography. But in last 20, 25 years, we no longer use film. And what we have done is to shift to digital holography, where the same interference is actually recorded on a camera. And then you do some numerical processing. So you start with the hologram, with the interference pattern, you recover the field O in this camera plane, and then back propagate this field numerically to the object, and you say that image is formed. Now, my group has been working for last several years on good algorithms, advanced algorithms to get this high resolution, highly accurate phase information in single shot. And there is also, we have done a lot of work in this area. There is a product coming up, which has come up already. We also done some diagnostic work on this, and if people are interested, there is also a TEDx talk last year. But this is not a topic for today here. We were just trying to, but what I want to say is, when I show this as a phase image of cell and claim that this is 3D, it is not exactly 3D, because what I'm showing you is a phase image corresponding to this bright field image of the cell. The height map here tells you something about the optical path difference. And in this sense, it is not really a true 3D. It is just a projection image, okay? But let us go back to our question, that is true 3D really possible? And the question is something like this. that we have a 3D object. So there are a number of voxels, let's say nx times ny times nz. And when you're recording this information into this object field, OXY, that you can recover out of the hologram, you are storing this information onto the nx times ny pixels effectively. So you have gone from 3D to 2D, which is fine because now you have reduced the numbers in which this information is stored. But when we replay this hologram, what we are claiming essentially is that we are taking information in nx times ny pixels of the detector and regenerating nx times ny times nz voxels. And now this is really surprising. And how is this possible? Because we are taking less numbers and generating more numbers. So is this really possible? This seems to be very odd. And this is a classic, some sort of a incomplete data problem that your unknown object was in 3D space and your recorded hologram field, the complex field in the hologram plane is in 2D. And it seems that the replay is just a linear operator, which is a propagator. And how is this possible that it is able to generate more number of numbers? So to probe this a little bit more, what we thought was let us do a simple model. And in fact, let us see what happens typically. So you have, I'm taking a cartoon object, 4 letters A, B, C, D in 4 different planes of this box, and you record a hologram. And then when you replay this object field from this hologram, in fact, when you look back into what is going into this 3D volume, it is no longer like the original object, but it is something like this. What I'm showing here is the field amplitude effectively. And so what happens is, wherever this letter A was there, for example, the field will come, meaning you will have a focused image of A, but before that plane and after that plane, there is also this field. And meaning if you try to look at this numerically, what is getting generated in that box, it is no longer like the original object. And mind you, meaning when we were doing this with our eyes were only meaning with eyes also this whole field was there, but our eyes just concentrated on these 4 letters because that is where the focus is sharp. Okay. But if you try to do this now numerically in the digital holography era, then it's no longer a 3D image and you have something else there. And so it is important to see what is the mathematical nature of this replay field that goes into the box. Okay. And so to that extent, we thought that we'll do a simple model. And the simple model is that, we can neglect the secondary scattering for starters. And what we will say is that the field OXY in this camera plane, which I think we can now recover very accurately out of the interference, I can model this field in this way. So I can take this box, which is between Z1 to Z2, and slice it into many, many slices along this direction. And then what I'm going to do is each of these slices I'm going to propagate to the camera. So that is this, for example, that you have a slice at Z equal to Z prime. So that it's a 2D function, ux prime, y prime at Z prime. And then you have for example, a Fresnel propagator or the angular spectrum propagator, which will, it will take this slice onto the camera. And then we are going to integrate all these slices essentially. Okay, so there is an integral over dz prime as well. And so this is a simple model. It is right now not taking into account any secondary scattering, but that is how mostly holography has been dealt with in practice. Meaning once you go to very highly scattering objects like tissue and things like that, this will not work. But nominally for many objects that are of interest, in fact, if it's a reflection, it's a reflecting surface or something like that, then this is perfectly fine too. So what we thought was we will try to do, so this object field OXY is, so this integral operator we call as A hat, and this acts on the 3D object UXYZ, and it gives you a 2D field in the detector plane. Okay. Now you can use a very simple a scalar product identity, and so what you can say is, let's suppose there is a 2D fields which is O1 and O2. So O1 is generated as A hat U1, and O2 is another field in the detector plane, and then that scalar product is going to be equal to the 3D scalar product in the 3D space. And so this A hat just goes on the other side and it becomes A dagger. And so these two scalar products have to be equal. And so if you try to use this and do some little bit manipulation of integrals, what you find is that A dagger O is actually something like this. And you notice here that it's an integral over, it's a OXY, which is the field in the detector plane or the object field in the detector plane. And then you have this H star there. And if you look at the Fresnel propagator, H star is just a back propagation. And so what we are saying is that what we actually do traditionally in holography, which is the hologram replay or the replay of the object field, is actually not it's not an inverse operator. Obviously, it is a transpose operation. Okay, so what we are actually getting in the usual holography in the original 3D volume is not the true 3D image back, but it's an approximation in some sense to that. And without your eyes having the ability to focus onto sharp objects, this is not going to look like anything like if you look at the box and look at what field is getting generated there, it is not going to look like what was the original object. And so to summarize the first part, basically I'm just going to tell you this, that so we call this operator A, which takes information from 3D to 2D. And then the replay, which is the traditional replay of hologram, is actually not A inverse, but it is more like A transpose. And so, in fact, formally, there will be no inverse because this is a rectangular kind of matrix. And so you cannot have. And the point is, can we actually use this fact that this replay is actually A dagger to get to something what we can call as a true 3D solution, or more like a CAD model like solution to the 3D image reconstruction? Before doing that, I thought that let us go back to Geber's original works and see how he, in fact, this is a article he wrote after he got the Nobel Prize. And there is very interesting thing in there. So in the first line of this article, it says holography, which is sometimes called as the three-dimensional lensless photography. And there is a reference one, which is actually a footnote. And it says that the term three-dimensional is used here to designate an image or process which produced it, which is substantially isomorphic with the original object. So this is a footnote, and it says that it is not really a true 3D image, but it is something that is substantially isomorphic. And so Geber already knew that this is not a true 3D image, but everybody, if you talk about holography, everybody just says that, okay, we are doing 3D imaging, but it's not true. Okay. So what we thought is we can actually formulate this problem. It's an incomplete data problem. So we have to, definitely there will be a number of solutions to this problem because the data number of detector pixels is actually much less than the number of voxels in the 3D volume. And so we have to actually formulate this problem as an optimization problem, because without that, we cannot go to the right solution. Otherwise, there are infinite number of solutions to the problem. And so we kind of pose this problem in this way, that there is a cost function of this 3D field u, which is this object wave minus a hat u, this squared error. So this is like a error term. So you want a recovered object u, which is a 3D object, and that matches with the object wave in the hologram plane. And then on top of it, to constrain, to find the desired solution, you have to put some constraint. And so you can have constraints like sparsity or 3D support and things like that, okay? So you can see here that typically when you design this kind of cost functions, they are actually real and positive valued, but the solution u is what is known, it is actually complex value. And so if you try to follow the standard gradient kind of algorithms that, try to take a functional gradient of this cost function and move in the steepest descent direction, then they will not work, because you will need to think about this as a, since this is a complex valued field, you will need what is known as the Wirtinger or complex derivatives. And I'll just briefly tell you what these things are. But before that, let us see, how this looks like. So if you have this object ABCD, then the real part and imaginary part of this object may look something like this. These are, these are diffracted waves and their real imaginary part. And for the penalty function or the constraint function, we are using, at least for the simple object, we are using a total variation or L1 norm of gradient kind of penalty. So the penalty is actually on a gradient of or at all pixels m of this volume. And so you are actually taking a 3D gradient, taking a magnitude of that, and then summing up all the magnitudes. So for a simple object, this there will be a penalty to have a very high value of this penalty, okay, of this cost function psi. Okay. And operationally, the algorithm is actually just simple. When you do Wirtinger derivative, what you have to do is you have to take a derivative with respect to u star. That is the steepest descent direction. And so a simple form of algorithm can be written like this, that you have so you take your nth guess for the solution and then subtract the functional gradient of the cost function at the nth guess. And this is how you progress to the next guess. And then you can add some other constraints like the support, the 3D support volume and things like that. But in general, this goes in that fashion. And so if you calculate, if you look at the C1, which is the error term, and C2 is something like total variation, then it is very easy to show that the functional gradient of C1 with U star has see here that A dagger again appears. Okay, so what you're doing here is you have an object guess, and then you propagate it forward to the detector. You take this as an error and then do back propagation back to the volume. Okay, so this is the gradient of C1, and the gradient of C2 is this is a well-known standard form, which is some sort of an anisotropic diffusion form, which is a edge-preserving kind of penalty. So total variation is an edge-preserving kind of penalty and encourages sparse objects with sparse gradients. Okay. But if you try to do this, there's something very interesting. You can see the traditional reconstruction. And so the traditional reconstruction, if you look at it, it looks like this, that these waves will come back, they will focus at some point and then again diverge. And so if you look at 4 different planes in this volume, you see that this letter A, B, C, D there. So in one plane, it is focused. In all other planes, it is going to be kind of defocused. But in this new reconstruction, if you try to solve this problem, you see that the A is here, but the other terms are essentially not there. Okay, so here is B in the second plane, but there is nothing here. All right, and so essentially what you have is it's a CAD model like solution that you can get back. Okay. And so this term, total variation, and the way it acts on the solution, it's actually a nonlinear kind of penalty term. And so, in fact, you can never get this kind of solution by physical replay, because in a physical replay, you can never have a situation where the field is, so for example, you take a letter, particular letter B, and it will never so happen that the field is 0 all the way, and suddenly it appears and again the field is nearly 0. Okay, so this kind of thing is not possible by any physical replay process, but it is only possible algorithmically in this fashion. And so in fact, this opens up many interesting questions about what is 3D and what we call 3D in a number of holographic systems. If you're interested, you can read, this paper has been written more like a tutorial way, but you can read all about it in this article, which came out a few months ago. So I would say that holography of all flavors is a classic incomplete data problem. And so the recording of information about 3D does not actually guarantee that true 3D recovery is possible, unless some form of nonlinear processing is involved, or some physical form of nonlinearity is introduced. And so most holograms that you read about, therefore, do not actually provide a true 3D image, but provide a 3D perception relying on ability of our eyes to focus. Okay. And here is something else, which is I recently found that this floating kind of displays, they are also generally trying to fool you, but there is only one display that exists, which is truly floating in some sense, where a femtosecond laser is actually focused into air, it generates plasma, and which is kind of floating in the air, and you can scan with an SLM the position of this spot, and you can make this kind of floating fairies and things like that. Okay, so but again, you notice that if you want to generate, see the IR radiation that is not seen here, so it's only a floating display for the plasma originated light. Otherwise, there is the laser in other places too. But at least you can see that this kind of true 3D floating display is also possible only with some sort of nonlinearity. And the same thing is possible algorithmically also, unless you don't do this kind of any form of linear processing will not allow this actually. And so finally, I generally won't write this much text on the slide, but since we are doing this in remote mode, I thought I'll put it like this. So the first thing as a summary I would like to say is holographic replay, as understood traditionally, does not actually provide a true 3D image. The replay is actually a Hermitian transpose operation corresponding to the hologram formation operation. So the going from 2D to 3D is actually a Hermitian transpose of going from 3D to 2D, at least when you do physical backpropagation of the object wave. And so when examined from this perspective of digital holography, the numerically backpropagated field is only an approximation to the original 3D object. And so the bigger question is, how well can we reconstruct a true 3D image in a way that is like a CAD model of the original object? So first of all, we need to worry about degrees of freedom. So because from going from 3D to 2D, we are reducing the degrees of freedom, and so this is possible for sure to recover if the object is sparse in some sense. So it could be sparse in the voxel domain directly, or it could be sparse in the gradient domain or in some other transform domain, which is, so it is almost like a classic this compressive sensing kind of problem. But it is not just a mathematical problem, because if you make more and more complex objects, then whatever I started with this approximation of neglecting secondary waves will not hold, and we need to revise this operator A, what it means. Okay, and so the method may be still useful, I think, for several practical cases like transparent cells or lenses in metrology. And so there are many systems that are optical today that actually claim 3D by recording something in 2D. And so all these places, I think this kind of formalism will actually help bring out what is true 3D. Okay, we are also on to some experiments on this, but right now I don't have any results. My students have just come back to the campus just a month ago, and we are still kind of getting used to it. But in future sometime, maybe we will try to demonstrate some experiments where definitely this kind of, for example, cells that we have been imaging in microscope, the holographic microscope, they are all 3D objects. And so instead of just getting this projection, getting some tomographic view will be interesting. So thank you very much. I will stop here. I think, I hope I'm right on time.
Thank you very much, Professor, for the informative talk. The floor is now open for questions. Anyone wanting to ask a question can raise a hand so that I can unmute you. Yes, Sandeep, you can ask.
Hello, Professor Kedar.
Yes.
Sandeep here.
Yeah.
So you said that normal gradient descent method will not work to optimize the cost function because it's a complex number.
Yes.
But if you write the complex number in terms of like real number plus imaginary number, then you can have like instead of like n number of variables, we'll have like 2n number of variables. Then can you use the normal gradient descent method or like particle swarming optimization method?
Yes. So then you generally what is seen in these problems is that if you treat real imaginary parts separately, then you have to control them separately, and that is that poses a problem. Having controlling the complex variable directly has a lot of advantages, and so there are many optimization methods today that utilize this Wirtinger derivative kind of concept. so it just gets more tedious, and the control over real and imaginary parts separately is not so easy.
Thank you.
Yes.
Pawan, I'd like to have a go. Yeah. Kedar, thanks. That was a very nice presentation. Kedar, I got thinking about the process of seeing, right? When I see something.
Yes.
It's a projection on two planes perpendicular to my line of sight simultaneously, right?
Yes, yes.
So
yeah.
Yeah, so basically a 3D object, it only becomes 3D because of these two stereographic kind of a projection. And then I'll have to forcibly see around the object to make its entire image, entire 3D structure visible, correct?
Yes, yes. So I'm not talking about that stereo effect here. I'm just talking about just one eye, even with one eye. So if I'm looking at you, I tend to focus on you. You know, I don't try. Meaning there is a light field in between you and me, but I don't focus at some intermediate plane. You know.
So again, I'm sorry to interrupt you. That statement again raises a flag. See, when you look at me, by default you are looking at me stereographically. Am I right?
No, but even with one eye, you know, my eye lens will naturally try to focus onto you. You know, it will not focus onto some intermediate plane. So, you know, so if my eyes focused on some plane in between, I will just get blurred. I will not see it. This is kind of intriguing, but we kind of take it for granted, I think, you know, but it is continuously something is happening when we look at objects.
Okay. So, I mean, what I wanted to, maybe a sub question could also be that, would a theoretical analysis have added value if some sort of stereography is built into it?
Yeah, so now the question is, see the stereography here, it's only meaning it goes towards, you know, how big the detector is actually, you know, so if instead of two different views, I can just have a large detector, and then things will be similar if I want to look around the object and things like that. So that just depends on what is the extent of your object field detection or the numerical aperture of the box with respect to your detector. You know, so that will help solve that kind of issues. Yes.
I see. Thank you very much. Thank you.
But then the nice thing here is that you know, the reason you can get something tomographic is really when you backpropagate, things focus somewhere, and that helps in highlighting those parts when you use sparsity. Actually, you know, so the sparse penalty that we use in this algorithm actually tries to retain that part and gets out. You know, the rest of the part is slowly taken to is made zero, actually, you know, nearly zero.
I see.
Yeah.
Thank you so much.
Any question?
Yeah.
See.
Hello, Sandeep again.
Yes, Sandeep.
Professor, how do you choose the optimization function? Like, is there a way to choose, like, because there may be like multiple optimization function that you can get like a better result for that. So how do you choose it?
You need to have some understanding of, but you know, there are few of them, they have worked pretty good over the years. So in general, you know, the sparsity idea relates to some extent to compressibility of the signal. Okay. And because we know that a lot of images we take today, they're compressed. And so similar transformations actually are useful in reconstruction as well when the data is limited. You know. So there is a literature on that side of signal processing, and people know what kind of transforms are good for sparse representation of natural objects. Okay. So you can also go to wavelet-like basis. There also, you know, the objects are captured very well. So that could be another possibility. Yeah.
Yeah, like in your case, like you have, so suppose if I want to optimize the cost function and I'm using a normal gradient descent method, so normal L2 norm, basically it works fine, right?
It doesn't work because L2 norm solution will be just like, almost like, you know, it will fill all the voxels actually. It will make all voxels non-zero. And so meaning that is what happens. If you try to solve like that, the energy will be spread over the whole 3D box. And it doesn't know that, it's like a most likely kind of solution. And it doesn't know that, what kind of solution you're looking for. So that you have to actually put via the sparse penalty.
Get it. Thanks.
Yeah.
Thank you very much. Any questions? That's it, I think. Thank you very much, Professor, for a very informative
Thank you very much. Yeah.
And this closes our session C of the conference. Before we proceed to session D, we shall have a small tea break and we shall again meet at 4:30. Thank you very much.
Thanks, Kedar.
Yeah.
Bye.
Bye.
Hi.
Hello, Urvashi.
Yeah, hi. Yeah. How are you?
Good, good. So,
Yeah,
how
can
are
you
you?
hear me properly?
Yes, yes.
Yes, because I'm trying a new microphone.
Okay. All clear.
Yeah, because we have a break right now, right? So I was just also hoping to just share screen once and ensure it's fine. Yeah.
Yeah.
How are you doing otherwise?
All good.
Oh, you have to enable my share screen, I think.
I think Sushil is here.
Yeah, hi, Urvashi. I'm here.
Hi. How are you?
Good, good. How are you doing?
I'm doing fine. Yeah.
I need to make you the co-host for a moment.
Okay.
Why is your name on the list? Not here. You are. Okay, 1 second. I think that authority is now.
Yes, yes. Thank you. Yeah.
Give me a moment.
No, you should send it to him. Send it.
Yeah, you are ready there, Urvashi. Thanks. Can you try now?
Yeah. Fine, right? I mean, can you see?
Yes.
It's working, right? Fine.
Yes.
Yeah. Let's stop.
So how's things at RRI?
Yeah, things are okay.
All students are back to the labs at
Sorry?
work.
Can you repeat that, please?
I said all students are back to the labs.
Yeah, well, officially, yes. But then, of course, we are still trying to have like a couple of students in one air-conditioned area type thing to the best of our abilities, but then sometimes not. Yeah, so we've had a few cases a few months ago, but at the moment for the last few months seems, I mean, I don't know, seems slightly okay.
Okay.
But we also have these periodic RT-PCR tests from our municipality. So they come and conduct that in our clinic. And so people are encouraged to take it. Many people do, most people do actually. And so then periodically we ensure that, there's no silent carrier because that is the, yeah. How are things in TIFA?
Yeah, good. Much better than earlier. Actually, our colony and the institute wasn't really badly affected.
Okay.
A lot of credit of that goes to Gopal.
Yeah.
He's on that committee which had this COVID action force, stuff like that. So.
Okay. Yeah, we also have one. I'm not a member of it, but I think it's very important to have people who are more proactive. And yeah, they were thinking of doing a bio bubble and all, but that seems a bit too much. Already too many uncertainties.
Yeah.
This bio bubble thing has been floating, but then I don't think we are all very keen on it. Yeah. You know what that means, right? Like basically, yeah, one lab. So if you just get tested every 2 weeks and then not wear a mask, but
Oh, okay.
So from this week, like we have 100% attendance.
Okay.
So.
Okay, Vikas is.
Gopal, so my volume is at maximum. So am I also audible pretty much? Because as I mentioned, I'm testing out a new system. So is it still perfectly fine? Or should I?
No, you're good.
Because you're, hello, Ashutosh.
Hello, ma'am. Hello, everyone.
Ashutosh also, Ashutosh is the first speaker, right? Yeah. Ashutosh is frozen. Yeah, that is usually Ashutosh from home.
Yeah.
You don't always see him. I mean, connection keeps going and coming.
Yeah, I mean, poor internet connection.
Vikas, are you sharing the session here? Your screen is frozen, Vikas.
Yes.
Okay. Okay, so you can take over.
Okay. Welcome, everyone, to the last session of this conference. This will be co-chaired by Vikas, which is me, and Pawan, who you saw in the previous session. To begin with, we'll have a contributory talk by Ashutosh Singh from Raman Research Institute, Bangalore, who will be talking on revisiting comparison between entanglement measures for 2-qubit pure states. So you can begin.
Yeah. So is my screen visible to you? Hello.
Yes.
Okay. Okay. So good afternoon, everyone. I am Ashutosh Singh, and I'll be talking about comparison between for 2-qubit pure states. This work was done at RI during my PhD in the guidance of Professor Urvashi Sinha and our collaborator, Professor Dipankar Home, and student collaborator, Izaz Ahmed. This is a brief outline of my.
Sorry, Ashutosh, could you please
Moving on to
talk
the-
slowly? Could you please talk a little slowly so that, I mean, there is also some breakage in your voice. So
I see. Okay, sure. So this is the, maybe I'll just turn off my video. Perhaps that will be better. Yeah. So this is the brief outline of my talk. Moving on to the motivation. My screen is frozen. Just 1 minute. Yeah. So non-Maxwellian entangled state, and you are asked the question that to what extent the state is away from the Maxwellian entangled state. Then there are different ways of answering this question. One is that you find the overlap of the given state from the Maxwellian entangled state. And then the other way, that is what we are going to propose, will be that you consider different Maxwellian entangled state, even if they're orthogonal, such as psi plus and psi minus, on the same footing, and then you quantify the amount of entanglement present in a state, and then see that amount of entanglement that a given state has, how less it is compared to the Maxwellian entangled state. And it is in this context we address this question. And this question is important for evaluating the efficacy of the state given Maxwellian entangled state and that of a non-Maxwellian entangled state. Now, it is this question that we examine in this paper for 2-qubit pure entangled state in terms of different entanglement measures such as negativity, log negativity, and entanglement of formation. Although these entanglement measures are very well known and also is being used for a long time, but to what extent they differ in quantifying the amount of entanglement and the deviation has remained an unanswered question. And that is what we are going to explore here. What we report in the end is some intriguing nuances on such a comparison. So to begin with, let us consider a 2-qubit pure state written in Schmidt decomposition form. Psi equal to C0, 0, 0 plus C1, 1, 1, where C0 and C1 are the Schmidt coefficient. Now, if you plot different entanglement measures as a function of the Schmidt coefficient C0, then you get such a graph. So for concurrence, negativity, twice negativity, log negativity, entanglement of formation, and entanglement entropy. What one immediately sees is that concurrence and twice negativity exactly match, entanglement of formation and entanglement entropy exactly match, and log negativity is a distinct measure of it. Entanglement of formation and entanglement entropy match, while negativity, log negativity, and entanglement of formation are three distinct measures of entanglement. And that is what we will use for the further study. So these entanglement measures are defined as given here in the form of the Schmidt coefficient C0 and C1, and these expressions are noted down here. Now let us define the fractional deviations of a given state from Maxwellian entangled state. Suppose there is a non-Maxwellian entangled state whose entanglement value is n, then what we do is we subtract it from the value corresponding to Maxwellian entangled state, which is 0.5 for negativity. So 0.5 minus n gives the deviation, and then we renormalize it with 0.5 so that this deviation parameter is again between 0 to 1. Likewise, we do for log negativity. So maximum value of log negativity is 1, And then for a given non-maximum entanglement state, if it is ln, then the deviation parameter QL is defined by 1 minus ln. And likewise for entanglement of formation. So these three are the deviation parameter defined based on negativity, log negativity, and entanglement of formation. Then we go on to define the absolute difference between these fractional deviation parameters. So delta QNL is defined as absolute difference between QN and QL, and likewise QEL and QNE. And as soon as we plot this as a function of Schmidt coefficient, what we see is that for C0 equal to 0, C0 equal to 1 by root 2, and C0 equal to 1, all these differences vanish. C0 equal to 0 and 1 anyway correspond to the trivial separable state. However, for C0 equal to 1 by root 2, it is maximally entangled state, and then also all the entanglement measures match, and therefore we have zero deviation between them. However, for C0 equal to 0.22 and that for C0 equal to 0.97, we have maximum deviation. And what we see is that QEL gives the maximum deviation of 23.57% for C0 equal to 0.217. The maximum deviation between Q and E is 14.99%, and that between negativity and log negativity is 8.61% for these state parameters. So this is obtained by numerical optimization. Then we go on to preparing these states using the process of SPDC. And what we see here is basically the state preparation part. We have basically a laser and then some optics for correcting the polarization and preparing the input polarization in a diagonal state. And then you have a sandwich type 1 nonlinear crystal. It prepares the entangled state, and then the two photons pass onto the surface of a cone, and you collect them from these and these positions, from diametrically opposite positions of the cone, and then send them through a setup of quantum state tomography. So basically quarter plate, half a plate, and PVS combination is used for projecting the input state onto different bases, and from that you reconstruct the input state. So this is the basic schematic of the QST setup, and then you couple them through single mode fiber into your SPAD detectors and do a coincidence measurement. And basically here band pass filter is used just for the spectral filtering. Likewise, same setup is used here. Lens here is used just to collimate the beam so that you can couple these photons into single mode fiber. Now we compare these experimental results with respect to what we got, from the theoretical estimations, and what we find that we prepare these three states. Their Schmidt coefficient ratios are in the have the value 0.96, 2.03, and 3.1. And what we see that for the state 3, the maximum deviation that we see for QNL is 8.25%, and that for QNA is 13.39%, and that for QEL is 21.64%. Immediately, if we go back and check the values that we got from numerical optimization, what we find is that they're pretty close to the maximum deviation that we found through the numerical optimization. So we were able to verify our results experimentally, and then we go on to studying similar comparison for higher dimension systems. So basically, what we do is we consider bipartite qubit state and tripartite qubit state. And what we see is that while in the 2-qubit case, different entanglement measures are monotonic, but in this situation, the entanglement measures do not remain monotonic anymore. Now, for bipartite qubit case, what we get is that for psi equal to C000 plus C111, C222, maximum deviation between negativity and generalized concurrence can be as large as 36.6%. And then that for tripartite qubit state, psi equal to 0000 plus C1111, we see that there are two different measures of entanglement called tau and G. They give exact same quantification of entanglement, that is C0 square, C1 square, where C0 and C1 are Schmidt parameters. Now for this state, delta Q trivially vanishes. Now, what is important to note here is that one can argue that for 2-qubit case, different entanglement measures are defined differently, so naturally they will capture different deviations. But what we found is that it is not true. For example, for concurrence and negativity, they are defined differently, but they give exact same amount of quantification. Likewise, entanglement of formation and entanglement in the case of higher dimensional system, we see that the entanglement measures tau and G are also defined differently, but they give exact same amount of quantification. Coming back to higher dimension systems, we see that different entanglement measures may not remain monotonic with respect to each other. So this is the key points that we just discussed. And then we went on to exploring some further direction based on different distance measures. So basically we define a distance measure T based on Frobenius norm. So suppose there is a given state psi and you want to find out how far it is from the state, psi max. Psi max could be a maximally entangled state. So you basically define a distance parameter like this based on Frobenius norm, where Frobenius norm is given by this expression. And then you define another distance measure based on fidelity, and then expression is given by this. What we see is that as we find the fractional deviation parameters for D and C, we find that D and C exactly match with respect to each other, and D provides an upper bound to the fractional deviation curve for N and Ln, but not for entanglement of formation. So again, D and C are defined differently based on two different distance measures. Still, they give exact same amount of quantification. And on the other hand, D and C provide upper bound to N and Ln, but not for the entanglement of formation. Next, we go on to defining another fractional deviation parameter based on Bell violation. So Bell violation for any for a 2-qubit state in 2-outcome 2-setting scenario is given by this expression, where C0 and C1 are Schmidt coefficient of the state. And then you can define a fractional deviation parameter based on Bell violation as this QBV equal to BV max minus BV divided by BV max. So BV max could be Bell violation of maximally entangled state, that is 2√2, and then BV will be the maximum violation provided by any non-maximally entangled state. So if you have non-maximally entangled state, you find out the right basis and then see what maximum Bell violation it gives. So you subtract that value BV from the Bell violation provided by a maximally entangled state and then renormalize so that the value is between 0 to 1. And then what you see is that based on this measure, we are able to get a deviation parameter QBV, which gives an upper bound for entanglement of formation, negativity, and log negativity, all three. So these are some directions that we study towards finding, different notions of, distance measures for entanglement, and what we in the end conclude that the results of studies in the present paper bring out the need for exploring further directions and different ideas for quantifying how far or close a given entangled state is to or from the maximally entangled state, and comparing the results obtained by using such quantifiers with those based on different entanglement measures. And this leads to the following question. Is there any fundamental criterion for assessing which quantifier is the appropriate one to be used for addressing questions such as the one posed in this paper, or would such a criterion have to be operationally defined, essentially dependent on the specific context in which the entangled state is used as a resource? And a comprehensive study is required for shedding further light on this issue, as well as for gaining a deeper understanding of the comparison between different entanglement measures, taking into account the studies proving their respective physical significances. So this is all from my side. I think there's some question and I'm open to take that.
Yeah, so Professor Gopal, you can go ahead with your question.
Thanks. Yeah, nice talk. I just want to know, so to calculate D, you need knowledge of psi max, right? How will you?
Well, so we have given state psi, and if you want to compute D, so what basically we do is we treat all maximally entangled state on the same footing. So for example, if I have to find a distance between psi plus and psi minus, basically they will be treated on the same footing, and they will not have any distance because both of them have maximum amount of entanglement present in them. So basically we found, we choose all maximally entangled state psi max, and then find distance with respect to psi, and whichever gives the minimum distance is the appropriate psi max for that. So there is an optimization mechanism that goes into it.
For example, because you all also showed experiments, the question I'm asking is so you generate some psi.
Yes.
But you also need to have knowledge of psi max in your experimental setup for calculating the D.
Not necessarily. I mean, here, for example, you take any psi, any state psi, right? And then if you want to compute D, then psi max could be any of the 2 qubit maximally entangled states, and whichever gives the least distance will be the appropriate quantifier.
Okay.
So there's an optimization procedure, so we have to find out which psi max gives the minimum distance, and that will be your psi max for defining the distance measure D.
Okay.
Is that clear to some extent?
Yes. So, and your experiments are with the single crystal, right? One nonlinear crystal.
No. These are done using a paired BBO crystal. So we basically use type 1 SPDC process in a paired BBO crystal to generate a state like HS plus VB by root 2.
Okay. So these are back to back.
Yes. Their optic axes are orthogonal. Yes.
Orthogonal. Okay. Thanks.
Can I go, Gopal, if you're done? Okay. Very nice talk, Ashutosh. I exactly wanted to discuss this experimental setup. Okay. So, what is your wavelength of?
Are there any further questions?
Because I started asking, so maybe there's a delay because of Zoom. Unless you want to stop me from asking, but I guess not. Anyway, Ashutosh, to save time, I just go ahead with my question.
Okay.
So there's this input laser, which what is the wavelength of that?
405 nanometer.
405. So you have two 810 coming across on the other side, right?
Right.
So do you need a lens, because isn't this beam already collimated?
No, I mean, at least Gaussian divergence will be there. So
I see. And what is can you walk me through the polarization state before and after each element here?
Yes. So suppose you have excuse me. Yeah, so suppose here you have a laser beam, it may not give pure HOV polarization. So you want to correct for the polarization and have a maximum output, So use a half a plate and PVS combination to prepare, pure H state after the PVS. So that is the use of this half a plate and PVS combination to prepare the input polarization state of the laser beam, which may not be a pure state. You prepare pure horizontal polarization state using that. And then you have a half a plate H1, you put it at 22.5 degree, and then you prepare a diagonal polarized laser light. And then this is a temporal compensator. So basically what you do is when these photons pass through this nonlinear crystal, there is birefringence as well as dispersion. Because of this, the photons created in the first crystal and those created in the second crystal develop a temporal lag. And in order to
sorry, what dispersion happens before you get into the NLC?
Yes. So this TC is a temporal compensator. Yeah. So this is used to pre-compensate the temporal walk-off that the photons see in the nonlinear crystal. Okay. So there are two processes that are happening. So first one is a pair of photons getting created in the first crystal, and then a pair of photons getting created in the second crystal. Now, because there is a finite thickness of the crystal, and therefore, suppose if you assume that SPDC process happens in the middle of the crystal, that's a crude approximation. Middle of the crystal, the first one, and then middle of the crystal, the second one. Then there will be a temporal delay between the photons created in the first crystal and that in the second crystal because of two factors. One is birefringence, and there is dispersion. There's a wavelength change and there is polarization change. So one travels as E ray, other travels as O ray, and also there are different velocities because of they being at different wavelengths. And as a result, if you put two detectors, one detector here and another here, and if you do a coincidence measurement, then by knowing the arrival time statistics of the photon, you can predict which photon was created in which crystal, and this gives you a distinguishability parameter, and therefore the photons will not remain maximally entangled because they're not maximally indistinguishable. So in order to kill their distinguishability, you basically use a temporal compensator here, TC.
I see. And what is the polarization after the mirrors M2 and M3?
Mirror M2 and M3. Yes. So here we cannot comment the polarization because this is the entangled state. So the state is alpha HS plus beta VV. It could be HS plus VV by root 2. For alpha and beta, it could be 1 by root 2. So individual photons do not have a polarization state because it is an entangled state.
Okay, I see. And okay, so thank you for that. Okay, so the other question I wanted to ask was you used the phrase numerical optimization when you showed the deviation plot.
Yes.
I think Yeah. Can you elaborate on what exactly do you do when you do numerical optimization? This one, yeah.
Yes. So we have these terms, we have different Schmidt coefficients C0 and C1,
right?
And then you have different entanglement measures. So basically you find delta Q NL. Now the objective is to find for what value of C0 and C1 you get the maximum deviation. That's it.
So where is the optimization? What is the process of optimization?
I mean, you may end up getting a local minimum. So you do not want a you may end up getting a local maximum, meaning that maximum deviation could be a local one. You do not want. You want over all the state space. What is the parameter C0 and C1 that gives the maximum deviation?
All state space basically requires you to span C0 from 0 to your maximum value of C0. Correct?
Yes.
So I calculate that for each C0 and I get a C1 on the other side.
Yes.
And so I have all the states and then I calculate the max delta QNL.
Yes.
So is that a calculation or is that an optimization? I mean, see, for me, maybe I'm mistaken. I don't know this field very well. For optimization would be that for one particular parameter, you can get many values and then you have to iteratively sort of refine the initial parameter. Okay. In my mind, it is a well-defined process itself that once you know what C0 is your choice, okay, that decides C1, and then you calculate step by step the max delta QNL. Is that right, or am I missing a point?
No. Can I?
Sure.
Shed a
okay, Urvashi, can I? Sorry, Urvashi.
Yeah, you go on. Yeah.
I'll invite you in a few minutes' time. Correct. So did you understand my question, Ashutosh?
Yes, I did. Here, I think there are just two parameters. I mean, like C0 and C1, they are interlinked, so there's just one independent parameter.
There's one parameter, C0, I would imagine. Yeah.
True. Yeah, it could be like finding the global maxima. Yes.
Okay, we'll come back to that.
But in other cases, when you are going to other here, for D and C, here problem becomes a bit complex because there are different choices for psi max. Okay, yeah. So you have a complete maximally entangled state over a 2-qubit state space, and then you have to find distance of a given state from all the maximally entangled state.
Yeah, so this part you explained to Gopal's question, you explained this, and I probably picked the one. But can I move on to my last question, which is kind of because of time. This is kind of a very naive and generic question. Okay.
Sure.
What is the motivation of defining deviations from the maximally entangled state? Where does it have implications? Since I'm not from the field, can you elaborate slightly?
Yes. So I mean, suppose you are given a non-maximally entangled state, and if you want to use it for a certain application, and once one person gives you reports the amount of entanglement as a function of negativity, other person reports as concurrence, other person reports log negativity, because they have a certain trend. Okay, so one may get fooled, by just looking at the number that one state is more entangled than other. If two people report different quantifiers, and that is where it is important to note that there is a significant departure between different entanglement measures, and it is as high as 23.57% for 2-qubit state and 36% for higher dimension systems. So I mean, it is important to note these differences, and then all entanglement measures are monotonic. There is no issue so long as people use the same entanglement measure, no issues. But if people report two different entanglement measures, then one has to be very careful and cautious, in finding that which is more or which is less entangled, because there is a high amount of departure between them.
Okay, got it. Thank you very much, Ashutosh. Urvashi, can I request you to come back to that point?
Yeah. No, I'm perfectly fine. You want me to come back to a point?
No,
no, I was actually just trying to say that, the way he's using the word optimization is that, we can of course fix the value of C0 and then find a range for C1. But one has to appreciate that C0 also has a range, and we are constrained by what the values are for the maximally entangled state. So, I mean, C0 and C1 will of course be 1 by root 2, 1 by root 2. I mean, so then it's not like 0 to 1, 0 to 1 in that sense. So then it is a little bit of, choosing, let's say 0.1 for C0 going over the entire C1 range. Then again, C0 goes to 0.12 going also. Then this becomes very difficult if you want to do it on pen and paper. So the idea of using, some sort of software to do this so that it can be automated actually is appealing, because otherwise we have actually missed out. So this 23.57 that he's showing came after a lot of care. I mean, this deviation that he has shown for this, the slide that we are currently looking at. P0 value is 0.217 and 0.976. So it is very difficult to actually do something like this purely by hand. So that is why he would, use a numerical technique, so that we don't miss out. Because as Ashutosh was saying, it's very easy to miss out on these large deviations. And what we wanted to show was, so long as you and I are using negativity as our thing, okay. But then if we actually go to negativity and log, something else, you want to do log negativity, I want to do concurrence, then we don't always match. So we better stick to either the same quantity, because it's not like you are 5 feet and same in centimeter. It's not. That is the point about this, non-equivalence. So that is why, not to miss out on a particular trend, he would have used that's what I wanted to just.
I see. Thank you. Thank you.
Yeah.
Thanks.
And one last point, because here one may it may appear that just one parameter is there, but if we go on to others, there are even 5 also comes in. Psi plus psi minus, if we want to distance between them, it is 0. You don't get just like that. So you have to optimize over all the 5 parameters. So I mean, this is generic method we adopted for all the distance measures, and therefore we call it numerical.
So by phi, Ashutosh, you actually mean the relative phase term, Sushil.
Yes.
So it is not just about the coefficients. No? There is also a relative phase between the two terms which are forming the entangled state, and that goes from 0 to 360. And so that also needs an optimization to give you the correct distance measure. So there are, as you know, for 2-qubit state, we will have 3 parameters that come in to define it, because of the global phase, not an issue. So each is a complex number, right? Psi 1 and psi 2. So naturally 4, but 1 will go off because of trace, blah, blah. And so then that phi parameter is also crucial. And so if you wanted to actually do this one by one like that, it's not going to quite converge.
If I may interrupt, we are running short on time.
So I will shorten my talk, because.
Well,
thank you very much.
Yeah, so thank you for that talk and the discussion that followed. So now we'll move on to the next talk by Professor Urvashi Sinha, which she has promised that she will shorten. Okay, so
Rarely do I have the opportunity of following up on my student. I think this is a privilege which I usually wouldn't have, So I'm happy to shorten it just to help out with your conference time. So I have 25 minutes. Is that okay?
Yeah, I mean, hang on. I still need to.
Oh, you're going to say something. Okay, sweet.
Yes.
Still I have 25 minutes. Yeah. Okay.
Yeah, but I was just mocking about the time. This like
Thank
you
God.
can take your time.
I have 70 slides. Yeah.
Okay, so Urvashi Sinha is a professor at the Raman Research Institute in Bangalore, where she's heading the Quantum Information and Computing Laboratory, or Quick Labs for short. Professor Sinha is also an associate faculty member at the Institute of Quantum Computing, University of Waterloo, and the Center for Quantum Information and Quantum Control, University of Toronto. She was a Nehru-Chevening scholar while pursuing her MSc in physics from Cambridge, following which she was a Gates Cambridge scholar during her PhD at Cambridge itself, which was on experiments in high-temperature superconductivity. She then went on to be a postdoc at the Cavendish Labs, as well as IQC Canada. Her lab at RRI specializes in experiments on photonic quantum information processing, including quantum computing and quantum communication using single and entangled photons. She's heading India's first project on satellite-based secure quantum communications, which is super cool. Her scientific recognitions include the Homi Bhabha Fellowship in the year 2017, as well as the 2018 ICTP-ICO Galileo Donardo Award in Optics. She was recognized as one of Asia's top 100 scientists by the Asian Scientist for the year 2019, and also has been awarded the Simmons Emmy Noether Fellowship at the Perimeter Institute, Canada. Today, she's going to be talking on secure quantum communication at their Quick Labs. So with that, I invite you to begin.
Thanks a lot, Vikas. And are you the chairperson of this, your student chapter? Because I always get an email from chair. Are you the chair?
Oh, no.
You're not. So
Not
I would
yet,
like
at
to
least.
thank the chair as well,
Yeah.
and of course, Sushil, I think, is the mentor. I've been trying to tell students at RRI, come on, start the student chapter. But then I'm not as effective as Sushil. So that is the reason why I have not managed so far to convince people. But then on that, it is, I always like to give talks in these, and it is, of course, a privilege to be talking here in the TIFR OSA student chapter. So I will try to, stick to my time or go a couple of minutes less just for your, keep your time in the conference. So as mentioned, I'm going to talk on secure quantum communications at RRI Bangalore. And, given the time frame we have, won't get into a lot of detail about various things, but just give you a flavor about the different stuff that we are doing on this particular subject matter. And hopefully encourage people to take up similar activities here or elsewhere. Well, this is a snapshot of various experiments in the lab, and as you know, at the moment we don't really have visits, but then when we have visits, then do come and see these things in action. What we work on, and in fact the previous talk had some detailed discussion on these photon sources. So of course, Ashutosh was the previous speaker. And so we work on different applications of single and entangled photons, okay? And so while entanglement was the topic of the previous one, here we are going to talk about a little bit about the quantum communication aspect. And this is a review article that I wrote, which students especially are welcome to have a look at because, it has lots of details on these photon sources. So this is your typical SPDC source, this point being your point of entanglement. Vikas, can you confirm that my mouse is something that is visible to you when it moves on the screen? You can see
yes, yes, it is.
Yeah. So this particular point, of course, is the point from which you can harness entanglement, because you don't know which cone it belongs to, right? And so it could belong to either, and that is that's a picture from the lab, actually. Before going on to communications, couple of minutes, I'd like to give you an overview on the different experiments, different genre of experiments that we are doing other than communications at RRI. And of course, one of my basic interests, pet interests, I would say, is on various fundamental aspects of quantum mechanics. And so, while of course we are very excited about these applications in computing, communications, and whatnot, I do believe that our understanding of these applications also is much, much better if we understand the core concepts very, very precisely. So these precision tests that we tend to do forms the basis for this thought process. So here you have a series of experiments and some theory work in which we have shown that the superposition principle, which of course is the bedrock for quantum computing, actually has a correction term when you apply it to slit-based interference experiments. Any interference, but slit-based ones actually show this up really prominently. And so this correction term is something which we proposed in this particular work and then followed it up with this experiment where you can see how we have measured this correction term. And this is a theory. And of course, as you know, little dots with the error bar are always the experiment. And so this is something which is a precision test on an open field, even using microwaves, which we did to prove the existence of this correction term for the first time in the classical domain. The other aspect, which is again of the same genre, is fundamental quantum optics. And of course, this is something you guys are working on at various sectors. So this is an experiment that you see here, which is on the Hongo-Mandel interference effect, which of course is a quintessential tool for characterizing photon sources. And so now for the Hongo-Mandel effect to be 100% Hongo-Mandel dip, you hear, at least in the second chapter of a quantum optics book, that is the diagnostic. 100% dip money, you have this quantum phenomena. But what we went on to show in this particular paper is that indeed you don't really need quantum sources. You can do this using classical pulses as well with proper phase control. And so that was here. Okay, this is of course the studies of entanglement measures and dynamics. Ashutosh gave a lot of details on the dynamics part. In fact, the sudden death of entanglement is another experiment that he was involved in during his PhD, which he has now finished. But then we are going to finish the experiment as well shortly on manipulating sudden death of entanglement. Generalized measurements, weak measurements, any lab which wants to say it has anything to do with quantum had better have something to do with measurements scenario. And here we have this very nice tool called weak measurements, which is essentially being able to probe a quantum system such that we can, through an ensemble of weak interactions, gain information about what is happening between preparation and measurement, so to speak. Okay, and so that is something which doesn't usually happen in conventional quantum optics. Just wanted to check, Vikas, is my video on? Because I'm not entirely sure anymore, because I see my whole
your
screen.
video is on.
Okay, great. Yeah. So this is weak measurements by which you can do many interesting things between the preparation and measurement, conventional measurement step. So we went on to measure the expectation value of non-Hermitian operator, for instance, using weak measurements. Going on to more applications which perhaps you guys are more familiar with, for instance, quantum computing. What our lab is doing is not working on qubits necessarily, although we have some stuff going on with qubits, photonic qubits. But one of the things which we are pursuing is actually working on higher dimensional systems, where instead of qubits, we work with higher dimensional degrees of freedom. So essentially 3, 4, and so on. That is called qubit-based quantum information, both computing as well as communication. So here you have the experimental setup where we have a very nice, almost maximally entangled pair of entangled qubits here. And we have gone on to show a new measure of entanglement for these qubits, which is using much less number of resources than the conventional one for quantum state tomography. And this is something which sets the ball rolling for various applications we have in mind in the future. And again, students, if you're interested in this from a more general perspective, you can have a look at this article that I wrote in Scientific American, where I gave a little overview of these experiments in the lab. Going on to quantum communication, which is the main topic for today, today's talk. Of course, the main aspect of quantum in quantum communication is in fact the key distribution part, which is of course quantum key distribution. And as I like to say, this is the most quote unquote practical quantum technology. What does that mean? We hear of quantum computing and several other things, but then quantum computing, for instance, is something which is very exciting, but we are not quite there in the, like we have devices which you and I are kind of using for computing purposes. That stage will come, but in the future, not quite as of present times, right? But quantum key distribution is something which is actually being used practically by various agencies, whether it is the banking sector, the defense sector, in other countries at the moment, but soon in ours, we hope. And so even people like you and me, Samsung came up with this QRNG in the phone. So this is the kind of thing which actually is much more in terms of technology readiness level, it's kind of higher than some of the other things which we hear in the quantum technologies domain. And that is kind of the reason why I say it's kind of most practical in that sense. Well, why you should, of course, worry about it is not because it's the most practical, but because it is actually very, very useful. And so these things that I have listed here, I think we are all, suspected users of at least the first 3 applications, whether it's buying something with a credit card, in very young students' case, the parents' credit card, online banking maybe, and of course, most of us hopefully are voting. The defense communication part is, of course, a niche area which our country's defense sector is involved in. So what is common between all these things that I've listed is that these are all examples of strategic communication, right? Where security is important. So if I'm going to buy something with a credit card and I give my details, it better not reach Vikas. Because if that happens, if he's unscrupulous, he might just, use it for buying something that I didn't intend to buy. And so things like that we have to avoid. So there is a level of security that is required in this communication. And so that is what, of course, forms the basis for classical cryptography, right? And the problem, however, is that the current means of doing this, many of these techniques will be compromised with quantum computers. And so we need to take steps now so that we can prevent this catastrophe. And the solution is quantum cryptography. So what is that? What is wrong with classical cryptography? Whenever you say that you're doing something and you're very excited about it, and of course, as a scientist, we tend to get excited very easily with little joyous, small victories on a I would say yearly basis. Mostly it is troubleshooting. But then, of course, comes the point that still there must be some reason behind all this, which is beyond our own excitement. So, what is wrong with what we're doing now is important, right? So, what is wrong with classical cryptography? What is wrong? I mean, basically the problem with it is that unconditional security is not possible. For instance, RSA protocol, okay, that is a standard public key crypto protocol that is based on the mathematical complexity of factoring large numbers. Okay? Now, it is correct that, factoring large numbers is not straightforward. 3 times 7 is 21. But what are the prime factors of 1, 1, 2, 3, 7, 1? I don't think you can just say it as easily. But then there is Shor's algorithm, and this is Peter Shor. He came up with the algorithm, which using quantum gates can perform factorization in polynomial time, essentially changing the hardness class of this problem, and which makes it possible now, all of a sudden, in real time. And so then, of course, it's an issue. So essentially, the issue is that not quantum, but computational resources, they grow very fast. And today's hard problem could be solved tomorrow using brute force attack. Okay, new algorithms could come up for classical computers, especially the young generation these days. I think they are born with coding abilities. My 9-year-old is learning coding, telling me about modified Grover. And oh my God, within 2 years' time, maybe she will know much more than what I do in classical coding. Okay, and so these people are a threat. They can come up with algorithms which will break things, which perhaps at the moment seems unbreakable on classical computers. Of course, realization of quantum computers, for instance, Shor's algorithm will run on it. So my security should be independent of future advancements in computational power, new algorithms, or new technology. That is, it should be future secure. What is this? This is a very important statement. Future secure means that today something that is secure should also remain secure 30 years down the line. If something comes up and breaks it then my, whatever it is that I'm trying to secure is compromised, then it's a problem. So I leave behind some, some inheritance for my next generation. They never get it because by then security is compromised. That's a problem. So this brings forth the need for quantum cryptography, where security is based on laws of nature or laws of physics and not on the mathematical complexity of a problem. And of course, the most important part here is the key distribution, which is quantum key distribution. Having said that, this is something I always like to say here, and that is this, that currently we're talking about these various key lengths and what is the security claim and so on. So this RSA 2048 bit, that is supposed to be secure till 2030. So Microsoft Research very, proudly said that it would take 1 billion years on a classical computer. A quantum computer could do it in 100 seconds. Of course, then you think, now what's going on? But then having said that, please remember that a quantum computer will employ Shor's algorithm to solve the factorization problem. It is estimated that this 2048-bit RSA keys could be broken on a quantum computer comprising 4,000 qubits and 100 million gates. And of course, we are not there yet. We will take a little longer to reach this level or this size of a quantum computer where we have 4,000 qubits and 100 million gates. But that doesn't mean we remain complacent now. Because of course, if in few years' time, when we have this quantum computer, then this thing shouldn't be a threat at all. So we should have already moved on to some new paradigm so that this threat doesn't even exist. And that is why we need to work now on quantum cryptography so that the things proceed parallelly and the threat that is anticipated from the quantum computing architecture doesn't pose a threat anymore. Okay. So how does quantum mechanics protect information? Of course, there are many things to say here, but some of the ideas actually summarize this. For instance, measurement disturbs the signal on an average. If signals are non-orthogonal, then adversary cannot ascertain which one it is. That is the basis of, that is using Heisenberg's uncertainty principle. No cloning theorem comes in because unknown quantum states cannot be cloned by the adversary. Of course, quantum entanglement comes in. So quantum correlations can be used to protect information. So these are basically the ideas which are used to form the basis for the security that quantum mechanics provides us. And there are different approaches to QKD. You could have prepare and measure based approaches based on either uncertainty principle like BB84 protocol, B92 variants therein. Entanglement based QKD, where the security is based on entanglement. So popular ones would be BBM92, E91 and several variants. Okay. And why do we need entanglement-based QKD? Because if you want to go a step further, if you want to go to a situation in which you don't even trust the devices that you are using currently, security vulnerability introduced at the device level itself, then you need QKD, which is device independent. And in fact, entanglement is the only known way of providing such security. We won't get into the details, but that is what is one of the reasons for entanglement-based QKD. Now, for the next 5 minutes, I'll talk about one of the applications that we have been working on, and then for the next 10, I'll talk about another one, and that's the idea. So the first thing I wanted to say in terms of our recent work in this domain is actually a very interesting quantum state estimation technique that we have established in our lab. Okay? And why is this important? Because of course, having said all this, a lot of it is based on our knowledge of the initial state. So if we know that, okay, fine, the states are getting encoded at Alice's end are H and V, let's say, only then, of course, at some level, we will know that our error will be low in the key also, that is established between Alice and Bob. So the wave function, of course, is used to completely describe a quantum system and is central to quantum theory. In theoretical calculations, one can assume a form of the wave function and then proceed with the calculations, right? But what about experiments? Example, quantum computing or even quantum communication. So precision and knowledge of the state of the system leads to precision in all that follows. We simply cannot assume something and think that our assumption is right. Something theorists are sometimes guilty of doing, because they just assume this is the wave function psi and the rest is history. But then in our case, when we are doing stuff in the lab, that assumption, we don't have the liberty of making such an assumption. We have to know how precisely we have been able to do this. In fact, related to the previous talk where Ashutosh was trying to say, we have this maximally entangled state, but then again, when he measures something in the lab and measures the distance, his maximally entangled state could very well be the perfect psi plus, because that's a theoretical one. But the experimental one, the psi that is producing, need not quite be what he thought it was. So then that will lead to errors in whatever we are doing in the lab. So once we know the density matrix, of course, we can calculate many important quantities. For instance, if you are, from the field, you would know that reduced density matrix can be used for calculating entanglement measures, like entanglement entropy, for instance. So in our work, we use one of the most fundamental phenomena in quantum systems, that is interference, to devise and experimentally demonstrate a new method for quantum state estimation, which we call quantum state interferography. It's an interferometric technique or method using which an unknown quantum state can be inferred from the visibilities, phase shifts, and average intensities obtained from a number of interference patterns. Okay, and so this is the reference if you are interested, because I have 5 minutes to talk about this, so a lot of details will not be there in this, but look up the paper. And of course, being from the quantum domain, we are always a bit, we have this thing of always going back to the roots. So, what we are doing here is, of course, using interference for quantum state estimation. But interference is, of course, at the heart of quantum, right? As you know, a double slit interference was called the most beautiful experiment of all time by readers of physics world. And in fact, Richard Feynman, of course, says that, or said that we choose to examine a phenomena which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart, heart of quantum mechanics. In reality, the interference experiment contains the only mystery. So in some sense, interference is at the heart of many things we do. Again, we are using interference to do something very different from the usual thing, that is quantum state estimation. Okay? And so what is it? Our central question is, we want to have a black box approach to state determination, such that, this is the question. Can we have a device with which, without any change of internal settings by the user, we can determine the quantum state of the system? So you have the device, you have this beam which is defining your state, and then you read it out. That is what we want to find out, and that is what we kind of go on to do. Okay. So here we have so there are many other ways in which people are doing this, and of course I won't get into the details, but that is using weak measurement or direct state measurement or tomography. So here we are not doing any of them. This is a new single shot state estimation method using interference as a tool. Okay. And just a quick this thing here, visual aid. So if you do the standard quantum state tomography, where essentially you're projecting your quantum state to different projections and then reconstructing the state, then that actually scales as d square in terms of the number of measurements required. So here you have this tomography. So suppose you have a 10-dimensional system, tomography will read 99 measurements. Okay, but for our quantum state interferography, if you assume with this pure state assumption, you will of course need d minus 1, which is 9. The best that people have done so far is 5d minus 7. Okay. Which is better than tomography, but ours is d minus 1, which is of course the best so far. So that just brings it down to 9. So instead of d square minus 1, we have reduced it to d minus 1 number of measurements. And so for 2 dimension, you can see that will give us 1. So that is why it's single shot, right? So this is of course a schematic. Okay. So these are various experimental results. So when you want to determine the quantum state, then of course we have actually gone on to go over the entire block sphere. So by using half wave plate and quarter wave plate we can actually sample the whole block sphere. So we have actually done that. So different angles and how this phase shift intensity, they match with theory. This is what we're showing you here. So this is the phase shift versus various wave plate angles. Here we have the average intensity, and here we have the visibility. These are the three terms which we are measuring. Okay, and so the fidelity that we obtain for pure states is between 0.97 and 0.99, of course highest being 1, and for mixed states slightly lower, but of course average is still 0.95. Okay, so this is extremely good and very comparable to tomography, if not better. And this is a schematic for how this can be done for higher dimensions. I'll skip the details for now. And here we show you how you can actually use quantum state interferography for determining the entanglement of a bipartite state. So entanglement determination, usually we do it through tomography and requires many more settings. So as you can see, here we require 2 settings, whereas quantum state tomography we require 9. Okay, skip the details for now. And another very interesting prospect, which we have shown in the paper also, but then something to take forward later, is how we can miniaturize this whole thing and actually have a little box which we can carry around and measure the quantum state whenever we want to. That is the idea of miniaturization, and we've kind of shown how that can happen in our paper. So this is the idea. So essentially have little holes and then, films for these, what you call it, the operations, the polarization and the half-wave plate. And then you basically just do the polar decomposition and measure the state. Okay. So this is one of the things about how we can use interference as a resource to estimate the quantum state by a single shot measurement for qubits, d-1 for qubits, and a single shot also for pure entangled state estimation, entanglement estimation. Going on to the QKD experiments, well, just an overview. These are all the various experiments that are ongoing. We are, of course, working on satellite-based QKD on India's first project on the same, quantum experiments using satellite technology, integrated photonics-based QKD, then quantum teleportation, which is another form of secure, can be secure, but then basically quantum communication without QKD. And here we have quantum random number generation under this new project that we started a few months ago. Okay. Regarding prepare and measure based protocols, of course, we've done all the standard ones, but some non-standard ones as well. This B92 protocol that we have done, 1.5 years ago, I would say, is actually a modification of the original one, in which we have ended up getting a higher key rate and a lower error than the results that were best known so far using parametric down conversion based B92. Okay, so these are, of course, snapshots. Let's skip the details of the setup, but essentially this is an important thing where you can see that the key rate is around 50 kilobits per second, and Q bar, which is the quantum bit error rate, has been constrained to be below 4.8%. This 4.8% is very important because you see, if you're doing QKD, you can always say I have this key rate and this error, but then it has to mean something beyond that. So there is actually a lot of calculations that one does using information theory, by which you can put an information theoretic security threshold for these various protocols. So for B92, it's 4.8. So anything above 4.8, if you get, then that is not a very good candidate for a secure key. So you have to constrain your Q bar below 4.8. Only then you can accept that run. Okay, and so that is something we have taken a lot of pains to do, and constraining it below 4.8 and still getting a very good key rate for the system in hand. As I mentioned, so this was the earlier result, which had these numbers. And of course, I was being better than that. Then, of course, we have also done entanglement-based quantum key distribution. At the moment, ongoing, our demonstration of BBM92, protocol. So we are currently, of course, working on the free space part. I'll show you some pictures in the end. And of course, goes without saying that the quality of entanglement plays a very important role in the the demonstration of the protocol as well. And so, as you can see, the current source which we are working on for BBM92 has a concurrence of 0.995, and concurrence is the measure of entanglement, highest value being 1. So clearly, this is as good as we can get this to be, and so naturally we will end up having a good key rates and low Q bar. And so this is another reference which students can definitely look at for our experiment on for our in-lab demonstration of QKD. In fact, this was the first reported in-lab end-to-end free space QKD, reported in an international journal from our country. And so this is a very nice thing. Please have a look. It's a very long paper, but also gained a lot of attention from various sectors, the IBM and so on. A lot of excitement was generated. One of the things we did in this paper, actually, of course, the experiment is fine, but one of the things we also ended up doing, which inadvertently we ended up doing, is develop a very what should I say, useful simulation toolkit for QKD. Okay, so you want to do QKD of various different optical components, lots of components are required before you can actually demonstrate this. So now comes the point that are you going to buy everything, set it up, and then figure out what would be the key rate and error? Or would you have some means of having some simulation going earlier so that you have an idea of whether this is going to work out for you or not? Of course, we would choose the latter because we don't have infinite resources. In fact, very limited resources we have, like as researchers. So then we would like to know, whether this is going to be a good investment for me and whether it's going to give me competitive rates. Okay, and so lots of simulation toolkits exist in literature. These are some snapshots of some examples that we have found. But what we wanted was a quick and precise simulation of physical processes considering realistic experimental imperfections. Okay, source, detection, background noise, all protocols we want to simulate. So essentially what happens is that these things that you see, and there are more, they were all developed perhaps by software developers. So they consider it more as a software development, which is fine. But then forgetting the fact that an experiment is an experiment, it will have its imperfections. Your beam splitter will not be 50. Your detector will not have 100% efficiency. So these things need to be also brought into your simulation. Only then you will have something which will realistically match with what you will end up actually demonstrating after a lot of hard work. And so that is the idea of QKD Sim, because QKD is becoming commercially viable. We want to do something where we don't have to directly test these every time. So that is why we take into account these physical process models and imperfection and non-idealities and come up with a simulation and following what is called the AGIFOL model of software development. Okay? And our experiment and simulation, they match very well already. And now we are already at the second iteration where we hope that the match will even be better. All this is motivated towards, and I have another 3 minutes left. So all this is motivated, of course, in our lab towards, increasing the distance of communication. Because while we are doing in lab ones across institutes, so on and so forth, the main idea behind this is, of course, towards our project in satellite QKD, where we want to increase the distance. So if you want to just increase the distance like that, beyond the point, line of sight is a concern. So pre-space, you have to see each other in order to communicate. So beyond a certain point, let's say a couple of 100 kilometers, it becomes difficult. Then you want to do fiber, okay? But fiber has a problem because, of course, there's an attenuation. And if you actually go to a certain distance, the signal drops. Normally, what you would do, you would boost it up using a repeater. But you can't do that in quantum because, of course, no cloning theorem will be violated. So you have to come up with some unconventional way of doing this. And the two known approaches right now, which is being investigated globally, is using quantum repeaters, quantum versions of these repeaters, or satellite as a trusted node. Okay? And so in this quantum repeaters domain, we have a project under the DST Quest program where we are working on relays, memories, and repeaters, where the general idea is, swapping of entanglement almost like a relay race. So two guys are entangled, then they swap it between two more. And so this way, distance is increasing. But then at some point, memory has to come in, and that will lead to the repeater approach, something they're doing. Of course, the other project is on satellite-based QKD, and here the idea is that a satellite comes to a ground station, spends some time, establishes a key, then it moves over to a new ground station, again establishes a key, and by performing some operations, then these two ground stations are linked by a key, which originally wouldn't be possible with just line of sight approach. And so that is the idea of using a satellite as a trusted node. And then various distances can be achieved using these techniques. The idea being going towards this, global quantum communication network, where we will have satellite-based QKD, then some fiber-based approaches, and together we can connect up different parts of a country and then different countries. And so that is the general idea towards which this entire field is going. Different approaches from different countries, different projects at different levels of development. Okay. So this is our project, which is a collaboration between RRI and ISRO, started in 2017. And of course, the idea being establishing information theoretically secure quantum communication over large distances, performing QKD between two Indian ground stations using an Indian satellite as a trusted node. And so these are our portable ground stations. As you see, these are within the RRI campus. And so this is one of our domes with the, the telescope. This is some of us within them with the telescope in the current situation. And, hopefully, as I like to say, the masks can't mask our enthusiasm. And so we are very much en route towards demonstrating on-campus free space KKD as we speak. So on that note, and on hopefully on time, I think I will like to stop now. So I just wanted to give an overview on various things, and yeah, thank you very much.
Yeah, so that was very much on time. The floor is now open for questions.
Well, should I stop sharing or no, maybe not.
Could I ask a question, Vikas?
Yeah, go ahead.
Vikas, yeah, okay. Yeah, Urvashi, very nice work and talk. Like, so I just very naive question. Like, when we talk about free space propagation, like, so what's the role of weather and pollution? How do you take care of these when?
That's of course $1 million question, and so that is something which actually requires a lot of effort in some very dedicated simulations have to be done in order to take it. So there are some 32 parameters which we are currently taking into account to see whether a certain location is suitable for a ground station. Because of course, on campus it's fine. Beyond the point, it is definitely going to work with a little bit of attenuation in the key rate. But then we are of course aiming to look up, right? And so then in some sense, indeed, we don't want a location which has too much, cloud cover. So cloud cover is an issue. Then of course dust. So we want to be a little high. We don't want to sit bang in the middle of Bangalore, probably. And so then many such things are being done by us with using known tools, but then for different locations. And so definitely something, a major point to be taken. But then of course, if it is something meant for the students, so so you and I will probably are the kind of people who will be sitting in those ground stations and doing these things. But then somebody like our Prime Minister, if he wants to use this, he will be sitting in his own location and we'll be transferring it with the fiber. So that is the point. So we'll choose the locations cleverly, but then definitely satisfying other requirements as well.
So I mean, the point which I would like to make is like eventually like free space may be there, but the ground stations are fixed at certain locations, optimal locations. Then the fiber-based networks will be essential.
Absolutely. So it has to be a hybrid which will solve real life problems. Yeah. But then, of course, the free space is very important because that will give you the much longer distance without the fiber. The fiber. So there is one way of using the fiber, which is called the trusted node-based approach. So you can essentially have these, let's say 100 kilometer links with one node. So these nodes you are trusting. So Alice Bob, then Bob becomes Alice for the next Bob. And so that way, so China has already done a 2,000 kilometer link using this. So many things to combine and.
Vikas, can I go?
Yes, go ahead.
Actually, that was really amazing, very fantastic. All the best to your group for all this.
Thanks,
something that you were about to elaborate but did not was about quantum repeaters.
Yeah.
So, current state of art, what are the candidates for quantum repeaters?
Yeah. So of course, the quantum repeater is actually a combination of the quantum relay with quantum memory. Okay. So the relay part is what I was, I don't know what exactly is happening. Okay. Just one second, Sushil. I just wanted to go back to the relay part. So I just didn't have the time to say this. Good you asked this question. So essentially now what is the relay? So here you have an entangled photon source and here you have another entangled photon source. So 1 and 2 are entangled and 3 and 4 are entangled. What we do is we make 2 and 3 perform a Bell basis measurement, as a result of which 1 and 4 become entangled. So essentially we have swapped the entanglement, which was originally between 1, 2 and 3, 4 and made 1 and 4 entangled. So in effect, having a slightly longer distance between the original parties, which were all located in one spot and the other. But then beyond the point, you won't be able to do this. You can have a few stations, but then beyond the point, this is not feasible. So we need to store the information also, because you see, on demand, we need to be able to do this sort of swapping beyond the point. And so somewhere we need to have a memory kick in. And this is where there's a lot of research going on, right? Because while there is EIT-based approaches that is a very common one. Then there are these rare earth materials which are being used for as materials for storing quantum information. So there are several groups worldwide which are working on trying to get innovative approaches, because the point is that we need a long-lived memory which is also at room temperature. Because otherwise, there's some of these guys, they require cooling, which is okay for research, but then if you really want to make this practical and all. And then of course, if it's a room temperature, it is microsecond, millisecond, then it's not very useful. You want to increase the time. So this is why, there are different approaches to the memory. So we don't know which one, there are new papers which come out every day, new materials. So lots of scope for materials in this. And so once, but then the idea is relay with the memory will give you the repeater. So we need both to kick in. And so while the relay part is somewhat better understood, the memory, there is a lot to explore.
Okay, thank you.
Yeah.
If there are no more questions.
Students have no questions.
That has been a problem for the last
We
2 days.
just had a nice chat. Yeah. Okay. No problem. So I'll stop. Thanks.
Yeah. So thank you, Professor Ubasi, for that amazing talk.
Thanks a lot.
With that, I'd like to end my session as a chair and pass it on to Pawan.
Hello everyone, we now have the final talk by Professor Kasturi Saha. Professor Kasturi Saha did her BSc from St. Stephen's College, Delhi, and then went on to do her MSc from IIT Delhi. She then opened a PhD under Professor Alexander Gaeta's group in School of Applied and Engineering Physics at Cornell. She then did a postdoctoral fellow with Professor Capillaro group in a research laboratory of electronics at MIT, USA. Her research areas include nanophotonics, precision metrology, and the development of quantum technology with solid-state color defects. She's also a proud recipient of DST Inspire Faculty Fellowship. Currently, she's an assistant professor at IIT Bombay in the Electrical Engineering Department. We now invite Professor Kasturi Saha to provide us insights with the various color defect centers. Over to you, Professor.
Thank you. Thank you, Pawan, for the introduction, and thank you for this invitation. I hope you can hear me clearly. Is it fine?
Yeah, it's audible. Yeah.
Okay. Thank you. So thank you, everyone. And I guess it's been a long day and all of you have been listening to multiple talks. Hopefully, I'll be able to share something interesting and keep you engaged about NV centers in Diamond. So I'll just share my screen.
Yeah, you can share your screen.
Yes, so just give me a second. So are you able to see my screen now?
Not yet. Yeah, we can see it now.
Okay. Okay, so I'll just go to the 1 second. I'll just go to the pointer option so that you can see a laser pointer. Okay. I hope you can all see the laser pointer that I'm moving right now. And again, thank you once again for this invitation. So today I will be telling you about the dynamic wide field microscope that we have built using a quantum diamond microscope. Essentially, what we want to do is do wide field imaging, and we want to look at various different problems of wide field imaging, especially magnetic field imaging. So here you can see a little image of my lab, and I'll be telling you more about the experiment on how we do this wide field imaging. So to give you a quick motivation about why we are interested in, and this is just one of the problems that we are interested in. So if you look at this 1895 image of the, of X-ray, this image has been taken by Röntgen, the inventor of X-rays, and this is his wife's hand. And what you can see here are the bones of her hand and the ring here. When Ranjan's wife actually saw this image, she said, "I have seen my death." But indeed, this image is really one of the pioneering images for X-ray, and tells us that, over the years, since 1895, we have kept on using X-ray imaging for looking at bones. And here you can clearly see the bone structure. So in 1971, we went on to doing this kind of an image that you see here, which is of an MRI image, which is a completely alternate way of imaging the human body, which is magnetic resonance imaging. And the difference between the first and the third one is that here in the first one, you can only see the bones, and whereas in the last, like the third image, you can actually see the structure. You can start to see the structure of your tissues, right? So, but it took so many years, right, to get to the point where you go from just looking at bones to looking at tissues. But what is more interesting is if we can now go deep dive into this tissue structure and actually image the cells which make up this tissue, right? So here we are interested in looking at the neurons. So this is an image of the neuron, and you can see that the neuron is connected to its neighboring neuron with an axon, and some dendrites are there, and these two neurons actually share information using electrical pulses. And that is how we communicate with each other, think, do all our activity, all our thinking process happens via these communications, which are actually electrical pulses, right? So just to remind you of the complexity that we are looking at, we are a voxel, which is of a size of 1 millimeter cube, has about 50,000 cells and 6,000 synapses and about 300 million connections. So you can immediately see that it's a really complex network that we are trying to visualize if we want to go from here to here, right? So it's indeed a really complex problem, and we want to break down this problem into a very tiny part and try to find out some way in which we can look at these cells and image these cells, right? So the traditional way of imaging these neurons is essentially just doing an optical microscope image, which is a 2-photon image. It turns out that this 2-photon imaging, and I'm not really going to go into this the details of this 2-photon imaging, or the details of the optical microscopy. Essentially what you want to do is pinpoint the location of each of these neurons. But as you know, as any optical method, as the optics, so the laser, perhaps if it goes inside, say, the mouse brain, it's going to scatter within the tissues, and so you really are limited by the scattering, right? So you really cannot image deep down into the brain structure and actually understand the cellular structure. So the motivation for us is then to find out an alternative way of imaging. So that's really the key that we want to find out. And the way we have thought of this problem is that, well, if this is an electrical pulse that is being used to communicate from one neuron to the other, an electrical pulse traveling down a wire essentially produces a magnetic field. And what we are interested in is, if we can have a sensor which is very precise, then we can measure that magnetic field. And that's where we come in with this sort of a quantum diamond microscope. And what I want to tell you is a little bit about the color defects in diamond and how we build a wide field microscope that will be used for imaging such neurons. So what we are actually interested in is looking at these diamonds which happen to have these defects, and any defect as you know, that diamond is completely clear, colorless. So if it's a very pure quality diamond, then it's colorless. But when you have defects, like for instance this one, nitrogen, then the diamond actually becomes yellow in color because it fluoresces in that yellow. And then if you have various other different kinds of defects, you will have different very colorful gemstones. So in our lab, we don't have anything that looks like this. It actually just looks like this. If you have a yellow diamond, which essentially has a lot of nitrogen defects in it, and if you do a photoluminescence sort of a spectrum, you will see if you have a variety of different, say, diamonds that actually look like this, you will see a variety of different kind of spectra. But what is important in this PL spectra is essentially these two little peaks that you see here, which corresponds to this NV0 and NV NV minus. So what are this NV? So I was just telling you about the nitrogen defect, but now we're going to talk about the NV, which is really the most important part of our story. So we actually work with not yellow diamonds, not colorless diamonds, but the ones that actually look like this, which are pink. These are nano diamond images. Okay. So if you actually zoom into one of these nano diamonds, typically here, this is 200 micron, you can get nano diamonds of the size of about, 100 nanometers or so diameter. If you zoom in there, you get nitrogen vacancy. So nitrogen, which is the substitutional defect in this carbon lattice. And next to it, if you have a vacancy, then it forms this nitrogen vacancy complex, right? So it's not just nitrogen and vacancy that is there, but you also need this additional electron, which is captured from the rest of the lattice, and then it forms this NV minus, which also has this spin that is pointing around the 111 axis here. So it is the NV minus that is the defect of interest. Of course, there is other two charges that are there. It's charge neutral and also charge NV plus, which also have a possibility of existing within the same diamond sample. Right. So what do we do? You actually shine with a green laser, and then this is 532 nanometer, could be 520 nanometer, because you just need to excite these electrons. And then what you observe is this red fluorescence. And if you are able to collect the red fluorescence, you may see something like this. And this is a very special image because this is an array of NV centers actually that we are imaging. This is a very special sample where you can see that, the NVs have been imaged via a confocal microscope, so that you can actually do layer by layer imaging of an entire, say, 300 micron thick sample. So this is an optically controllable spin state. And why do I say that? Because if you look at the electronic structure of the NV minus, this is how it looks like. You have a ground state which is a triplet. So you have a degenerate plus minus 1 level and a 0, which is of the ground state 0, and then you have an excited state. So what happens is when you shine the green light, you excite this NV from its ground state to an excited state, and then it decays via emitting this 638 nanometer, and that is why you see that pink color. If you have many NVs, you will see the diamond becoming pink. And then there is an alternate path, which is there is a metastable state here. So every once in a while you can actually decay via this metastable state, which is a non-radiative. This is a non-radiative pathway, and whenever it goes to this metastable state, it will always come back down to 0. So essentially what you can do is you can actually polarize the spin state. So if you start from plus minus 1, eventually over time, if you keep shining the green light, it will just go down, decay to this metastable state and come down to 0. Now, the most interesting thing is now you can always apply a magnetic field, and the magnetic field, as you know, with a Zeeman effect, you can split the plus and the minus 1 levels. And therefore, what you can now do is you have created sort of a pseudo 2-level system. So either you can resonantly interact with the 0 plus 1 or the 0 minus 1, whichever level of your choice, depending on the experiment that you actually want to do. You have now formed a very nice looking qubit here. Of course, there are many more complications to this system, because as you can immediately see, if you look at the lattice structure of diamond, you can have a nitrogen vacancy probabilistically, but you can also have a nitrogen that did not convert to a nitrogen vacancy because there was no vacancy next to it. So there could be some hanging around nitrogen, which are called P1 centers. Then another kind of impurity that could be there is the carbon 13, which is essentially the isotope of carbon 12, and therefore that also acts like an impurity, and any impurity essentially behaves like a little toggling magnet around this system. And any toggling magnet is like, causes decoherence in the system. So the purer your system is with only NV minus, the better your system will be and more your coherence time will be. But then again, more coherence time also means that it's going to be a little bit challenging, because you have better coherence time, of course, is what you want. But then if you have all these P1 centers or carbon 12, carbon 13 centers lying around, then it's not going to be a very useful system. So typically in an ensemble system, and ensemble meaning if you have 10 to the power 13 or 14 NV minus per centimeter cube, a typical T2 star at room temperature is about 1 microsecond. Whereas if you have single NVs, then you have T2 stars of 500 microseconds or more. You can add dynamical decoupling to it, and you can get better and better coherence time. So NVs centers are very good room temperature qubits, and also these can be used in addition to the electronic spin which is here. You also have the nuclear spin from the nitrogen, which is also a spin 1 if it is an N14. But if it's an N15, then you have a spin half system next to it, and a carbon 13 also acts like a nuclear spin. And these in fact act like, so if I want to tie into Urvashi's talk, these actually behave very good like repeaters and memories. So you can actually store the information up to milliseconds and even up to seconds. People have shown with NV centers. NV centers actually can work very well as quantum repeaters as well as for quantum nodes. Like you can store information in these NV centers. But of course, again, like she said, the challenge is that you need to have very long time scales, and milliseconds and is really not a number that you would want. You would want to go really more than seconds if you want a memory, right? So therefore the better it is, the you can do the better task, right? Now, so how do we actually polarize and read out, and what do we do in a real experiment? Right, so we apply this sort of a microwave which is on resonance with the 0 plus 1 or the 0 minus 1. The first step in our experiment would be actually to polarize. So polarize just requires a green light. So you keep pumping with the system with a green laser, and after some amount of time you will see that all the NVs have come down to the 0 state, because it has even if it starts from plus or minus 1, every once in a while it will always go down to this metastable state and decay down to 0. With 0 it will always, if it starts from 0, it will always come back to 0. It's a spin preserving state, right? So once we have polarized, then we read out. You can also read out, because when you apply a microwave, essentially what you do is that you, every time you apply a microwave on resonance, you can shuttle back and forth between the 0 plus 1 and the minus 1. And whenever you go to the minus 1 or the plus 1 state, essentially you fluoresce 30% less than if you were to start from 0. And that's how we actually distinguish between the ground state 0 and the plus minus 1 levels. Okay, so that's how we do the experiment. And then of course, if you have an additional microwave or magnetic field, that will shift the level. And so if you can measure this shift, you can actually measure any externally applied magnetic field. That's the real principle of working of an NV center. Okay, now this is a very gifted system, because you can have vacancies not just in one of these arms, but you can have vacancies in all 4 arms of the carbon, because the diamond, if you remember, this is the diamond lattice, and you can see that the red ball can move around in all 4 arms. Now, what advantage does that give us? So if you have 0 field here, you can see that these are 2 lines. It's an N15 example, because it has a hyperfine. So it will split into N15 means this is just a hyperfine interaction. So you can see 2 structures here. So spin half system, so it will split into 2. But then if you apply a single axis, you can see on this is the 0 field is at 2.87 or 28707 here. And so you will see on 2 sides, because the field is very well aligned along this direction, and so there's the other 3 sort of clump in at one location, and that's why you see 2 on one side and 2 on the other side. Now, the most interesting thing is that when you have a vector field, which means that you don't align anything, you can see all 4 peaks on one side of the zero field splitting, and another 4 peaks on the other side. Now you have a lot of information here. You can completely reconstruct back the magnetic field by using this vector sensor. So that's how an NV sensor actually works for measurement of vector magnetic fields. So what do you do if you have such a vector magnetic field sensor? Like I said, one of the interesting applications would be if you could measure the neuronal signal, right, which is of the AP or the axon potential, right? But then there are other extremely very nice examples where you can use this sensor. For instance, it has been shown in 2016 that you can use this NV center for looking at the magnetic field profile of a hard disk, for instance. Now, this could be any magnetic material or 2D material, for instance. Then this is the example that I already gave you, which is of measuring the magnetic field profile from any biological neuronal signal. So here, this is a C. elegans worm. Now, this C. elegans is a very dumb worm. It has only one neuron, so it doesn't have many, doesn't have any complications, and it was shown that an NV center could measure very nicely the neuronal potential and show you the neuronal potential of this C. elegans worm. And in a very contrasting application, you can also do some geomagnetic field kind of sensing, right? So what are the numbers that we are talking about here? The sensitivity as to date shown is that the DC sensitivity can go up to 50 picotesla per square root hertz. And then AC can also be even better. You have 0.9 picotesla per square root hertz. The advantage here is that you are diffraction limited to 250 nanometers, but can use optically enhanced techniques like STED, for instance, and go up to 5 nanometers. Of course, if you compare this with a squid, you can never beat the femtotesla kind of sensitivity of the squid. But then here, the advantage for us is that you can actually do this at room temperature, but with a 400 cross 400 micron field of view, and all at the same time. You can get several, diffraction limited spatial resolution. So that's really the key advantage of this kind of a sensor. And you can actually couple this with squid, for instance, and do very nice, wide field imaging. Now, what limits us in the sensitivity? Clearly, if you have many sensors, when you have an ensemble of sensors, you can gain with a square root of n if you use many sensors like this in many NV sensors or the ensemble setup. But then you are always limited by the coherence time, the T2 star, for instance. So what can we do to make life better? We can, of course, use really the power of quantum mechanics here, or use quantum enhanced techniques, and you can get squeeze states. And that's really the advantage of using these quantum sensors, is that you can get various different types of other sensors, and you can go down to the Heisenberg limit and go down to the n/n scaling of the sensitivity. So what have we done? So we've actually put together this quantum sensor. We have a sample, we have an objective, use a green laser with a 532 nanometer wavelength, and use a 60x objective, focus onto a sample and collect the red light from this sample. Sometimes we do it with a single photodetector, or sometimes we do it with a CCD camera. And we have some, additionally, we have this microwave, as you know, required to do the measurements for the ESR. And in addition, we do some other external things. Here, if you see, this is an image of the actual experimental setup. You have the laser, you have an acousto-optic modulator. You would like to chop the green laser and perform experiments whenever you want. So that's just the role of the acousto-optic modulator. And so you send it down to the diamond, which is actually sitting here. You can see a lot of green light here. So the diamond is actually here. So objective, the diamond is sitting on an antenna. The antenna is used for exciting the microwaves. Now this image actually shows you the red light. So if you look carefully, this is the diamond sample. From the sides, you can see some red light coming out. That's essentially the fluorescence that we observe. Okay, so that's what we collect, but here we are actually using the objective and collecting it in the back path directly. We don't actually collect using side collection, but one can also do side collection to collect out all the fluorescence. Now, here, this is a very nice image. I'm very fond of this image. So essentially, this is the microwave antenna. We have two different types of microwave antennas. This image is a fluorescence image of the diamond. So the diamond is actually like this. And the diamond is sitting on the microwave loop, which is an omega. So you can see the fluorescence, which is in orange, which is an omega. And then there is some, significant sort of fluorescence coming from this region, which is the loop region. So this PCB that we have actually also fluoresces in the same wavelength as our NVs, unfortunately. So we have, that's why we actually have a hole in the center. So if you look at it, this is the hole in the center, and that's where we probe most of our NVs. We are not really using the full sample here. This is a 3 millimeter by 3 millimeter sample. So you can see the red light that we just collect from this diamond, right? So what do we do with this red light? Well, of course, we want to look at the ODMR. That's the first step. And like I promised when I showed you the cartoon image, you were forced to believe, for instance, that, well, they should have 4 peaks on either side of this, 2.87 zero field splitting. But here I'm showing you, this is data from the diamonds that we have in the lab. You can see 4 peaks on one side, 4 peaks on other side. They have various different, amplitudes depending on the magnetic field they see. They also have, the locations are also defined by the magnetic field. But if we also go beyond just doing the standard ODMR, we do a modulation sort of a spectroscopy here. We apply this, do a lock-in technique here, and we modulate the microwave field. And here you can see at zero field, you will see the typical lock-in kind of signature of this, the Lorentzian. But you see that there is this split, it's not a continuous one. And this split actually comes because of the fact that this NV center also sees electric field. So electric field can also add to this, in addition to the magnetic field, it will also see the electric field, and this contributes to this sort of a splitting. But this is only at zero field splitting because the coupling of the electric field is very, very small. And so you see this field at zero field, but as soon as you apply another sort of a magnetic field, and you can see that now it looks like a very nice sort of a lock-in signature, where you can we don't have this anything funny going on in the center. So the peak is not split at all. So for instance, look at this one where you can see that all the 4 peaks. So this is actually 2 peaks very close by, and you can see all the 4 peaks nicely about the 2.87 center. Now we've done sensitivity measurements for our sample, and we get up to 50 nanotesla of sensitivity. And what we have done is we sit to do some sort of a dynamic magnetic field measurement. We use an external coil. So just like a Helmholtz coil, just one part of that Helmholtz coil, we apply an oscillating magnetic field. And what we then do is we measure the shift. So essentially we sit at one point, and then by whenever we want to measure this magnetic field, we keep switching this additional magnetic field. And you can see that the red is the applied actual magnetic field, and the NV center very nicely follows the magnetic field, and we are able to measure this magnetic field with very high precision. Right now, this is an integrated signal that we are measuring, but what we have shown, and this is for the first time, is that we've gone and done a lock-in sort of image of this NV center in wide field, which means that in this entire field of view of 260 micron in the diameter, you can see that each of these pixels are actually, there's a lock-in detection that we have done. And you can see this is the signature, the ODMR signature lock-in per pixel. These are some example traces. So you can very nicely see the various peaks that appear from the ODMR, and very similar to the integrated signal that we can obtain. This is obtained via a CCD camera by doing per pixel lock-in. Now, what is the advantage of doing a per pixel lock-in? So essentially what we did is we repeated something that we did to the single pixel sort of or the integrated signal, which means that we applied a modulated magnetic field externally and measured the magnetic field. So here we do a per pixel lock-in, and you can see that as you keep changing the modulated field, you can see that the contrast also changes here. So here you're actually measuring somewhere between minus 100 microtesla to about 100 microtesla of field, and this is using the per pixel lock-in. Now, what I want you to observe here is that, well, you can measure the microwave field or the magnetic field here, but what is the advantage of this per pixel? So if you look at this reference, wherein they have actually measured the magnetic field from biological samples, and look at the time scale here. So this is 120 minutes, okay, 120 minutes to 210 minutes. You can see that it takes at least about 10 to 20 minutes to obtain each of these scans. Okay, now what we have done is we've gone from minutes, several minutes, to several seconds. So you can see here, this is we are doing at seconds of resolution. We are able to immediately measure the field. So that's the advantage that we have over the, what is in the current world status. This is for the first time we've been able to show that, we are able to do very fast imaging of magnetic field. And these are some of these example traces where you can see just picked up from some random location on this sort of a image. You can see the magnetic field going up and down. This is the applied magnetic field. Of course, there are various challenges. You have lots of things to worry about because you have fluctuating, there are many things that are fluctuating, and so if the resonance frequency fluctuates, then you essentially lose the your measurement capability. And that's not because of sensitivity, it's because there is a drift in the resonance frequency. So if you are not able to stick to your center resonance frequency, you'll never be able to measure very well when you have a dynamic change that you want to measure. So we are actually working on this and fixing up those problems, and in the process of writing this thing up so that we are able to claim this very quickly. So with that, I would sort of point you back and sort of link you back to the original goal that we wanted to address. That is, we want to measure something like this. This again is a C. elegans worm, which has only one neuron. But what we want to do is measure something which is as complicated as a network of neurons. And we want to actually look at this, each of these location of these neurons by using this idea of measuring the signal from each of these neurons. And recently we have published in in communication physics as to how we can actually, if you have the magnetic map, then how do you reconstruct back this entire the location of this neuron, because they're two independent problems actually. So the first step is actually to measure the magnetic field map, and then the second step is to actually reconstruct back the location of the magnetic field. So we've actually gone the reverse way. We've developed the protocol for doing the location, pinpointing the location, and now we are working on the actual experimental method for measuring this wide field magnetic field. So of course we have a lot of problems, and with that I would like to summarize. Our significant challenge is the magnetic field for each of these neurons, unfortunately, is in the picotesla regime, and we are at nanotesla for currently. Per pixel is even worse. We are at microtesla sensitivity for per pixel. So there's a long way to go, but the problem is well understood. We have to work on several things regarding the setup, the sample. There's a lot of instrumentation that needs to be developed for this particular challenge. It's a problem that we are working on with several steps in mind, and hopefully we will get there. But in the interim, there are many other such problems that we could look at, even with the existing nanotesla sensitivity that we have in our setup. So with that, I would like to thank you, and I hope I am on time. This is the group. The work essentially being done on the wide field image is being done by Madhur, and he's been working on the setup primarily on this, and we have some other projects going on in the lab where we want to essentially look at some solid condensed matter samples where with very interesting magnetic field properties, and also measure stress and other vector magnetometry kind of experiments that we are interested in. With the same diamond microscope we should be able to look at. So thank you very much for your attention, and I can take some questions.
Thank you very much, Professor, for the lovely talk. The floor is now open for Q&A, and I can see A. Gopal has raised his hand. Professor, over to you.
Hi, Kasturi. Yeah, good to see lots of results from your lab.
Thank you.
Yes. Yeah, I mean, as I understand, your diamond has many NVs, and these are randomly distributed.
Right.
Right. So what kind of spatial resolution do you get eventually? Like what's the spatial resolution you are getting?
So with the wide field microscope, currently we have a spatial resolution of 4 microns. That's with the current sensitivity we have. And also the pixels, the number of pixels we have in our CCD camera. But we can definitely do a few more things and come to 250 nanometers spatial resolution.
But how do you isolate? Like, so if you have two NVs close together, like, so you'll have the...
We don't isolate. Actually, we don't absolutely. So for an ensemble system, we don't want to isolate at all.
But the second stage, you need for image reconstruction.
Sorry.
Okay. So for the second step which you want to do of image reconstruction, like, so for that, like, you need to resolve two closely spaced signals, or something has to be done, right? Or otherwise,
no,
like
we do a different way altogether. So what we do is essentially, that's a different problem that what we do. So what we say is that, well, the signal actually, it turns out, and that's the problem looking at it from the neuron perspective, and I'm just saying from the neuron perspective, that the signal, as it turns out, that the cell body actually has a lot more magnetic field than the actual dendrite. Okay, or the axon. Now what we can think of it is that it's like a localized ball of magnetic field. So instead of a wire approximation, you just have sort of a, a point kind of a source that is giving you the magnetic field. And then what we do is we have these, we've developed this sort of a protocol by using this matching pursuit based kind of a protocol, where we do a matching between the magnetic field that we would observe if a certain neuron were to be sitting in a certain location. Then what is the corresponding magnetic field we would measure. And then if you have a network of neurons, so we break the symmetry of this, as you know that any wire cannot be reconstructed back in 3D, right? So just by doing this magnetic field sensing, so we actually break that symmetry problem by applying the time here. So a neuronal signal is actually a millisecond long signal. So we know for how long the signal will travel, and we know how to distinguish between signals. So that's how we will actually pinpoint the location. And what we have, yeah.
Like, so this the current resolution will work very nicely for the biological samples.
Yes.
From the spatial resolution point of view. But I'm asking in terms of for solid state samples.
For solid, yeah. So actually for solid state samples, if you use, so with the lock-in detection you cannot do, but if you just use a very high resolution CCD camera, you will be able to get very easily to 250 yeah.
So what's the density of NVs you have?
So density of NVs is 10 to the power of 13 NVs per centimeter cube.
Okay.
Yeah.
Great. Yeah. Thanks.
I see Sandeep has a question. Sandeep, you can go ahead.
Hi, Dr.
Yes, Sandeep.
So you are measuring the magnetic field, and basically you have like many NV centers. From that, basically you are trying to get the magnetic field. But if you have a single magnetic single NV center, will that like increase the resolution of the magnetic field? Like, can you go lower? Like right now you are measuring nano Tesla.
Yeah, I mean, that's so essentially what you're going to do is you are collecting the red light from many NV centers and projecting it onto a CCD camera. Now, depending on the whatever megapixels that you have in your CCD camera and the objective lenses that you can use, you will be diffraction limited to your sensitivity. That's essentially what you will get. You will be diffraction limited on your spatial resolution essentially. So with so that's got nothing to do with actually single NV centers. If you just probe, you know that you are spatially, you're actually just using a confocal, and you know that it's diffraction limited to 250 nanometers. But you can also do the same thing with the CCD camera, and it really depends on the your camera specifications there.
So it doesn't matter like how many NV centers are there.
No,
right?
it matters because your
the sensitivity of the magnetic field.
the sensitivity of magnetic field and spatial resolution are two different things. Sensitivity will be very high if you have many NV centers, right? So spatial resolution is limited by your whatever your diffraction limited optical spot that you can get. That's your diffraction limit will give you the spatial resolution, but sensitivity for a single NV center versus an ensemble is just goes as square root of n, as you know. But if you use better techniques, you can go up to 1/n.
Thank you.
Any other questions? I don't see any questions here. Sure, I have a question. What are the typical power levels we can see so that with the minimum power level with which you can see red even with the naked eye?
What's the minimum power?
Say we are not using in the confocal setup, just in the
so
beam path.
actually, you can see it with few milliwatts. You can actually see with naked eye. So actually about with 5 milliwatts. In fact, the samples that you gave, we saw it with 5 or 10 milliwatts, right? So we saw it, you can clearly see it with naked eye. 10 milliwatts, you will be able to see the red light very clearly. Yeah.
Okay. So I guess there are no other questions.
Avan,
yes.
Sorry, I was holding back because I don't have a question on this particular talk, but a very generic question. So Kasturi, I mean, I just from somebody totally outside the field, with diamond, people talk about NV centers like you did. Some people also used to talk about silicon vacancy centers. Correct?
Yes.
What? I mean, which one of these? What are the specialties of the two? How do you compare the two?
Yeah. So let me go back to the very first image that I have shown. Let me see 1 second. I'll tell you what is the difference. So so the difference essentially comes from, so if you look at this, the PL, can you see this slide which has the PL spectra of various different samples? Right? So if you look at it, the NV0 has this little spike and the NV minus has this little spike. So that's the zero phonon line essentially that corresponds to the NV minus. Now in this zero phonon line is only 3% of light of the entire PL spectrum. So if you want to do any kind of qubit operation, then all you're interested in is in this zero phonon line region fluorescence, right? And that's a very tiny part for an NV minus. For a silicon vacancy, unlike the NV minus, about 70% of the light is actually in that zero phonon line itself. So if you want to use it for a single photon source application, then it is better to go for a silicon vacancy, and which is why people have been working on silicon vacancies as single photon sources, and other types of defects. Also, people want to get more light into the zero phonon line.
Oh, okay. So do the two have kind of different applications, utilities?
Yes, but again, silicon vacancies turn out to be more complicated in terms of the electronic level structure, magnetic level structure. And recently people have also found out like silicon vacancies in silicon carbide have very similar kind of level structure, electronic level structure for like NVs. And therefore, so similar like ground state, which is a triplet degenerate, you can apply, microwave and do manipulations. But you also have the advantage that you have a zero phonon line, which has very high amount of optical properties or coherence. And so things have evolved in that sense.
Okay, got you. Thanks.
Yeah.
Thank you.
I don't see any further questions. Thank you very much, Professor, for the lovely talk.
Thank you. And so do I have to carry out my duty right now? I guess we'll
let you not immediately.
Okay.
And I now ask the host to take over the over to you, Himadri.
Thank you, Pawan. So with this, we are now officially ended with the talk session of our SCAO 2021 conference. And heading forward, we would have our closing ceremony. So I'd request every one of you to please switch on your cameras so that we can all be a part of this closing ceremony now. And so first and foremost, I'd request words from the chapter advisor. So Sushil, you may please proceed ahead.
Yeah, thanks, Himadri. So, okay, I won't take much time of all of you. It's already evening of the second day. But right, it's actually a great feeling for me as a chapter advisor for this chapter, which was materialized purely by the hard work of these kids sitting there. Okay. By the looks of them, they don't always look like they can pull something off, but they did massively. And I want to hark back to Urvashi's comment about me being extremely efficient in getting this done. And I should tell Urvashi that you are only partly right. Okay, I did one thing very well, and that was nothing. I made sure that I did not interfere because I would have surely messed up in the whole process. And for those of you who may have attended Ravitej Upu's talk in the afternoon, who was an earlier student in our lab, he mentioned that there was an earlier attempt once. There was another attempt a couple of years later after Ravitej had left. But I don't know, it just takes a few factors to come together by itself. And well, one thing, of course, is a sufficient number of students willing to share the responsibility. Other one is shared enthusiasm and some kind of an impetus. Okay, some kind of an impetus was required for everything to become coherent. And I think that came in the form of the international review, which TIFR, my department, went through a couple of years ago. And you may know Professor Philip Russell, the photonic crystal fiber guy from Max Planck. Professor Philip Russell is in Max Planck Institute for Science of Light in Erlangen. He was the inventor of the photonic crystal fiber, and he was a part of the international review committee for our department. And he came and interacted with all the students, and somehow he managed to give that big jolt. Like, okay, you guys have to have an OSA student chapter. And that seemed to have clicked with all the students, and suddenly I find them all talking and working enthusiastically. So the good thing about the chapter formation is there isn't much paperwork. There are duties and you have to take care of a few things. But OSA has actually made it simple for all students. So any students from other institutes listening, yeah, they should take this opportunity. And I must say I'm extremely impressed with all these students, because the procedural part of the OSA student chapter was one part. The second one was the COVID part, because by the time the acceptance from OSA came, we were bang in the middle of COVID and nothing could move. I mean, the plans that were given earlier, of course, were seminars at that time, visiting professor, conferences in person and so on, but they knew that nothing is going to happen. But they stuck to it. They knew that we can't just sit there doing nothing. So I'm glad that they worked out 2 or 3 programs, believe me, but this one seems to have materialized already, and there's something coming up in less than a couple of months. So again, congratulations, guys, and I'm really feeling a sense of pride. Like I said, you guys casually worked together, were casually working towards it, so it didn't really appear outwardly until I saw when you came to me that this is what we have decided, and that was really impressive. Some of us have organized conferences before, so we know the hard work that goes in. And so I must say a pat on the back, very well done. And behind this activity success, of course, is the general optics community in India, part of which is sitting in front of you, all the students and faculty. So like you heard every faculty member mention that, okay, this is organized by the students. So yes, I want to do something. And that sentiment is there in the optics community, all faculty in India that you will experience. So I'm very happy to be a part of this optics community. Whenever something from the student comes up, the community is right on its toes. Yes, we will help you. We will support you. So thanks, guys, sitting here, all Kasturi, Urvasi, other faculty members who came and gave a talk, and all students. Well, you are all colleagues and contemporaries. So I'm sure at some point, these organizers are going to be in your student chapter meetings. So please make full efforts to come together and do something together. The rate at which chapters are increasing, very soon we will be having events organized by multiple chapters coming together. So the scale is only going to grow, and eventually we all hope that the optics photonics community in India grows on an exponential scale. So once again, congratulations to the team. Thanks to the guests, and it's a great pleasure to see all of you attending the conference. Thank you very much, Shivadri.
Thank you, Sushil, for that motivational speech. We are really pumped to know that you're so proud of us. And of course, we will make you more proud as we go forward. So
yeah, I realize
organize more such events. And we have a planning on doing a YouTube review as well. Interviews as well.
Himadri, I realize it can come across very easily in our normal interactions, but I am.
Sorry.
Yeah,
okay,
go ahead.
So So next, I'd ask to deliver the vote of thanks. So Vikas, I'll hand over the mic to you.
Okay, so this responsibility has been given to me because I did the least amount of work in the conference otherwise. So first and foremost, I'd like to thank all the participants who are present here, and also all the speakers who have taken time from their schedule and have attended this conference. This conference, SCAO 2021, would not have been possible without everyone's involvement. So I'd like to thank Himadri for managing all the communications through email, and Ravi Shankar for the website development, Raunak and Krishna for preparing the slides. So if you noticed any typos, you know whom to blame. Sandeep for managing the Zoom platform as the host. Following which, I'd like to thank all the chairs, apparently including me, Himadri, Krishna, Ankit, Aparajit, Abhinav, Sandeep, Ravi, and Pawan. And also, I'd like to extend the thanks to all the other chapter members, Kiran, Divya, Chandan, Sonali, and Anandam. Lastly, we'd like to thank our advisor, Professor Sushil Majumdar, who consistently supported and enabled us to form this chapter and organize this conference. And also to all the judges who have attended this conference, and we'll know the results soon. So now with that, we'll move on to the last event, which is the much awaited award ceremony. So I request Dr. Kasturi Saha to announce the winners for the best poster and best contributory talk.
So yeah, so I have this, I have to open this envelope with the names in it, and I'm going to do that right now from this virtually. And so the best poster goes to Nilamoni Daloi, a research scholar from IIT Guwahati, and clap, clap, clap for Nilamoni. And the best contributed talk goes to Arup Kundu, from research scholar at TIFR Mumbai. So clap, clap, clap. Thank you.
Yeah, so with this, we are at the end of the SCAO 2021 conference. And I hope you all enjoyed and you're leaving with some knowledge about the advances in optics. And I thank you all to make this event successful. And also request you to please fill out the feedback form that we have sent to your emails. So yes, we would really like to hear what we can do more and how we can develop ourselves so that the events that we organize in future would be even more better than this. And thank you all. With this, we are concluding our SCAO 2021 conference.
Okay, guys, can you just join me in giving a hand to the organizers, just virtually? Good one. Thank you so much.
बोल रहे थे
Join hands.